This is Duke University.
Hi, I'm Drew, and my colleagues and I would like to welcome you to Java Programming Solving Problems with Software. We here at Duke are so excited that you're taking this first step in learning to solve real problems using Java. In this course, you will learn a 7-step process designed to help you understand how to approach any programming problem. You'll use this process to solve real problems, and you'll learn that computer science is so much more than the syntax of a programming language like Java. You'll have a chance to work on problems such as analyzing DNA, manipulating CSV files, and processing images. These are real problems that engineers, scientists, programmers, and others work on in real life, and you too will be able to tackle these problems as you begin to learn Java.
I'm Susan. In this course, you'll learn to program in Java using techniques that can be used with simple programs, but that can also scale to larger programs and larger problems. The libraries and APIs we introduce make it easy to process data in many formats. You'll be able to use these same techniques, tools, and libraries in solving the problems we've designed for you. Problems whose solutions require the programming knowledge that you'll learn here.
I'm Robert. As you learn about the syntax and semantics of Java programs, you will practice with a programming environment that's been specifically designed and proven to help learners like you who are getting started in programming. This programming environment will let you design, test, run, and debug your programs using techniques that software engineers, scientists, and programmers apply as they design, create, and solve problems using Java and other languages. This programming environment can scale to large problems and is a great first step as you learn to master increasingly sophisticated concepts.
I'm Owen, and I'm really excited about the problems we've created for this course. We've used our collective years of experience to simplify problems and to provide you with opportunities to demonstrate your mastery of Java programming, while you work on real problems that are only slightly simplified from those problems faced every day by those working in the many fields that use computational and programming approaches. We've designed our Java libraries in a similar way, using standard Java idioms that you'll see if you continue to study programming, but that are more easily used by those just getting started with Java.
Once again, welcome to Java Programming, Solving Problems with Software. See you in the course!
Hi, I'm Elizabeth. I'm part of the instructor team here at Duke University. Before you get started with this course, I want to make sure you're aware of some important resources and give you some tips for doing well. The assignments in this course will be programming exercises, so you'll practice writing code. Anything labeled programming exercise here in the course content is an assignment and contains instructions to help you write your own program. When you've finished writing your code, there will be a practice quiz where you can check your program works properly by comparing your results to answers provided by the instructors. I also want to show you the course site, dukelearntoprogram.com. You can see we have a page for each course and a page of frequently asked questions about the specialization. This has everything from certificates to the software we use in the course. If you go back to the home page and select the course you're working on, you'll get to that course's main page. So I'm using course 2 here as an example. What I want to point out now are project resources, documentation, and the frequently asked questions page. Project resources is where you can download code to follow along with the video lectures or to begin the assignments. Documentation has a summary of the Java methods you'll learn in this course. This is useful if you forget the name of a method or if you want to find out if there's a Java method to accomplish a particular task. It's not an exhaustive list of all Java methods, it's just a summary of the most useful ones for this course. Finally, the frequently asked questions, or FAQ page, contains questions specific to this course. For questions about the specialization as a whole, click this link up here. So hopefully this video has given you an idea of how the course is structured and what resources you'll need to know about. If you have any feedback about how we can make these resources more useful to you, please let us know in the discussion forums on Coursera. To help you do your best, we want to give you some suggestions about how to learn in the course. First, do a little each day. It's really hard to learn programming all at once. If you do a few course items each day instead of trying to do it all in a day or two, you'll remember things better, you'll be more motivated, and you'll have more time to work through problems in your code. Speaking of problems with code, also known as bugs, it's normal to make mistakes when you're programming. So our next tip is, don't give up. Everyone gets bugs in their programs, and part of programming is figuring out what's wrong and how to fix it. When you're programming, we really recommend following the 7-step process. This means you should plan how to solve the problem before you start writing any code. If you didn't take our first course, don't worry, there will be a chance to review the 7-step process later. The 7-step process is important because it gives you a method for solving problems. Then when you've figured out a solution, you can start writing code. Once you're ready to start writing your programs, make sure you've read the relevant documentation so you know what Java methods exist and how to use them. Refer back to the documentation as often as you need to. Next, take advantage of the live coding videos and the practice quizzes. For the live coding videos, this is a great opportunity to program alongside the instructors. You can also download the code from the videos and run it yourself. Try making small changes to make sure you really understand what each part of the program does. Finally, for the practice quizzes, even though they don't contribute to your final grade, there's still a good chance for you to test your code. Use the practice quizzes to find and fix problems before you move on to the graded quizzes. Finally, if you're still having trouble with your programs, ask for help from the instructor team and your peers in the course discussion forums. Part of being a good programmer is knowing how to ask for help effectively. We'll talk more about that in the next video. It's completely normal to struggle with learning programming, and when that happens, the instructor team and your peers in the courses are here to help. The best way to ask for help is through the discussion forums, which you can find here. You can also answer questions in the discussion forums, and we really encourage that, because explaining programming concepts is a great way for you to learn, and you also get to help out one of your classmates. Here are some general tips about asking questions in the forums. First, before you start a new topic, you should check the FAQ pages on DukeLearnToProgram.com and existing forum threads to see if your question has already been answered there. The first thing you should do when you have a question about a programming assignment or a quiz is check the FAQ page for that course. Second, start a new thread if you have a new question. Don't post your question as a reply to an existing thread unless it's really closely related. This way it's easier for people to see what your question is about and help you more quickly. Third, if you need to post code, use the code formatting box, which is the one with this symbol on. This is much easier to read than if you just copy and paste it directly into the post. We also want to give you some tips on writing a good question so that others can help you most easily. If you're having trouble with a programming assignment, name and link to the assignment you're working on. If your program is throwing an exception, you can post a screenshot of the error message and also the line of code that it occurs at. If your program is producing a result that's different from what you expected, make sure you say what input you're running your code on, the output you expected to get, and the output you actually got. For example, suppose I'm trying to write a program to change every green pixel in an image to blue. I should share the image I'm running my program on, my input. I should explain that I'm expecting every green pixel to become blue, my expected output, and I should also explain that every green pixel is actually becoming red, my actual output. Then others in the forum can better understand the problem I'm having. If you have to share some code because others can't help based on the description of what your program is doing, it's okay to share a few lines of code, but don't share your whole program. Figure out which part of your program you think the error is in, and share a few lines of that method. Don't copy and paste your whole program into your post. If you have a general programming question, such as how do I write a for loop, or how do I add items to a list, it's okay to post those lines of code because they're so general. Finally, if you have a conceptual question, make sure you name and link to any course materials you refer to. When you're answering questions, it's okay to share code for general programming concepts, such as how do I write a for loop. However, if someone is having a problem in their code, don't give them the solution. Try to guide them towards fixing their code themselves by giving hints. If you don't know what the problem is, suggest what they might do next to debug their code. Let's look at some example posts. In this post, I didn't really ask for help very well. I said my code wasn't working, and I asked if anyone knew what might be wrong, but I didn't really explain what the code is trying to do, what it's actually doing, or what troubleshooting I had tried so far. I also posted a lot of code. So I edited my post, and now it's much better. You can see that I explained which assignment I'm working on, and I provided a link to it. I also explained what happens when I run my program, so my actual output, and what should have happened when I run it, so my expected output. Finally, I only posted a few lines of code that I thought the problem was in. Now that you've learned how to ask and answer questions about your code, you're ready to start learning how to program. I hope you enjoy the course, and I look forward to interacting with you all in the forums. Good luck!
Hello. We wanted to take a moment to tell you about a specialization created by instructors from Duke University and the University of California, San Diego. It's called Object-Oriented Programming in Java. I'm Owen Astrachan, one of the instructors from Duke University, and I'll be helping you learn this specialization. We're going to start from the beginning with Java and learn how to use it to write programs to solve a wide variety of problems.
I'm Susan Roger, and I'm another one of your instructors from Duke University. We'll start out with the basics in Java. So while we hope you have some programming experience already, we're going to assume you don't know anything about Java, but that you are eager to learn.
The next course of this specialization is Java Programming, Arrays, Lists, and Structured Data. I'm Robert Duvall, and I'm excited to be teaching you about Java. In our next course, you'll dive more deeply into Java and learn to store data in more complex ways, allowing you to solve even more interesting and exciting problems. I think there's even a dinosaur in one of our examples.
And I'm Drew Hilton, and I'm your fourth instructor from Duke. After you learn these Java fundamentals with us, our friends from UCSD will take over and teach you even more exciting things about Java and object-oriented programming. We'll let them introduce themselves to you now, and then you'll see them again in a couple of months.
Hi, I'm Mia Minnis. I'll be one of your UC San Diego instructors. You'll meet us when you get to the third course, Object-Oriented Programming. In this course, we'll build on the programming concepts you learned from our friends at Duke, and then we'll also talk more about the object-oriented nature of Java and how you can use it to build bigger programs to solve more complex problems.
Hi, I'm Leo Porter, and I'm an instructor at UC San Diego. Another topic that you'll be learning in the third course of the specialization is graphical user interfaces and event handling. With these skills, you'll be able to build interactive applications that are both easy and intuitive to use.
I'm Christine Alvarado, the final instructor on the UC San Diego team for this specialization. I want to tell you a little about the fourth course in the specialization. In that course, you learn how to store data more efficiently so your program can quickly perform operations on large sets of data. By the time you finish that course, you'll be a pretty good Java programmer. So let's get started.
Hi. In this lesson, we're going to introduce you to Java programming and the BlueJ environment we use in this course to design, develop, test, and run Java programs. Java is a popular and widely used language. It is the foundation for the Android operating system that powers more smartphones than any other system in the world. Java is an extremely useful and quite powerful language, with extensive support on almost every kind of computer. Java is also accessible to beginners, which is why we're using it in our courses. At the end of this lesson, you'll have experience with BlueJ, the development environment we use for programming with Java. You'll be able to use BlueJ to compile and run a Java program. You'll know the basic design, edit, compile, and execute cycle that's part of programming with hundreds of different languages. And you'll see firsthand how simple and powerful Java is in accessing information that will print "Hello World" in many languages. This is our take on a traditional first program. We'll explain that more as you begin your exploration of Java programming. So, hola mundo, konnichiwa, zdravствуйте, ni hao, and hello world. Let's get started.
Hello, world of learners. In this video, we will look at how code is organized in Java and how programs are executed by the computer. We will also demonstrate how to run programs in BlueJ, the programming environment you will use in this course. Java is an object-oriented language. This means you'll use classes and objects in writing your code. Classes are a way of organizing your programs, and objects are created using classes when your program runs. We'll learn more about objects and object-oriented programming in the next course. Classes have a .java file extension. In a Java class, you will write one or more Java methods, instructions for your computer to carry out when you run your program. The code you write is called source code. Source code is high-level code, which is human-readable but not machine-readable. So when I open this Java class here, I can read the Java program one of my fellow instructors wrote in it. Now, in order for the computer to run my program, my source code must be translated into low-level bytecode, which is machine readable. Bytecode files have a .class file extension. This process of translating source code held inside classes into bytecode is called compilation. When you write Java programs, before you run your program, you will need to compile it. So, where do you write this code that will eventually be run by the computer? Programmers write code in programming environments. In these courses, we'll be using a particular environment called BlueJ. We chose BlueJ because it's a great programming environment for novices. It allows you to start programming without having to worry about editor complexities. And we've added some special features that you'll use as you develop Java programs for this course. You're going to run your first Java program. We're going to show you how to download it from the Duke Learn to Program website and then open up BlueJ and run the program. So I have the Duke Learn to Program website up right here, and we're going to go to Course 2 and click on there. There's lots of resources that we have provided for you on this website. Since we're going to run a particular project, we'll click on Project Resources. And here you can see our first program called Hello World, the BlueJ project. I'm going to click on that, and that is going to give you the Java program and the data file. So if you just click on that, it's a zip file, and we'll just unpack it and you'll have everything there. So I am now going to start BlueJ. So you should have already installed BlueJ. I'm going to click here, and BlueJ is going to start. And for me, I've already got the program there, but if you don't see it, you may have to click up here on Project and Open Project, and you'll have to go to where your project downloaded to, which folder it's in. Once you have it there, you'll see Hello World. So let's click on that and see what's there. This is your Java file. And here you can see the code for this. I'm just going to scroll over so we can see a little bit more. So this is a class, Hello World, and it has one method in it called runHello. And this is a very simple program. What we're going to do is we are just going to open up a file and we're going to print every line in the file. Each line in the file is a greeting from some country. So we're going to create a file resource, and you can see we're going to tie it to the file called hello_unicode.txt. We are going to assign it to a file resource called res. And then what we're going to do is we're going to loop over the file. So we have a for loop where we are going to, every time we call the file resource res.lines, it gives us another line from the file. We're going to assign that line to the variable called line, and then you can see the line inside the for loop is going to print that line. So that's what our program does. In order to run the program, we are going to right-click on Hello World here. You can see all the diagonal lines there. That means we haven't compiled the program yet. You need to compile the program so your computer can understand it. So we will right-click here, and there's a compile, so we'll compile it. If everything works good, you see the slanted lines disappear except for just the two in the right corner. And then that means it's compiled, it's created the class file, which is a machine readable code that the computer understands. So now we can right-click on that and create an instance or an object. You can give it whatever name you want. I'm just going to leave that name there. And so the object has been created, and now we can run it. So I'm going to right-click on here, and you can see that method runHello is right there. I'm going to run it, and voila, we have just printed all the lines from the file. And you can see all these wonderful greetings here. We have hello, hello, bonjour, guten tag, aloha, all of these nice greetings. Now I want to show you where these come from. There is a file that you are also downloading and I have a copy of it right over here. Let's see, let me get this. So this is the file hello_unicode.txt, and you can see the exact same lines that we printed here. All here. Bonjour, Guten Tag, Aloha, all of these are right here. So our program, again, let me just come back to our program right here. Again, just real quick, we open up the file. You saw the file. We go over the file. We create a file resource and go through one line at a time in the file. We grab the line and we print the line. And that's it. So hopefully you've gotten your program to run, your first Java program, and you've enjoyed it. Thank you.
Hello, we're going to learn how to calculate the perimeter of shapes using Java. We'll use what is called a Java class, which you'll learn more about soon, named shape, to model polygons in geometry. These kinds of shapes are used in many applications. For example, a triangle is the simplest polygon or shape. It's simply a collection of 3 points. But triangles can be combined into complex shapes that are colorful or form the basis of wireframe diagrams used in computer graphics and video games. We'll use a shape Java class to represent a collection of points. We'll use a class for point and for shape to understand programming concepts that are applicable across many programming languages. We'll need to construct shapes by adding points one at a time. This will allow us to create shapes like this 6-sided shape, which is constructed from 6 points. Here is a shape with 5 points. Here is another 6-sided shape. The order in which the points are added to the shape is important. When we look at the code for the Java shape class, we'll also need methods for accessing the points, either one at a time or using other approaches. We'll likely want to create operations or methods that use shapes, like drawing a shape or finding the perimeter of a shape. We've seen that shapes can have many points. Our shape class is simple, but we could expand it to create complex shapes of many, many points, like this butterfly. When viewed more closely, it's clear that the butterfly is simply a collection of colored triangles, like the wireframe drawing we saw earlier. The shape class we'll look at is very simple. Circles aren't really a finite collection of points, so circles and some other shapes are harder to model using our Java class. In geometry, a circle is an infinite collection of points that are all the same distance from the center of a circle. Our Java class is just a finite collection of points. However, even with our simple class, we could model a circle using many points as shown in the diagram here. So even our simple class will prove very powerful. After we cover some of the basics of writing programs in Java, we'll explore the point and shape classes in more detail.
Okay, you will be using the Java classes shape and point, but what will you be able to do with these classes? Well, in some ways, you know the answer to that. You will be able to draw shapes or calculate a shape's perimeter, but just knowing what a Java class or script can do does not mean you understand it. So the question we are going to answer now is, how would you understand what this code does by yourself? That is, what are the semantics or meaning of each part of the code? Understanding the precise meaning of code is important because you can't write code without saying precisely what you mean. When we talk about understanding the semantics of code, what exactly do we mean? We mean, how would you execute the code by hand with nothing but pencil and paper? This skill is very important for a couple of reasons. First, it's how you understand code well enough to write what you mean. Second, when your code does not behave as you expect, how do you figure out what is going wrong? You need to understand what it does, and this gives you the skills to do that.
Hello, we're going to start learning to execute code with the most basic statements in Java and build up to more complex statements from there. Here we have 2 variable declarations, one for an int called x and one for an int called y. If we execute these statements as is, we will create boxes labeled x and y to hold the values we eventually decide to put in these variables. But in this example, we have not explicitly provided any initial values. In some languages, such as C, no default value is ever provided when you declare a variable, meaning you get undefined behavior if you use an uninitialized variable. This is such a common and significant problem that Java provides two solutions. An initial default value of 0 is given to instance variables, or an explicit error is given for using a local variable before initializing it. We will see these different types of variables in upcoming videos. Now let us look at another example, which initializes the variables when they are declared. Here, the first statement declares an int called x. Executing it makes a box for x and immediately assigns the value 4 to x. We show this by putting 4 in the box for x. Executing the next line both creates a box for y and puts the value 6 in that box. Combining the declaration and initialization of your variables into the same statement won't pose a problem in any language, and anyone reading your code knows exactly what you meant for the code to do. So this is a good habit to get into. Of course, variables are only useful if you make use of the value that they have. Here, the first code declares x and initializes it to 4. Next, y declares and initializes it to x plus 2. To perform this statement, we must evaluate the expression on the right-hand side of the equal sign. X is 4, so x plus 2 is 4 plus 2, or 6. We show this by creating a box for y and putting 6 into it. The last statement creates a variable z and initializes it to y minus x. So you would take the value of y, which is 6, and the value of x, which is 4, and subtracts them to get 2. You would then create a box for z and initialize it to 2. Great! Now you know how to execute code with variable declarations and assignment statements.
Now that you know a little bit more about expressions, let's see them in action. This code example starts with the declaration of an integer or int variable called x, which behaves exactly as you've already seen. Next, we initialize x to 4 plus 3 times 2. As you know from math, times has higher precedence than plus. So this expression evaluates to 4 plus 6, which is 10. So we put 10 in the box for x. Next, we declare another variable y of type int and initialize it to x minus 6, which is 10 minus 6, which is 4. So we create a box for y and put 4 in it. The last statement says x gets x times y. Sometimes novice programmers expect statements which look like this to behave like algebraic equations with an equal sign, where you might solve for x. However, that's not what happens. Instead, you follow the rules you've already learned. The right-hand side evaluates to 10 times 4, which is 40. And you put 40 in the box for x. Now, let's see another example. Before we work through this, take a moment to pause the video and see if you can figure out what values x, y, and z have at the end of this code fragment. Okay, let's step through it. First, we declare an initialized x. Next, we evaluate x times 3, which is 6, and initialize y to that value. Next, we compute y divided by 2, which is 3, and initialize z to that value. The last statement says x gets 2 plus z mod 2. Since the 2 plus z is in parentheses, we compute that first and get 5. Next, we compute 5 mod 2. Remember from your reading that 5 mod 2 means we divide 5 by 2, but take the remainder, not the quotient. So this expression evaluates to 1. So we update the value in x's box to be 1. Okay, great. Now you should be able to evaluate code involving a wide variety of mathematical expressions.
The next important idea to understand is function calls. Functions abstract a computation out, giving it a name and parameters. You then can use the function to perform that computation without rewriting it. You can also think about what the function does, and not how it does it. Technically speaking, Java doesn't have functions, it has methods, since all code in Java is inside of objects. However, before we learn the more complex behavior of objects and methods, we'll learn the basic principles of function calls. These concepts will then lay the foundation for understanding method calls. We have three functions here: my function, f, and g. Why are we starting at g? We'll assume for now that you chose to call g from the BlueJ interface. Later, you'll learn about the main method, which is where programs start when you run them outside of BlueJ. We start with a frame for g, and with the execution right at the start of that function. The first line declares a, so we create its box inside of the frame for g. Next, we're going to set a equal to the value of the function call myFunction of 37. To evaluate this expression, we need to create a frame of the function that we're calling. In this case, myFunction. This will hold the parameters and variables of my function. Next, we pass the parameters to my function. We create a box for each parameter with the names coming from the function declaration, x and y. We initialize these by copying in the values of the expressions that were passed, here 3 and 7. Next, we need to note where to return when we finish executing my function. This location in the code is named the call site, the place where the function was called. We'll note it with the marker 1 in the code and put the same marker in the corner of the frame. Finally, we move the execution arrow into my function and start executing code there. Here we declare and initialize z, evaluating the expression 2 times x minus y. The values for x and y come from the frame for my functions, 3 and 7 respectively. So z will be -1. Now we have reached a return statement. Return statements tell us to leave the current function, returning to the call site noted in the frame. They also tell us the value to return to the caller. The first thing we need to do is evaluate this expression to obtain the return value. Here the expression is z times x. So we evaluate -1 times 3 and we get -3. Next, find where we should return. This is the call site we noted in the frame. Then we copy the return value back to the call site. The function call evaluates to this return value. We move the execution arrow back to the call site and destroy the frame for the function we just returned from. Now we're back in G. The call to my function evaluated to -3. So this line behaves like a gets -3. We'll finish that assignment putting -3 in its box. Our next line again has a variable declaration and a function call. We make a box for b and go through the same process to call f. We make a frame for f and pass parameters. This time there's one parameter in whose value is a times a, which is 9. We note where to return and begin executing code inside of f. Our next statement is a return statement, but the expression involves a function call. So we have to evaluate that call before anything else. We start with a frame and pass parameters. X gets a value of n, which is 9, and y gets a value of n plus 1, which is 10. We note the call site, we'll use 2 this time, since we were already using 1 somewhere else, and move the execution arrow to the start of my function and start executing code there. We declare z and initialize it to 8. Now we are ready to return from my function. We evaluate z times x, which is 72. Then we find the call site noted in the frame and copy the return value there. Finally, we move our execution arrow back to the call site, destroying the frame for my function. Now we pick up where we left off in f using 72 for the value of the call to my function. We evaluate 3 plus 72 to get 75. Since we're evaluating the return statement, this is the return value of f. So we find the call site and copy the return value there. Then we return to that call site, destroying the frame for f. Now we can finish the initialization of b. b gets 75. Lastly, we reach the return statement for g, which is where we started. When we return from the function where we started, we are done!
Now, let's see how to execute code with conditional statements in it. Here, we have a function f, which has some if and if-else statements. We have another function g. We'll assume we've used BlueJ's interface to invoke the method or function g to start with. The first statement declares a variable a, so we'll make a box for a. Even though this statement initializes a, it's going to take us several steps to compute that value. So we're going to leave a's value as 0 until we compute the value of the method f applied to arguments 3 and 4. To evaluate this call to f, we make a frame, passing the values of the parameters. Note where to return, and then we move the execution arrow to the first line of f. The next line of code is an if statement, whose conditional expression is x less than y. We evaluate that expression and find 3 less than 4 is true. So we move the execution arrow into the then clause of this if statement and continue executing. The next statement is a call to system.out.println, which is how you print something in Java. We write x less than y in our output, and then we return y plus x. This follows the same rules you've already learned for return statements. We evaluate the expression to get the return value, which is 7, which is then what the function call evaluates to, and we return back to the caller, destroying the frame for f. Now we're ready to finish initializing a, since we know that the call to the method f evaluated to 7. So a is now 7. Now we're ready for the next line of code in G. We make a box for b, and we call f, passing in the arguments 7 and 5. Once again, we want to evaluate the condition x less than y. However, now x is 7 and y is 5, so x less than y is false. We find the closed curly brace for this if statement and see that the if statement has an else clause. So we move the execution arrow into the start of the else clause and continue executing from there. First, we see the system.out.println statement, and this prints the line x is greater than or equal to y. Then we reach another if statement. This if statement is nested inside of the else, but that doesn't affect the rules of how we evaluate it. We see that the conditional expression is false, since 7 is not greater than or equal to 8. There's no else clause, so we move the execution arrow immediately past the closed curly brace and continue execution. There are not any more statements inside the else clause, so we move the execution arrow outside of the else clause and keep going. Next, we have a return statement. So we evaluate the expression x minus 2 to find that the return value is 5. This then gets returned to the place we noted. So we destroy the frame for f and return back to G. We finish the assignment statement, and now we're ready for the return statement from G. We execute that, and we're done with the method G.
As you continue learning how Java works, it is important to talk for a bit about objects and classes. Before we delve into the specific semantics, let's talk for a minute about the high-level concepts. When you are writing a program, you often have data in the form of variables which store the values you are computing on, and code which manipulates that data according to the algorithm you have designed. Object-oriented programming is a paradigm of programming languages that groups data and the code that manipulates it together into logical units called objects. This language design aims to help programmers think about their program by grouping the code and data together into one logical unit. As you write larger and larger programs, this principle becomes more and more helpful. As you progress and learn more about Java, you will learn about a lot of important principles that go along with these ideas. For now, however, we are just going to start with the basics. Here, you can see an example of a class declaration. A class is a template that specifies how to make objects. Let's look at each piece of this declaration. The first line tells Java that we are declaring a class called point. As with variables, we have a lot of freedom in what we name classes that we create, but we should name them descriptively. Here, we are making a class which represents a two-dimensional point, so point is a good name for it. Next, we declare two fields, int x and int y. Field is the name for a variable that is inside of an object. They are also called instance variables, since they are variables that are in each instance of the objects created from the class. These look like variable declarations, except that the word private comes before them. Private means that only code inside of this class can directly manipulate these fields. You'll learn more about why that is important as you become more skilled in Java, but for now, we'll just make all fields private. Next is the declaration of a constructor for the class. A constructor specifies how to create objects of this class. It is code that gets run when an object is created to initialize that object. Note that the constructor looks like a function but has no return type, and is named the same as the class. These are the hallmarks of a constructor declaration. In front of the constructor, we have the word public, which means that any code can use this constructor to create a point. After the constructor, we have three methods: getX, getY, and distance. Methods are functions that are inside of classes. In Java, everything is inside of a class, so technically all functions in Java are methods. These methods are invoked or called on a particular object and implicitly act on that object. You can see a method call here where the code says otherPoint.getX. This calls the getX method on the otherPoint object. It will get the x of that particular point object. Last, we have the declaration of a static method. These behave a little differently from regular methods. They don't act on any particular instance of the class. They just belong to the class in general. That concept is a little tricky, and we'll explain it more later. This method is called main, which is a special method. If you run your programs outside of BlueJ, main is the starting point. Execution begins in main before any objects are even created. The ideas of objects are supposed to help programmers think about their data in terms of objects that make logical sense. For example, if we make a new point, we are creating an object which represents something we can concretely think about. In this case, a point on a plane. We can then make another point which has its own x and y and represents a different instance of the same type of thing, another point on the plane. You can of course create as many of an object as you need for your algorithm. Once you have some objects, you can invoke methods on them, such as p1.distance p3, which you can think of as asking p1 to compute the distance to p3. That is, you can think of this line of code as saying, p1, go figure out how far you are from p3. You can think of the code that executes for this method call as logically belonging to the p1 object. Now that you have the high-level concepts, let us delve into the step-by-step execution of our example point code. We're going to start in main, which we'll talk about more later. Args gives you access to the command line arguments, which you won't need for quite a while, so we are just going to ignore that. The first line declares point p1 and initializes it to a new point. Note that classes are types, so we can use class types that we make to declare variables. Here we want p1 to be a point. Until we finish evaluating the right-hand side, we're going to draw this as an arrow with a flat end. We'll use this notation to indicate when a variable does not reference an object. Note that this is a bit different from numeric variables like ints, whose initial value is 0. We've colored this flat-ended arrow red to remember that we have not yet explicitly initialized this variable. Now, let us evaluate the right-hand side of the initialization expression. We are doing new, which will create a new object. What type of object are we going to create? We look right after new and see that we are creating a new point. So we are going to draw a box for a point which has fields x and y. Note that the box we just drew is not in the frame, but is outside of it. It is in a different area called the heap. Anytime you use new, you create data in the heap. The important difference is that data in the heap does not go away when a function returns, destroying its frame. Note that we have put 0 in the fields of this new point and colored them red as we have not explicitly initialized them yet. Speaking of initialization, remember that we said that the whole point of a constructor is to initialize a newly created object. The next thing that happens is that we call the constructor to initialize this point. As with any call, we set up a frame and pass parameters. However, constructors and methods take an additional implicit parameter which tells them which object they are operating on. That parameter is called this, and its value is an arrow which points at the object that is being acted on. In this case, this points at the object that we are creating to tell the constructor which object to initialize. Now we enter the code for the constructor and begin executing statements there. The first line says x gets start x. There's no x in this frame, so where do we store the value of start x? Here, x refers to the field inside of this object, That is, we want to put startX's value into the x field of the object we are initializing. So to find the right box, we follow the arrow for this, and then look for the x field in this object, and store the value 3 into that box. On the next line, y again refers to the field inside of this object, so we update that field to be 4. Now we have finished the code inside the constructor and are ready to return to main at call site 1. Back in main, we need to finish this assignment statement. To do that, we need to store the value of the right-hand side into the box for P1. A new expression evaluates to an arrow pointing at the object that it created. So, we will make P1 to point at the newly made point. The next line does a similar thing. It declares P2 and initializes it to a new point. So once again, we create a box for P2. We haven't initialized it explicitly yet, so we have a default value of a flat-ended arrow, meaning it does not point at any object yet. We color it red to remember that it is a default value. We then create a new point with its x and y fields set to default values of 0, and we call the constructor to initialize this point. Notice how this points at the newly created point. With multiple points in our world, it is important that we can keep track of which point we are working on. We then initialize the x inside of this point to be 6. As before, we found the right box by following the arrow from this, and we initialize the y inside of this point to be 8. Now, we have finished the constructor and are again ready to return to main. In main, we finish the assignment statement setting P2 to point at the newly created object. We'll stop there and pick up with executing the method call in the next video. In the previous video, we executed the declaration and initialization of points P1 and P2, and you learned about new and constructors. Now, it is time for you to learn about method calls. Method calls work a lot like function calls, except that we have to pass the this parameter to let the method know which object it is working on. Let us resume where we left off. This line is going to call P1.distance P2 and then print its return value. We need to set up a frame for distance, which will take 2 parameters. The implicit this parameter, which tells it which object it is acting on, and the other point parameter, which is explicitly passed to it. The this parameter has the same value as the variable before the dot. In this case, we have P1.distance, so this has the same value as P1. It is an arrow pointing at the same point object. We have colored this arrow differently, but that does not have special meaning. It is just to help you keep straight which arrow is which in this diagram. For the other point parameter, we just copy the value that is passed in. In this case, P2. So the value of other point is an arrow pointing at the same point object as P2. Now, we go into the distance method and begin executing code there. Executing the first line, we are declaring a variable dx and need to initialize it to x minus other point.getX. To evaluate that expression, we need to call other point.getX. So we need to set up a frame for that method call. Again, this method takes an implicit this parameter to tell it which object to do getX on. Which object should this point at? Well, we did other point.getX, so we copy the value of other point, which is an arrow pointing at that point object. Now we go inside of getX and begin executing code there. Here we have return x, so we need to evaluate the expression x and return its value. How do we get the value of x? We follow the this pointer to find the object we are working on, and then look for the x field inside of that object. The value of that field is 6, so that is the value of the expression x here, which is what we'll return to the caller at call site 2. Returning to call site number 2, we want to evaluate x minus 6. How do we evaluate x here? We again look at the this pointer, which refers to this point object. And we get the x field inside of that point object. That value is 3, which is the value of x in this expression. So we will compute 3 minus 6 and initialize dx to minus 3. Now we are going to declare and initialize dy using a very similar process. First we make a box for dy, then we call getY on other point. Notice how this is a copy of the value of other point, an arrow pointing at our second point object. We get the value of the y field out of this object, which is 8, and return it to call site 2, where we return the execution arrow to. We evaluate y by looking in this object and finding its y field, which is 4. Now we are ready to finish the initialization of dy to 4 minus 8, which is negative 4. Our next line has a little bit of math. Let's look at it in detail. We are calling math.square root of dx squared plus dy squared. First, we can compute the value of the parameter, which is 9 plus 16, which is 25. So we need to evaluate math.square root of 25. This looks like a method call, but where did the math object come from? It turns out that math is a class, not an object, and is part of the Java library. This is a static method call. The method is being called on the class in general, not on any particular object. Here, the math class is just a handy place to put a bunch of mathematical functions together. Since we don't have the code for math.square root, we have to know what effect it has. If we did not know, we would look it up in the Java documentation. However, as you might have guessed, this method just computes the square root of its argument. So math.square root of 25 will return 5.0. Our distance function returns that value to its caller, so the value of the call to distance in main will be 5.0. We then return execution to main, where we are ready to complete the print statement, which will print out 5.0. Now we are done with main, so we will return from it, destroying its frame and exiting our program.
At this point, you have seen a variety of types such as int, point, and file resource. But what exactly is a type? A type specifies how data should be represented, interpreted, and operated on, as well as what operations you can do with it. One important rule of computing is that everything is a number. If you didn't learn about the everything is a number principle in whatever intro courses brought you here, we'll give you some links to videos about it. Specifically, this means that everything is stored in the computer's memory as bits, ones and zeros. But not all numbers mean the same thing. Some numbers might mean plain numbers, while others might mean letters, and others might mean the locations of data in the computer's memory. So the type of a value specifies how to interpret those numbers. It tells Java how to assign meaning to the ones and zeros stored in memory. The type also specifies what operations you can perform on the data. The type tells Java not only what you can do, but how it should be done. Let's talk about both of these points in more detail. We just said that the type tells Java how to interpret the ones and zeros in memory. Let's talk about that a little bit more. On the left, we have the conceptual representation of the program state that we have been working with. There's a box for a variable called x. On the right, we have a bunch of bits from the computer's memory. The blue ones correspond to x. But what do they mean for the value of x? Well, if x is an int, then these bits would mean it has a value of 1,234,567,890. We're not going into the details of how you can figure that out here, nor do you need to know it for beginning Java programming. But if you take a computer organization class, you will learn a lot more about how data is represented. The point we want to make here is that if x had a different type, like float, then the same bits would have different meaning. These same ones and zeros would mean 1,228,890.25. And if x were a string, then the bits would be the location in the computer's memory of the actual string object, which would have a sequence of characters. Those would also be stored with a bunch of bits that would be interpreted as letters, since their type would be char. We also said that the type tells us what operations we can do and how they're done. Consider this simple bit of code. X plus y. Is it legal? And if so, what does it do? To answer this, you need to know the types of both x and y. If x and y are both ints, then this code is legal and performs integer arithmetic. If x and y are both strings, then this code is also legal but performs string concatenation. It makes a string with the letters of x first, then the letters of y immediately after. Notice that even though the plus operation is legal for two different types, we may perform that operation differently for one type than for the other. If x and y are both points, then this code is not legal. While we're talking about types, you might be wondering what you do if you need to convert between types. The answer is that it depends. For some type conversions, they can happen implicitly. If you have an int and you need to convert it to a double precision floating point number, the compiler will just automatically insert the conversion for you without complaint. The general rule is that you can use implicit conversion whenever the compiler will consider it safe. Here we are turning 3 into 3.0, which is not a problem. Note that the compiler does not consider the values, only the types, when deciding if an implicit conversion is okay. For some type conversions, you can explicitly cast. This means that you tell the compiler that even though what you're doing is questionable, you are sure you want to do it. Here we are turning the double 3.14 into an int, which will discard the fractional part, leaving us with x equals 3. The compiler wants to be sure that we meant to do this, so we explicitly cast by writing int in parentheses. Other conversions require calling methods to calculate out the converted value. For example, if we have the string quote 3 quote and want to turn it into an integer, we can't just directly cast it because the conversion is actually somewhat complicated. Instead, we have to call a method like integer.parseInt, which will perform the conversion. The last thing we will mention about types is that there are two major categories of types in Java: primitives and objects. There are 8 primitive types: int, double, char, boolean, long, float, byte, short. We'll primarily use the first 4 of these. Variables of primitive types hold their value directly in their box. Primitive types don't have methods, so you can't do .method call on a primitive, and they can't be null, although each primitive type has an associated wrapper class, which gives you an object to hold that primitive. Everything else is an object type. Some are built into Java, like string. Others are part of libraries that you might use, like point or file resource. And yet others are classes you will create yourself. Whenever you make a class, the class you make is its own new type. Unlike primitives, the value of variables of object types is an arrow pointing at the object. This arrow is called a reference. You can invoke methods on the object with .method name, and the reference can be null, meaning it does not refer to any object. If you do equals equals on 2 objects, you're checking to see if the arrows point at exactly the same object. Okay, that's the basics of types. We know it's a lot to absorb at once, but you'll get better with these ideas as you practice more Java.
Hi. Now we're going to learn how a for each loop works. This piece of code looks similar to the hello around the world example that you started with earlier. To make this work, we need to add an import statement to the top to tell Java where to find the file resource class. File resource is in a package that we provide to you to let you manipulate data in files before you learn the more advanced techniques and concepts that would let you do this in Java directly without the classes we've created. Accordingly, this is found in the edu.duke package. If you want to run this code in BlueJ, you could do so by creating a hello world object and then invoking its runHello method. We could also add a main method, which does the same thing if we want to be able to run the code directly but outside of BlueJ in another environment. Let's start executing the code by hand. We start in main with a frame that contains args. We're not going to use this args argument, so we're not going to worry about its value. The first line declares HW and initializes it using new. You learned about new in a previous lesson, but there's a slight difference here. The Hello World class does not have a constructor. So what do? In this case, Java provides a default constructor, one with no arguments, that does nothing. So we execute this line as you're used to, but we don't call a constructor. We make an object. Class Hello World has no fields, so the object itself doesn't have any state or anything else we can see in it. Then we finish the assignment statement. Next, we call runHello, passing in HW as the implicit this argument. Inside of runHello, our first statement declares the variable f. The next statement initializes f to a new file resource object. This raises two questions. First, what does a file resource object look like? Meaning, what fields are there in the file resource object? It turns out we don't actually need to know this precisely. The details of how a file resource object works can remain hidden from us as long as we know what it does. This is an instance of the important programming principle known as abstraction. Second, what does the constructor for a file resource object do? To find the answer to this question, we would consult the documentation for file resource. Consulting documentation for libraries, sometimes called APIs, that you use in programming is an important task. Since file resource comes from the Duke Learn to Program libraries, we would look at the documentation website and we would read about the constructors for a file resource class. There are 3 constructors, and the one we want is the one in the middle, since we're passing a string literal in, the string, quote, file.txt, quote. This documentation says the constructor will find that file with that name on our computer. Given this information, we're just going to represent the file resource object as knowing what file we asked for, the file whose name is, quote, file.txt, end quote. We don't know precisely what fields are stored in this object, but that's okay. We'll represent it as precisely as we can because we know what the object does. We finished the assignment statement, so now f references this file resource object we just created by calling the constructor. The next line is new to us. It's a for loop. In particular, this for loop is often called a for each loop because it does something for each value in an iterable. What's an iterable? The short and simple answer is that it's an object which gives you a sequence of values. Let's dig a little more closely into the details of this loop. The first part declares a variable. The type is string and the name of the variable is line. This declaration will behave like any other. We'll create a box for line. Next is a colon. This is the syntax of a for each loop. We don't use an equal or assignment operator since we aren't assigning one value to line. Instead, we're going to use each value in the iterable sequence. Many people read the colon as in when they read the code out loud or to themselves. For string line in f.lines. Next, we have an expression which evaluates to the iterable whose values we want variable line to refer to, one after the other. In this case, that expression is a call to f.lines. To understand what this does, we'll need to understand what f.line returns. So we'll again need to consult our documentation. From this API documentation, we see that f.lines gives us an iterable, whose values are each line in the file in the order that they appear. This means that we'll need to look at the file whose name is file.txt to see what its contents are in order to understand and simulate the code behavior. On my computer, I've made file.txt and put these 2 lines in it, hello on one line and world on the next line. It isn't a very exciting file, but we want this example to be relatively short. Returning to our code, we now create this sequence of strings, hello and world. We'll create the box for line, and we'll make it refer to the first element of this iterable sequence. Now, we go into the body of the for loop and begin executing statements there. The next line is a print statement, so we print out the value of line, which is hello. Now our execution arrow is just before the close curly brace of the for each loop. We've reached its end. When you reach the end of a for loop, you move the execution arrow back to the start of the loop to do the next iteration, the next time through the loop, with a new value for the loop variable. In this case, our loop variable is the string line, so we need to update it to have the next value in the iterable. we update line's arrow to point at the next value in this sequence, and again go into the body of the loop. We encounter our print statement, but this time line has a different value, so we print world. Now we've once again reached the end of the body of the for loop, so we go back to the beginning, the start of the loop. We need to update line to refer to the next value in the iterable sequence. However, if we try to do that, we'll find that there are no more elements in the iterable sequence. We already used the last one, so instead we exit the loop. We move the execution arrow past the body of this for each loop and begin executing code there. When we do this, the loop variable, in this case the string line, goes out of scope. That means it no longer exists, so we remove its box. Now we're ready to return from the method runHello, destroying its frame. Since the call to that method runHello was the last line in main, we also return from main, exiting the program.
Today, you're going to learn how to solve programming problems using the 7-step approach that we will use throughout the rest of this course. When you're solving a problem, you're going to start with a problem statement. You know that you want to end up with working code, but going straight from a problem statement to working code is a rather large leap. It can take some significant thought and work. This is why we break it down into 7 steps for you, giving you a manageable approach where you know what to do next to solve the problem. This is the 7-step process that we recommend you use whenever you are solving programming problems that are difficult. As your programming skills improve, many problems will become easy enough to just do them in your head. However, there will always be some problems that are harder, and having a step-by-step approach will be helpful to you. Let us look at each step in a bit more detail. The first step is to work an example of the problem yourself, by hand. This should be a small instance of the problem, something with about 4 or 5 pieces of data to manipulate. You don't want to try to process 1,000,000 pieces of data yourself. That would take forever. If you have trouble doing the problem yourself, you cannot write a program to do it. So what should you do if you get stuck here? Well, one of 2 things could be wrong. Maybe the problem is just unclear. The problem statement does not give you enough information about what you're supposed to do. In a classroom setting, you could consult your teacher or TA. In a professional setting, you might work with your technical lead or customer to clarify the requirements, or you might just need to refine the problem statement yourself. The other potential problem is that you lack domain knowledge, the knowledge of the field that the problem belongs to. If you're trying to write a program to compute physical motion, and you do not know the physics equations that you need, that would be a lack of domain knowledge. When you have this sort of problem, you need to find the relevant domain knowledge before you proceed. In step 2, you want to write down what you just did to solve this problem. You want to be as exact as possible. Do not leave anything out, and write down how you solved it in a step-by-step fashion. At this point in the process, you are just writing down the step-by-step approach for the one particular instance you solved, not the more general problem. The tricky part in this step is that we often do things without thinking about them. If you gloss over something or you're not precise about what you did, it will make the later steps harder. In step 3, you want to move from the particular instance that you solved in step 1 to an algorithm that works for any instance of the problem. That is, you want to devise an algorithm which can solve the problem correctly for any input that you give it. You'll do this by finding patterns in what you did and replacing specific behavior with more general behavior based on that pattern. Some important tools for finding patterns, which we will delve into more deeply soon, are looking for repetitive behavior, finding behavior which you do sometimes but not always, and figuring out under what conditions you do it, and figuring out how specific values you use relate to the parameters you picked. So what should you do if you have trouble with this step? Go back and try steps 1 and 2 again. Use different inputs, which will give you another example to work from. You can see the steps for a different instance of the problem and have more information to help you find the patterns. In step 4, you want to check your algorithm. before you proceed to turn it into code. If you found the patterns incorrectly or otherwise made a mistake in step 3, you would like to find that out now. The way you check your algorithm is to pick at least one different input. Again, it should be a small one. And follow the steps of your algorithm for it. If your algorithm gives you the right answer, then you are ready to move on. If not, you should go back and fix it first. Now that you have devised an algorithm to solve the problem, you're ready to translate that algorithm into code. This step is where the syntax of a specific programming language comes into play. You need to write down your steps in the syntax of that language. Once you've written your code, you want to be sure that it works correctly. So you run test cases on it. Running a test case involves executing the code on a particular input and checking if it produced the right answer. The more test cases your code passes, the more confident you can be that it is correct. However, no amount of testing can guarantee that the code is right. When your program fails a test case, you know something is wrong. And when that happens, it's time to debug your program. You can watch a review video about debugging if you need more information, but at a high level, you will apply the scientific method to understand what is wrong with your program and determine how to fix it. Once you have identified the problem using the scientific method, you will need to revisit a previous step to fix it. If the problem is in the algorithm you designed, you will want to go back to step 3 and rethink your algorithm. If your algorithm is correct, but you implemented it incorrectly in code, you will want to return to step 5 to fix your code. Now you have learned the 7-step approach to solving a programming problem. In the next video, we will work through an example of the process. This process can guide you through programming problems you need to solve not only throughout the rest of this course, but whenever you need to solve a difficult problem. Thank you.
Hi. In this video, we're going to walk through an example of using our 7-step process to solve a programming problem. In particular, the problem we're going to work on is, given a shape, find its perimeter. Step 1 is to work an instance of the problem yourself. That means you'll need to draw a shape and find its perimeter. We'll need a little domain knowledge here for this problem. Specifically, what is the perimeter of a shape? If you don't recall, the perimeter is the sum of the lengths of all the sides of the shape. We'll need to know that a shape is defined by its points, and the points are listed in order as they appear around the perimeter. First, we'll draw a coordinate grid so we can draw our shape precisely and carefully. Then, we'll draw a shape on that grid. We're noting the coordinates of each point in the shape as we draw it. This will allow us to easily do math on them to compute the lengths of the edges of our shape. Once we have the shape, we can start finding its perimeter. This left edge has length 4, and this bottom edge has length 5. So we can add them together and get 9, the running total of our perimeter. The next edge is the diagonal, so we'll need to do a little bit of math. The difference in the x's is 3, and the difference in the y's is 4. The square root of 3 squared plus 4 squared, 9 plus 16 or 25, is 5. That's the length of this edge. We can then add 9 plus 5 so that our running total is 14. Now we see that the last edge has length 2. We add 2 to 14 to get 16. So 16 is our answer for this particular instance of the perimeter problem. Now you're ready for step 2, writing down specifically what we just did. First, we found the distance from the first point to the second point, which was 4. Then we took the second point to the third point, which was 5. Then we added 4 plus 5 to get our running total of 9. Next, we found the distance from the third point to the fourth point, which was 5, and added 9 plus 5, so our running total is 14. Then we found the distance from the fourth point back to the first point, which is 2, and we added 14 plus 2 to get 16. Last, we said that 16 was our answer. So we can write down the steps to solve this particular instance of the problem, as you can see here. Now we're ready to move on to step 3, where we're going to find the patterns and generalize to find the perimeter of any shape, not just the one we just saw. One thing you might notice is that we're doing almost the same thing repeatedly. When we generalize, we want to look for similar steps and express them as repetition. To do this, we'll need to make them match up exactly, which we might do here by starting out by adding 0 plus 4 to get 4. Why does this seem like a good way to make these match up? We'll keep adding the previous result to our running total of all the lengths, so it makes sense to start with 0 for our running total and add our current result to it. The next thing we might do in generalizing this algorithm is give this quantity a name. It won't always have these values, so we should name the quantity and refer to it by that name. We'll call it curdist, since it's the current distance. When we name this quantity curdist, we'll also want to change all the places we use that value when we computed it to reflect the name that we just chose. This gives us an algorithm that looks like this. Next, we should give this quantity a name. Here, total perimeter makes sense, or total perim, as this quantity is the total perimeter of the shape that we're calculating as we go through the steps. Again, when we name the quantity, we'll need to replace the places we use that value using the name we just gave it, total perim. This gives us an algorithm that looks like this. Let's stop and look at this algorithm for a second. Does anything strike you as maybe just a little bit odd? What about this place that we used 0? It isn't a previous value that we computed, but why did we put this line in to begin with? We wanted all the steps to repeat exactly, but now they look different. Can we make them look the same? Sure. We can make total perim start at 0 before we begin the repetitive steps. Then we can just update total perim in our first step. Now these steps form a repetitive pattern. They're the same except for which particular points they're working with. The first point in each of the repetition counts through the points of the shape in the order in which they appear. That's great. We like it when we can iterate over a sequence because we can ultimately express this in code with a for each loop. But this second point in each repetition is a bit more problematic. We'd have to have a way to get to the point after the current one. Now there are ways that we could set up our shapes interface or API to iterate over the points and ask for the next one too. But let's do something very clever. Let's reorder the steps so that we do the distance from the fourth point to the first point first. That is, let us write the steps in this order. First, is it okay to do this? When we want to reorder things, we have to think about it and be very careful. Here, the reordering is totally fine. It's totally fine since addition is commutative. It doesn't matter what order we do the addition in. Second, why is it useful? Well, now we're going through the points in order, giving us a natural for each repetition. But the other point, which does not lend itself to the for each repetition, is the one we just used. That means we can simply remember the previous point in a variable and use it with the next point. We express this idea by updating our algorithm to look like this. Notice how we update prev point to be the point we just finished with, before moving on to the next point. Then we make use of that point in the next set of steps. But what about this point? We can use the same idea we saw earlier when we initialized total perim to 0. Start prev point out with the value we want before we begin repeating the steps. But will it always be the fourth point? No. It just happens that we had 4 points here, but in general, we'll want to start prev point as the last point in our shape. Okay, great. Now we have nice repetitive steps where the only difference is the point we're working on, and those go in order through the points in the shape. So we can express all these steps in the colored boxes that you see here as a repetition for each point of the steps. This gives us a nice general algorithm for finding the perimeter of any shape. Later, we'll translate this into code. Hi, we've developed an algorithm to find the perimeter of any shape. But are we ready to turn this algorithm into code? Well, we could, but we'd like to be confident that it's right before we do that. After all, there were a lot we had to do to generalize our steps, and it's entirely possible that we made a mistake. Or perhaps we just didn't think through all the special cases. So before we turn this into code, we should test it out. To test the algorithm, we need a different instance of the problem, something other than what we used to make the algorithm. In fact, it's good if our test instance is pretty different from the one we used to make the algorithm. Here, we've shown a triangle instead of the four-sided trapezoid we used when we developed the algorithm. Before we go any further, take a second to figure out what the right answer is. What is the perimeter of this shape? When we finish, you'll want to check if the answer to our simulated algorithm is correct. And to do that, you'll need to know the right answer. Now, we'll execute the algorithm by hand for this particular input. As we test the algorithm, notice the similarities between the code and English. We're going to execute this English algorithm by hand, just as we executed code by hand. They both work pretty much the same way, and that's not a coincidence. When you turn this algorithm into code, you want to write down code that has the same semantics as the English, the same meaning. The code should transform the program state in the same way that the English transforms this diagram. So we'll start with total parim and set it to 0, and prev point being the last point in the shape. But what is the last point? We'll say the points in this shape start at the top and go counterclockwise. So this point in the lower right-hand corner is the last one. And we'll initialize prev point to be that point. We'll note briefly that if this were actual Java objects, prev point might be an arrow pointing at an object. But we're going to just write down the coordinates here to keep the diagram simple and legible. Next, we're going to do the steps for each point. So we need to start at the first point, which is this one at the top of the diagram. And that will be the initial value of cur point as we enter the for each repetition. Then we'll find the distance between these 2 points, which is 10. And we'll update total parim to be 10, 0 plus 10. And then we'll update prev point to be cur point. Now we're at the end of our for each repetition. So we'll update cur point to be the next point in the shape, which is -3, -4. When we update cur point, we go back to repeat these steps. We repeat the steps again, finding the distance between those 2 points, which is 8. And then we update total perimeter to be 10 plus 8, or 18. And then we update prev point to be the current point. Then we go back to the top of our loop, updating cur point. We repeat these steps for the last point in our shape, after which we've gone through all the points. So we skip to the steps after our repetition. Here, we can say that total parim is our answer. Total parim is 24. Is that the answer you came up with earlier? Yes, that is the perimeter of this shape. The fact that our algorithm came up with the right answer here gives us more confidence that we generalized correctly. We're done executing the algorithm by hand, and we have some great confidence that it's correct. So we're ready to turn the algorithm into code.
All right, now you've developed the algorithm to find the perimeter of a shape, and we want to turn it into Java code. You've seen a lot of Java code as we've talked about the syntax and semantics, and so what we're going to do is step by step go through and take the algorithm that we wrote and turn it into code that has semantics that match what we wanted our algorithm to do. So here I have a class called perimeter runner. It's going to have the method getPerimeter, which takes a shape and returns a double. It's got some other code in here, so it has a main that we can run, which will make an instance of this class and call testPerimeter, which will use file resource to read from a file and create a shape, and call the parameter and then print that out. We're going to go through and translate this to code, and I've written our algorithm here as comments, which are things for people that the compiler will ignore. So the first thing we say is start with total param equals 0. So this sounds like we need a variable. We called it total param. We're going to set it equal to 0. We need to think about what type we want. Since we set it equals 0, we might want an int. But if we think a little more carefully, we might realize we want a double since we're working with floating point numbers that might have fractions. So double total param equals 0. And if we'd written this as int, we hopefully would find that out in testing when we come up with answers that should have fractions and we don't have them. Then we say start with previous point equals the last point. So we need another variable previous point. What type of variable is this? Well, this is going to be a point. And it's going to be the last point. We meant in S, even though we didn't write that down. So we'll call get last point. How do I know that was there? I looked at the documentation for shape before I started doing this video and saw that it has a get last point method. Then we say for each point, which we wanted to call cur point in the shape. So this sounds like a for each loop. Each point, cur point in the shape dot get points, which is going to give us all of the points. We want to do these steps, and I'm going to go ahead and put them in curly braces. We want to find the distance from previous point to the current point and name it cur distance. So anytime we want to name a quantity, we want a variable. And so that's going to be the distance from prev point to cur point. Then we're going to update total param to be total param plus current distance. And then we're going to update previous point to be current point. Last, we said total param is my answer. Whenever we know our answer, we're going to return that because that's how we give our answer back to whoever called us. So now that I've written this code, I'm going to come up here and I'm going to click compile. And it says cannot find a symbol variable shape. It's because my shape was called S. And now it says class compiled with no syntax errors. So now I'm going to shrink this window down a little bit smaller. I'm going to come over here and I'm going to do main. Even though that's how we run programs outside of BlueJ, if we've written a main, we can do that. We're going to give it no arguments, so I'm just going to click OK. And it's going to ask me what input file has the points for this shape. So each of these files has some points. So for example, example 1 has -1, 3, -1, -1, 4, -1, 1, 3, which is what we used when we developed our algorithm. So that's a good first check. Make sure we get the answer we expected. And that gives us 16, which you may recall is what we came up with when we worked this example ourselves. Of course, using that might be bad because if we made a mistake, we wouldn't necessarily catch it since we've already used those values in developing this, so we might want another one. And so this says that this other shape with points of -3, 4, -3, -4, and 3, -4 has a parameter of 24. If you work that out yourself, you'll find that that's the right answer. And so we become more and more confident that this code that we just wrote is correct. So that's how you turn your algorithm into code. You go through step by step, take each step, write down the code that corresponds to what you wrote.
Hi, I'm Dr. Raluca Gordon. I'm a professor in the Duke Center for Genomic and Computational Biology and in the Department of Biostatistics and Bioinformatics. My work is strongly based on designing and using computational algorithms, programs, and tools, and I want to tell you just a little bit about that. But first, I'd like you to think about the word strings. What does an orchestra conductor think about when she hears the word strings? What does a sailor think about the word strings? What does a pianist think about the word strings? Well, I'm a genome scientist, so I will tell you what I think when I hear the word strings, and that is genomic strings. The genome of an organism stores all the genetic information necessary to build and maintain that organism. This genetic information is stored as a long list, or string, over the 4-letter alphabet A, T, C, and G. These 4 characters correspond to the 4 DNA bases: adenine, thymine, cytosine, and guanine. The sheer size of the genome makes it difficult, if not impossible, to analyze by hand. The human genome, for example, contains 3 billion characters. That is 1,000,000 times more than the characters shown here. Thus, finding any information in the genome requires computational approaches. In addition, the genome is complex and contains different types of information. Computational approaches are needed to find information, including genes, as you can see here. Finding genes requires more than simply looking for the tags or codons that identify the start and end of a gene. In addition to genes, such as the one shown here in red, we also need to look for regulatory elements, as shown here. We do this with computational tools and techniques. These regulatory elements are shown here as simple letters representing nucleotides. But it's important to remember that these are actually bound by proteins called transcription factors, which help turn genes on and off. My research is focused on identifying such regulatory elements in the human genome using various computational approaches. You will do similar things in this course, and this will prepare you to become a computer scientist or a genome scientist, depending on what your preferences are.
Hi, and welcome to this lesson on finding information and patterns in data, which is a very general topic that we will make concrete in working with Java strings. Strings are sequences of letters, digits, punctuation, any character that you might type, for example. Why will you learn about strings? You've learned previously that everything is a number. That's true, as you can see here, where I've captured the beginning of 3 different files. These files might be stored in memory, on a flash drive, or on your computer's hard drive. The first file was a video, a file with a .mp4 suffix. The second file was an image, a file with a .png suffix. And the third file was a plain text file with a .txt suffix. Can you tell which group of bits of zeros and ones goes with which file by simply looking at the zeros and ones? Some people may be able to do that, but most cannot. Although everything stored on a computer is a number, information stored on a computer is often readable. We use strings to store data so that we can read it and so that we can write programs to read the data and process it. Here are parts of 3 data files where the data are stored as strings. It's important that the data is readable by you, not just by the computer, although we could write programs even if everything was only a number. It will be easier to write programs to find patterns, knowledge, and information in data when the data is stored as strings. The first part of a file is genomic data stored in what's called FASTA format. You'll write programs in this lesson to find proteins and genes in genomic data. The second part of a file is from a web page. You'll write programs to find links and other information in a web page, doing at a small scale what search engines like Google do in ranking pages to be found by those doing web searches. The third part of a file is data from a CSV file, or Crime in Sacramento, California in 2008. A CSV file is a file in a special format. The CSV means comma separated values. You'll write code in a later lesson to process CSV files. We have several goals for you to learn as part of this lesson. You'll learn about the Java string class. You'll learn many details, how to write programs with the string class and how that's most often done. You'll learn common string functions and how to read documentation to find out more about strings. You'll learn about Java types and operators. Here you'll learn more about Java's numeric types and operators on those types, which for you will be int or integer and double or a floating point number. You'll learn about programming to find patterns in data by searching for specific parts of a string. You'll repeat searches to find information and patterns like all the links on a web page or all the genes in a strand of DNA. Let's get started solving problems. Thank you. Hello and welcome back. You are going to be working with strings that represent DNA, solving problems like searching for genes in them. This problem is a great one to learn on because even though we're going to start with a greatly simplified version of it, it's an important problem with real-world applications. Of course, the lessons you will learn about working with strings and programming in general will help you far beyond this problem domain. Whatever sorts of problems you want to solve, strings are likely to come up in them in one way or another. HTML, email, or really anything that is text that is represented as a string. You are also going to learn some other important lessons as you work on these problems, like how to do math in Java. Of course, math is also ubiquitous in programming since everything is a number. And perhaps most importantly, you will get more practice developing and implementing algorithms with the 7 steps. Before we dive into DNA-related problems, we need to give you a bit of domain knowledge, some terms and concepts related to working with DNA. Here is a string that could represent some piece of DNA. You will see that it's made up of 4 letters, A, T, C, and G. Each of these represents one nucleotide, which are the basic building blocks of DNA. 3 nucleotides together make a codon, which each describe one amino acid. The ATG codon shown here is special in that it indicates the start of a gene. Accordingly, it's called the start codon. And the TAA codon is also special in that it indicates the end of a gene, so it's called the stop codon. There are a couple other stop codons, but for now, we're only going to think about TAA. Everything between and including these 2 codons makes up one gene. The first problem you're going to work on is finding a gene in a string which represents DNA. That is, you want to write a program which takes a string like this one and gives you all the text between it and including the start codon ATG and the stop codon TAA. You're going to start with a greatly simplified version of this problem, just finding those letters and all the text between them. You will not worry about the fact that real genes must be multiples of 3 in length because they're made up of codons, or that there are some other stop codons, or a few other complexities to start with. As you master more string and algorithm concepts, you'll add features to your program, making it more realistic with each step. As always, the first thing you want to do is work on an instance of the problem yourself. Let's take this DNA sequence and find the first gene in it. Let's find the start codon. Aha, there it is. Now let's start looking after it to find the stop codon. And we find it right here. That means that we want to take all this text representing the nucleotides in this region as our answer, the gene that we found. Now that we have worked an example, we should write down what we just did. First, I found the first occurrence of ATG. Then I started looking after the ATG for TAA. Last, I took all the letters between and including them as my answer, ATG, ATT, TTC, etc., all the way to TAA. Okay, now that we wrote down what we did for that specific problem, we want to generalize it. Why did we look for ATG? We always want to look for it. That's the start codon. What about TAA after ATG? We always want to do that too. That is the stop codon. And taking all the letters between and including them, we always want to do that too. The only thing that isn't really general here is the specific string we wrote down as our answer, which was more of a descriptive note to ourselves than anything else. Now that we have a general algorithm, we'd like to turn it into code, but we need to learn some new Java concepts first. How do we find ATG in a string? For that matter, how do we even represent or talk about the position of something in a string? And how would we get all the letters in a particular range in a string? You'll learn about these concepts, then you'll be ready to turn this algorithm into code. Thank you.
To move forward implementing a gene-finding program, we will explore a couple of important string topics in this video. The first of them is how we can represent the position of something in a string. To answer this question, we return to the recurring concept that everything is a number. That is, we will give each position in the string a numeric index. Notice that these numbers start at 0 in the first position, not 1. This may seem a bit odd, since we usually start counting from 1, not 0. However, many programming languages start numbering sequences of things, such as strings, from 0 because it makes some tasks easier, as we shall see later. These numbers, which describe the positions in the string, are called indices or indexes. Either word is an okay plural of index. For example, if I wanted to talk about this E, I might say the letter at index 3 is E. We have now answered the first question. We can represent the position with a number, and we can talk about the index in the string where we find the ATG. Now it is time to answer the second question. How could we get all the letters in a particular range? Which we could now be a bit more precise and say between two particular indices. One option would be for you to write your own algorithm to do this. However, you can also use a built-in method of the string class. Whenever there is a built-in method to accomplish a particular task, it is better to use it than write your own. Not only does it save you work, but the built-in method has already been heavily tested by expert programmers, so you can be very confident that it works correctly. For this particular task, you want to use the built-in substring method. However, before we show you how to do that, let's take this example string and make it an actual Java string, assigned to a variable. Here we have a variable declared with the name s, of type string, and an equal sign to make an assignment statement, and a semicolon at the end of the line to end the statement. However, this isn't quite correct yet. We also need to put the string literal in quotation marks, as shown here. If we did not put these and just wrote the word, Java would think Duke programming was the name of a variable and give us an error that is undefined. By putting the text in quotation marks, Java knows that we want a string with that literal text. So now we have a valid statement which makes the variable s be the string Duke programming. Next, you can see an example of using the substring method. Here we declare another variable of type string called x and assign it to the result of s.substring 4, 7. What do these numbers mean, and what does this method call do? The first number specifies the index in s from which we want to start making our substring. The letter at this index will be included in the resulting string. The second number specifies the index in s where we want to stop making our substring. The letter in this index will be excluded from the resulting string. The method will stop right before it gets to that letter. This may seem odd. Why would you want to specify the index after where you want to stop? There are a variety of reasons why this method and many others are designed this way. But one nice reason is that the length of the resulting string will be the difference between the two numbers. 7 minus 4 is 3. So we will get a 3-letter string as our answer. In particular, you will end up with this 3-letter string made up of the letters from the indices 4, 5, and 6 of s. So x will be the string PRO. While you are learning about this built-in method of string, let's take a moment to talk about a few other useful methods and what they do. You just saw substring and learned how it gives you the letters in a particular range of indices. Another useful method is .length, which tells you how many characters are in the string. The string s has length 15. Notice that for a string of length 15, the valid indices are 0 through 14. If you try to access an index outside of this range, your program will have an error with a string out of bounds exception. Another really useful method is .indexOf. You pass this method another string and it tries to find the first occurrence of that string within the string you called the method on. For example, here we have asked the indexOf method to find the string program within the string s. You can see that the first occurrence of program is right here since it starts at index 4. That is the value that the method call would return. Here's another call to indexOf, s.indexOfg. Can you figure out what this would return? This will result in 7, since the first occurrence of the string g starts at index 7. If you call .indexOf on a string that is not found, such as .indexOf f, it returns -1. You can also give .indexOf a second parameter, specifying the index to start searching from. Here we have passed 8 as the second parameter, so the .indexOf method will ignore characters in the indices 0 to 7 as it searches for g. It will then find this g, which is the first one when you start looking from index 8. So this method call evaluates to 14. Another useful method is .startsWith, which tells you if a string starts with another string. Here you can see that s starts with Duke, so this method call evaluates to true. Likewise, .endsWith checks to see if a string ends with another string. S does not end with king, so this method call evaluates to false. Wow, that was a lot of methods and a bunch of information. How would you know all of this without us telling you about every method in the string class? And should you be memorizing all of these details? Of course not. Programming is not about memorization. Although, as you program a lot, methods that you use commonly will naturally become familiar. Instead, you should learn how to make use of the language documentation, which describes all of the built-in classes and their methods. If you search the internet for Java string, your first result will probably be something from docs.oracle.com. Oracle is the company that makes Java, and docs.oracle.com is the website where they host the language documentation. If you click on this link, you will end up with a page that tells you all about the string class. If you scroll down a bit, you will find a rather long list of all the built-in methods in string. Here are a few of them, including a few that you have just learned about, .indexOf and .length. These entries give a brief description of the methods, and if you click on one of the method names, you will get a more detailed description of what that method does. There is also a documentation page on the course site at DukeLearnToProgram.com. That page has simplified documentation of some important methods for quick reference. Great! Now you not only know about indices in strings and some useful built-in methods, but also how to learn about other methods when you need them.
Hi, we're going to find a gene in a DNA strand. We're going to do a very simple algorithm in order to find our gene. So I've started some code here. We have an algorithm method called findGeneSimple, and we haven't done much with it yet, but what I've also done down here is I've written a couple of DNA strands that we will use to test the code that we write. So you can see here we have string DNA. We're going to print our DNA strand. We're going to call findGeneSimple and then print out our gene. And then I just have done this with 4 different strands of DNA. So let's write the code now. So I've started by just saying the resulting gene is just going to be called a variable called result, and I've set it to null, the null string. And if you remember from the video, we are going to look for the start codon in the strand of DNA. And the start codon is ATG, the string ATG. So we can use the new string functions that we learned about. So I'm going to start by creating a variable that will hold the index position of the start codon. So we'll call it start index. And then we are going to look in the strand of DNA, and we'll use the index of function to look for ATG. And the index of function is going to go through the string, and it's going to stop when it finds ATG, and it's going to return the index location of where it starts. So that'll be the starting position of our gene. We also have to look for the stop codon, and that is TAA. So we're going to create a variable for that called stop index for the position of where the stop codon is. Again, we will look in our DNA strand, DNA, and we'll use index of. But if you just look for TAA, it will start at the beginning of the string. And we want to look for the stop codon after the start codon. So we know where the start codon is. It's in the variable start index. And we want to start looking past that. So you can add a second parameter to the index of function. And so we will add that and say start looking where ATG is, which is start index, plus 3, which is the length of ATG. So now we have the start index and the stop index of where start index of ATG and the stop index of TAA, and now we want the strand that includes those two and everything in between it. So I'm going to call that our result. Again, we'll use a string function. So we'll use the string function called substring. And the way substring works is you have to say, I want a piece of a string and I want to start. Where do we want to start? We want to start where ATG is. So we'll start at the start index. And then the rest of our gene is going to be everything past ATG up until TAA, which is at the stop index. But we also want to include TAA, so we'll add 3. So that means take our substring from where ATG starts, go all the way to the stop index plus 3, which is the first character after TAA. And the way substring works is it says start at the first start index and then go all the way up to, but not including the second parameter. And then let's compile this and see if it works. Okay, so it compiles fine. So let's go over here and we'll create a new find gene. And now we'll run our test method that we wrote. And there it is. So we can see here's the first DNA strand, and you look for ATG, there it is. And then look for TAA, and there's the first TAA that's after it. And you can see there's the gene that we found right here. And then the next example, here's ATG. We look for TAA all the way here, and you can see here that's the gene we found. Here's the third example, ATG all the way to TAA, and you can see we got a big gene there. And then here's the last example, ATG, TAA. So that works good too. All right, but what happens if ATG is not there? Or what happens if TAA is not there? So let's look at our example here, and let's change one of our strings. Let's change this string. We'll just save this one. And let's change it to a string that does not have ATG in it. Let's see what happens if we run that example. So we're going to come back over here. And we'll run our test find, and we got an error down here. You can see it says string index out of bounds exception, -1. String index out of range. what happened? Let's go look at our code. So we looked for ATG and we didn't find it. And what the index of function does, if it doesn't find the string you're looking for, it returns -1. So start index has the value -1. And then we're trying to build a string starting at -1, and -1 doesn't exist. So we got an error. So what are we going to do? We need to fix this code. So let's check right after we ask for ATG. Let's put an if statement in there to check to make sure that ATG was there. So we can ask if start index is equal to -1. That means there is no ATG. In that case, we need to, there is no gene. There is no gene if there's no ATG, there's no start. So what we'll do is we'll just return the empty string. So if we compile this now, and if we run it, get rid of this. So we'll create find gene, and then we'll run test find, and it ran, but there's no gene here. And that's because there's no ATG. Let's try another example. We'll change our code again to give another example. Let's just change this one here. Let's create a string where we have ATG, but we don't have TAA. So we have the start codon, but not the stop codon. So I'll create a string CGATG, GTTTAAA, AGT. So there's no, oh, there is, let's get rid of it. There we go. So now we have ATG right here, and to the right of it there is no TAA. So let's compile, and we'll run it. And you can see there it's not there. There's no gene for this second one because ATG, but there's no TAA. All right, so just like we put a check for if there's no ATG, we should do the same for if there's no stop codon, so no TAA. So let's add that code too. We would add it right after we get the value for stop codon. So right here we can check and see if stop, if the stop index equals -1, at that point we know there's no stop codon, and so there's no gene. And so we can again just return the empty string. Return empty string. So that's just a safe way. If there's no start codon or no stop codon, let's add a comment here. This is the case for no TAA. We'll compile our code, and we'll just double check and make sure that works. So it compiles, and we'll run it. And now we have our first string is good, we find a gene. Our second string, there is no gene, we have an ATG, but we don't have a TAA. This string looks good. This string has no ATG, and it actually does have a TAA, but that doesn't matter because it has no ATG. And so this gene, there is no gene for that one either. So anyway, that is the way to find a simple gene in a strand of DNA. We look for the start codon, and then if there's a start codon, we look past it for a stop codon. And if we find both of those, then we can return the start codon, the stop codon, and everything in between it as the gene. Thank you. All right, now you have an implementation of the rather oversimplified version of this program. It just looks for ATG and then TAA and gives back everything in between. But real genes have to be a multiple of 3 in length, since they're made of codons, each of which is 3 nucleotides long. For example, this string is a valid gene. You can see here how it can be divided into codons starting with ATG and ending with TAA. However, this string is not valid. Even though it has ATG and it has TAA, when we look between them, we don't find a valid sequence of codons. Now, let's make our algorithm a little bit more realistic. You will fix this aspect of your algorithm. It will still be a simplification, but a bit more realistic. At this point, it's really good to note that starting with the simple version and adding features is not only a useful technique for you as you learn new concepts, it lets us introduce a few concepts at a time, but also important when writing real, large, complex problems. Okay, so you just saw 2 examples of DNA strings. One that has a valid gene and one that does not. But how can you tell in general what is the change you need to make to your algorithm? It might be useful to show the indices, as we have shown here, and highlight the location of the start and stop codons. Do you see how to algorithmically tell the difference? If not, that's fine. It can be hard to spot patterns, but you will get better at it with practice. One great technique to find patterns is to make a table. You might remember that we did this in some of our examples. We can then add more examples to our table, as I'm showing here, to help us see the pattern. Some with yes answers and some with no answers. Maybe you see the pattern now, or maybe it is still hard to see. What can you do if the pattern still isn't clear? Maybe adding more rows will help, or maybe not. Instead, we might start exploring the relationships between the items in the table. Here we have added another column for the difference in the index of the stop codon and the index of the start codon. The ones that have yes answers have differences of 6 and 12, and the ones that have no answers have differences of 4 and 11. What do 12 and 6 have in common that 11 and 4 do not? We might be able to think of a lot of things. 6 and 12 are both multiples of 6, but that doesn't make sense in the context of this problem. If we did more examples, we could find ones with yes answers that have 3 or 9 or 15. However, 6 and 12, as well as 3, 9, and 15, are all multiples of 3. This relationship does make sense, as we know that the length must be a multiple of 3. Now that you know the relationship you know that you want to look for, you need to do some math in Java. You need a way to ask if the difference between 2 numbers is a multiple of 3. If you took course 1 with us, you might remember the mod operator, which gives you the remainder when you do division. X mod y, written x %sign y, means divide x by y, but give me the remainder, not the quotient. This can help you with the problem at hand, since a number that is a multiple of 3 has a remainder of 0 when divided by 3. That is, if x mod 3 is equal to 0, then x is a multiple of 3. You can use other mathematical operators in Java. Plus, minus, times, divide, they're all valid. You can also use equals equals to see if 2 numbers are the same, not equals to see if they're different, and less than or equals, greater than or equals to check for inequalities. You can also combine simpler expressions into more complex expressions. This expression checks if a minus b mod 3 is equal to 0. It is evaluated by first evaluating a minus b, then taking that result and doing mod 3 on it. Then finally taking that result and checking if it's equal to 0. This is pretty much exactly what you need for the problem at hand, to see if the difference between 2 things is a multiple of 3. While you are learning about math in Java, there are several different types of numbers. Actually, there are some variations on these, but you don't need to worry about that right now. One type of number is int, which represents integer numbers like -2, -1, 0, 1, 2, etc. Ints can't have a fractional part. The other type is double, which represents real numbers, ones with fractional parts like 1.2 or 3.4, 5, 7. Of course, you could also represent 3, which is 3.0 with a double. You only want to use doubles when you need to, since they have some behaviors that can be really confusing to novice programmers. One word of caution about integers, however, is that math on integers always yields integers. So what do you get if you divide 5 by 2? If you're thinking 2.5, remember that you can only get an integer result, so you get 2. What about 100 divided by 3 times 4? You will get 132, since 100 divided by 3 is 33, and 33 times 4 is 132. So what if you do 100 times 4 divided by 3? Seems like you should get the same answer, right? Well, actually, now you get 133. Why? 100 times 4 is 400, and 400 divided by 3 is 133. These sorts of issues should not come up in these courses, but are good to be wary of if you're doing integer division. Another thing to know about math in Java is that it has order of operations, rules like math. In programmer speak, these rules are called precedence and associativity. As with math, a plus b times c means to do b times c first, then add that result to a. What if you have mod? It has the same precedence as division, meaning it takes place at the same place in the order of operations. So a minus b mod 3 means to do b mod 3. Then subtract that result from a. This is why we put parentheses around a minus b earlier when we wanted to do the minus first, then take its result, mod 3. Comparisons for equality happen very late in the order of operations. A plus b equals c minus d means to first do a plus b, then do c minus d, and finally compare the two results to see if they are equal to each other. These rules are typically like they are in math. Multiplication and division come first, then addition and subtraction. Also like math, you can use parentheses to group things so that they come first. If you aren't sure what order things will happen, you can always use parentheses to be explicit and be sure you get what you want. Okay, now that you know about math in Java, it's time to go improve your gene finding algorithm. Thank you. Welcome. I'm excited to work with you as you extend the programming and problem-solving capabilities you've developed for finding genes in a strand of DNA. You'll work on finding genes using a model of stop and start codons that more closely resembles the work done by genome and computational scientists as they work on problems such as personalized medicine and understanding genetic issues with many species. You'll learn about new classes from the edu.duke library, and you'll practice with new programming constructs that will allow you to repeatedly execute program statements until a problem is solved, like finding all genes in DNA or all links on a web page. Let's get started. I hope you have fun. Thank you. Welcome back. In this lesson, you're going to learn a powerful new programming construct, an indefinite loop. You'll also learn about another iterable from the edu.duke library. You've already solved problems using the file resource and URL resource classes from the edu.duke library. Using iterables made it possible to repeatedly access data stored in a file on your computer or via a URL from the World Wide Web. You'll use this concept of repetition to find all the genes in a strand of DNA, a problem that genome scientists do as part of their work, and a problem that models finding all links in a web page, or all the YouTube videos you might want to watch about cats, or dragons, or anything else. The key idea here is that you'll use the algorithm from a previous lesson that found one gene in a strand of DNA, an algorithm you've tested and have confidence in. You'll repeatedly apply this algorithm over the entire strand of DNA to find all genes, not just one. You'll also learn about a new iterable that lets you store intermediate results. Instead of printing all the genes you find, you will be able to store them so that you can look for particular genes after you found strings that could be genes, for example. By storing the results of a gene search or of other kinds of search, you can write separate methods to process the genes rather than including the processing with the finding. This separation of concerns, find genes, process genes, filter any of those genes that have specific characteristics, is a hallmark of good software engineering, writing a method to do one thing rather than doing several things. This separation allows you to reuse code more easily and to develop code more easily. The storage you use will be an iterable you can add to while the program you write is running. To be more concrete, you're going to solve a variation of a problem you solved once before, the problem of finding a gene in a strand of DNA. Genes are found in a strand of DNA at different sites within the DNA. In a previous lesson, you developed code for finding one gene, like the region shown in red here. You found this gene by looking for particular markers called start codons and stop codons. These markers were used to identify the part of a string that could be a gene. You could have used a similar algorithm to find where a link occurs in the HTML text of a web page, looking for ahref rather than ATG, for example. DNA typically carries more than one gene, however, so rather than finding this one gene that's marked in red, you'll use programming techniques to find all the regions in a strand of DNA that could code for a gene, regions that begin with the start codon as shown here, but that also are indicated by one of 3 stop codons. In the next group of lessons, you'll learn many things about Java and programming as you practice solving this gene-finding problem. You'll learn how to repeat a process many times, even when you don't know how many times this is. You'll do this by using a while loop, a new kind of loop that complements the for loop you've used with iterables. You'll learn about the storage resource class from the edu.duke library. Using a storage resource object will allow you to add selected values to the storage and then access them in your code using the standard for loop with iterables you've used before. This storage will also be a preview of future programming techniques you'll learn about in using arrays to store values. You'll also practice with developing if statements and Boolean expressions that use what's called short circuit evaluation. This will be an important part of the practice and knowledge you'll gain as you move toward becoming a better programmer and problem solver. Thank you. As you have been learning about strings, you have been improving on your algorithm to find genes in DNA. However, let us take a moment to think about what your algorithm will do on this string. It will find the start codon ATG at index 0. Then it will find the stop codon TAA at index 8. It will then check if the distance between them, which is 8, is a multiple of 3. Because 8 is not a multiple of 3, your algorithm will conclude that this is not a valid gene. Between the ATG and TAA, there is one full codon, ATC, and 2/3 of another codon, GC. But if you were to keep looking past this TAA, you would find another TAA at index 15. Now the distance between the ATG and TAA is 15, which is a multiple of 3. So this is a valid gene. The first TAA that we found was not actually a codon, but rather pieces of 2 adjacent codons, the T from GCT and the AA from an AAT. Your next improvement to the gene finding algorithm is to add this functionality, to make the algorithm keep looking until it finds a stop codon that is a multiple of 3 away from the start codon. Having just worked that example, let us now do step 2 of the 7-step process and write down what we just did. The first thing we did was to find the ATG. Then we found the first occurrence of TAA after the ATG, which was right here at index 8. Then we checked if the distance between them was a multiple of 3 or not. In this case, it was not. So we found the next TAA after this first one. The second one is right here at index 15. Then we checked if the distance between this TAA and the start codon was a multiple of 3. It was, so all of the substring from 0 up to 18 was our answer. In this particular set of steps, we checked in 2 places to see if the distance was a multiple of 3. If this works in the general case, you can just implement this algorithm with familiar if-else statements. However, do we always only need to check twice? Let's look at a different DNA string. With this DNA string, we would need to check 3 times. The first 2 TAAs are not a multiple of 3 away from the start codon, but the third one is. Would checking 3 times be enough? Could we have to check 4 times, 5, 10, 50 times? This raises the question of how many times we have to check in general. And the answer is that we cannot pick a particular number of times. Even if you wrote 50 if-else statements, we could come up with a DNA string that has more than 50 TAAs that are not a multiple of 3 away from the start codon before finding a valid one. Instead, we need to write our algorithm so that it repeats the checking however many times it needs to. As you have seen before, repetition in your algorithm will turn into a loop when you translate the algorithm into code. To express your algorithm with repetition, you will need to make the repetitive steps the same and figure out what to loop over. Previously, you have seen for loops, which iterate over the elements in some iterable, such as pixels in an image. Now you're going to learn about a new kind of loop, known as a while loop, which lets you iterate as long as some condition holds. Before we try to generalize these steps by finding repetition, let us be a bit more precise about what we did. We found the first ATG at index 0. For the first TAA, we started looking at index 3 and found it at index 8. We checked if 8 was a multiple of 3. It wasn't. So we started looking at index 9 for the second TAA, and we found it at index 15. We checked if 15 was a multiple of 3. It was, so everything between was our answer. Now, let us take these steps and generalize them. We looked for ATG here. Why was that? We always want to look for ATG because it is the start codon. What about the fact that we found it at index 0? We're not always going to find it at index 0. However, we are going to want to use that information. So let's give that a name. When we turn this into code, what will be a variable that we will assign to this in this line and then use later? In particular, we'll call it start index. What about looking for TAA? We will always want to look for TAA since that is the stop codon. Will we always start at index 3? Probably not. Why did we start at index 3 here? We started there because it was right after the start codon that we found. In the general case, this would be start index plus 3. We won't always find it at index 8 either, so let's give that a name too. We'll call it current index. Let's also be a bit more specific about the distance between them. It is cur index minus start index, which happens in both of these steps. Next, you aren't always going to start looking from index 9. But why do we start at 9 here? If you look back at where we worked the problem and wrote down our steps, we started at 9 because The previous one started at 8. In our generalized algorithm, we named the previous location cur index, so we can start from cur index plus 1. We also should name the location where we found it. Should we give it a new name, such as next index? Or should we just update an existing name, such as cur index? In this case, we want to update cur index since that represents where we have found the most recent TAA. If you did not realize this right away and gave it a different name, you would realize it later on as you try to make the steps uniform so that you can express the repetition. Finally, we'll generalize the last step to just indicate that the text between them is the text from start index to cur index plus 3. Now these steps look repetitive. The repetition may be a bit hard to see since it only happens twice, but if you wrote down the steps for a string with more TAAs that don't work, you would see that you do these steps over and over again. To make this repetitive, let's write it down like this. Notice that steps 4, 5, and 6 are what we will repeat. We've slightly adjusted the steps from before to reflect the choice we were making in step 4 and the two possible outcomes in steps 5 and 6. However, we have left the conditions under which we repeat these steps blank here. How do we know when to stop repeating them? Also, what would you do after you stop repeating this loop? We would stop if we run out of TAAs. If that happened, cur index would be -1, which you know from having learned that you get -1 when you cannot find something in a string. If you were to encounter this case, it would mean that there is no valid gene in the string. So you should give an answer of the empty string. If you did not see this right off, what could you do to figure it out? You should work more examples until you understand the pattern. Now your algorithm is generalized. But you'll need to learn about while loops before you can translate this into code. Thank you.
To implement our improved gene finding algorithm, you need to learn about while loops, the code that generally comes up when you have a step in your algorithm like, as long as some condition is true. You can see an example of a while loop here. Let's look at this example to delve into the syntax and semantics of the while loop. All while loops start out with the keyword while. Then they have some condition, sometimes called a guard, in parentheses. This is the condition that you want to check to see if you should continue doing the loop. Then you have the loop body in curly braces. These are the statements that should be executed each iteration of the loop. Let's walk through this example to understand the semantics of the loop, what it means. For example, let us assume that x was previously declared and initialized to 0 and y was initialized to 7. When execution reaches the while loop, the first thing that happens is Java evaluates the condition, is x less than y? In this particular case, that means is 0 less than 7? 0 is less than 7, so the condition evaluates to true. Since the condition is true, execution will enter the loop body and continue executing statements there. The first statement prints x, which is 0, so we would output the line 0. The second statement sets x to x plus 3, which would update the value of x to be 3. Now execution has reached the end of the loop body. The closed curly brace marks its end. Then execution goes back up to the start of the loop, and we are right back where we started, but the variables have different values. X is 3 instead of 0. We continue following the same rules. Evaluate the condition, 3 is less than 7. The condition is true, so we enter the loop body. Print x, which is 3, and update x to be 6. Now we have reached the end of the loop again, so we go back up to the start of it. And again, follow the same rules check the condition. It is true, so we enter the loop body. Print x, which is 6, update x to be 9. Now we have reached the end of the loop body again, so we go back to the start. Yet again, we follow the same rules. Now, when we evaluate the condition, something different happens. Is 9 less than 7? No. So the condition is false. Instead of entering the loop body, we go past it. We would then continue executing whatever statements come after the loop. Great! Now you have learned the basics of while loops, their syntax, the grammatical rules for writing them, and their semantics, their meaning. Now you are ready to go code your improved gene-finding algorithm.
Okay, now you've learned about while loops and are ready to turn this algorithm into code, which will search for a TAA which is a multiple of 3 away from the ATG, even if there are other TAAs in between, which are pieces of 2 different codons stuck together. So here's the algorithm that we came up with, and now we're ready to turn it into code. Our first step says to find the first occurrence of ATG and call its index start index. So as you're hopefully becoming familiar with by now, we're going to say int start index equals DNA.index of ATG, because that's going to find us the first index of ATG. Our second step says find the TAA starting from start index plus 3 and call this result cur index. I'm going to say int cur index equals DNA.index of, and we're looking for TAA, and we want to start from start index plus 3. This should also be becoming hopefully familiar to you with index of starting from a position. Now we're going to say as long as cur index is not equal to -1. This is what you've just learned is a while loop. I want to repeat some steps as long as some condition is true. So while cur index is not equal to -1, I want to do these steps here. And I'm going to go ahead and I've indented my steps to match the grouping that was in our algorithm in the slides, and I'm going to just go ahead and put the curly brace here so I won't get confused later. All right, and so what do we want to do as long as cur index is -1? Well, or is not -1. We want to check if cur index minus start index is a multiple of 3. You've seen how to do this previously, where we can subtract cur index minus start index, take that mod 3, and see if it's equal to 0. And we said if so, we want to do one thing, and if not, we want to do another thing. And as you've probably gotten familiar with by now, if not is going to be else. We want to do some other thing in this case. So if so, the text between start index and cur index plus 3 is your answer. So anytime a method knows its answer right away and is done, we're going to return that answer back to whoever called us, which finishes the method and gives back the answer. So we want return, and we want the text between start index and cur index plus 3. What method would you use for this? Hopefully you've become familiar enough with string methods by now that substring is what comes to mind as what you'd want. So DNA.substring, start index, cur index plus 3. And then we said if not, update cur index to the index of the next TAA starting from cur index plus 1. So anytime we want to update a variable, we're going to use an assignment statement, and we can find the next one after that, again using index of to search from a specific position. Index of TAA from cur index plus 1. All right, so that just wrote that step down as it was. My brace is not indented right, so I'm just going to fix that. And then if we get to the end of this loop, if we keep going and cur index is -1, meaning we couldn't find any more TAAs, then our answer is going to be the empty string. All right, so I'm going to save that. I'm going to go over here and I'm going to hit compile. And it says reached end of file while parsing. And oops, I messed up in here somewhere. I'd written some test cases before we started. You'll notice that it's highlighting this curly brace, and if I scroll up, it's highlighting this curly brace. When I wrote these test cases, I forgot to put the curly brace that ends the method. Fix that really quickly. Compile it. And find gene simple. Yeah, I copied and pasted this testing code and changed the method name and didn't change that. So we'll fix a couple careless mistakes there. This is the danger of copying and pasting. You should never do it. Now really it will compile. All right, so I'm going to make one of these. And you'll notice here that I've written a little test method like we've had in the previous ones. Since things are getting a little more complicated with our test cases, I've put these comments here just to mark where the codons are. So this ATG is one codon, and then I've just marked here that this CTG is another codon. And so we can see that this TAA here, for example, is a whole codon, and this TAA here is not a whole codon. So we would expect this method to find this gene right here. And similarly for these other ones. So I'm just going to run this method really quickly. Okay. And for this first one, what did we expect? We expected ATG, CGT, AAT, TAA, ATG, CGT, AAT, TAA. So we got exactly what we wanted. And notice this is where that while loop we wrote just came into use, because this looks like a TAA, but we would have found that it wasn't a multiple of 3, and we would have kept going and found there actually is one later on. And then similarly, we've done this other string, which is a little bit longer, has some more things that look like maybe they're TAAs, but they're not, but it does have a TAA at the end. So we get that really long gene there. And then at the end here, if you look, we don't actually have any TAAs, and we get the empty string, which is what we'd want. So there we go. We've turned this algorithm into code using a while loop, and now it will look for any TAA which is a multiple of 3, even if it's not, even if there's one that's earlier that's not a multiple of 3 away, so that we can get the right answer.
All right. So far you have developed an algorithm that would find the start and stop codons, figure out that the length is a multiple of 3, and return the DNA string for this gene. Now it is time to add another layer of realism and thus complexity. There are actually 3 different stop codons: TAA, TGA, and TAG. So far your algorithm has only looked for TAA, but now it is time to make it look for the first one of any of these 3 stop codons that is a multiple of 3 away from the start codon count. So which one of these stop codons is the one you want? Well, the first TGA is not a multiple of 3 from the start codon, so that isn't the one you want. The second TGA is also not a multiple of 3 from the start, so you don't want that either. That leaves you with TAG and TAA, which are both multiples of 3 away. You want the one that comes first. In this case, the TAG codon at index 12. Okay, so now you know what the problem is. Let's solve it. To do this, let's go back to our algorithm that we have from before. The only thing that was specific to looking for TAA was these 2 occurrences of TAA in steps 3 and 7. Could we start from this algorithm and have most of our work done for us? The best way to do this is to split the problem up. We want to abstract out the part that searches for a stop codon into its own method. We'll call it find stop codon, and it will take the DNA string to search in, the index to start from, and the particular stop codon string, such as TAA, TGA, or TAG, to search for. The algorithm will need a few changes, such as returning the index instead of the text, and looking for any of the 3 stop codons, not just TAA. However, the basic mechanics of the algorithm, searching for a codon that is a multiple of 3 from the start, remain the same. We'll come back to those changes in a minute. For now, we'll just assume we have a find stop codon method that works. Once we have abstracted that out into its own function, we could use it to find the TAA stop codon. And call the method again to find the TAG stop codon. Then one more time to find the TGA stop codon. Note how this corresponds to what we did by hand. We identified the positions of the TAA, TAG, and TGA stop codons. It is a bit different from our example by hand since find stop codon will only give us a position that is a multiple of 3 away from start index, whereas we showed a TGA that was not a multiple of 3 for the purposes of illustration. Now that we have those 3 positions, we want the one that comes first. So we would just need to take the minimum of 3 values, which we will call min index. Finally, our answer is the substring from start index to min index plus 3. Now let's look at what we need to do to the algorithm that we abstracted out into find stop codon. First, these will no longer always be TAA. Instead, they will be the stop codon parameter, which tells us the particular stop codon we are looking for. The other change is that we want to give back the index where we found the stop codon instead of the text between the start and stop codons. Why? Our other algorithm needs these indices to compare to figure out which one to use before it gets the text. Whenever we find a valid stop codon in step 4, we can just give cur index as our answer. However, what should we give back to represent no valid index found in step 6? -1 is often a good choice to indicate no valid index, but let's see how this would work with the way we are using the result of this function. If we were to return -1, we could make it work, but we would have to change this code to do more complex comparisons than just taking the minimum of these 3 values. You'll see this approach later and learn a new concept in the process. But for now, let's make this work such that we can just take the minimum here. Instead, we can return the length of the DNA string, since that is larger than any valid index. Of course, now that we are doing that, we should explicitly check for the case where no valid stop codon was found. If min index is the length of the DNA string, none of the 3 stop codons was found. Okay, great. Now we have an algorithm. Let's go turn this into code. Thank you.
Hi, welcome to another version of Gene Finding. In today's episode, we're going to look for 3 different stop codons. In the previous coding exercises, you've seen code that found 1 stop codon, making sure it was a multiple 3 away from the start codon. In this version of the code that you've already seen described previously, we're going to look for 3 different stop codons. As you can see here, we have TAA, TAG, and TGA. And in order to find each of those, we're going to write another method, a method called find stop codon that we saw outlined before with our 7-step method. Up here, I've got this method, find stop codon, and it has 3 parameters. DNA stir, the string of DNA in which we're searching for a gene, start index, the location at which we're going to begin the search, and stop codon, the specific codon we're going to be looking for. We've got the code from our 7-step process, and what we're going to do here is write the code that goes along with this. You can see here, as we saw in the previous version of code, I'm going to create a variable cur index, and I'm going to make it the location of the first stop codon starting at start index plus 3. So as we've seen before, the way we do that is create an integer variable, cur index, and we write cur index gets the location in DNA stir of the stop codon starting at start index. That's exactly what it says here. Find the stop codon starting from start index plus 3, so I better make sure I'm doing that correctly, and store that value in cur index. Now, as long as cur index is not equal to -1, and as you've already learned, that's a while loop, so we're going to say while cur index is not equal to -1, and when I type the right curly brace, as you see here, I'm going to make sure I put in a left curly brace at the same time, indented the same way. And one thing I can do there to make sure that I've got it right is to compile my program. So I'm compiling it, and you can see I've got no syntax errors. So I know I'm on shape. Now, as long as cur index is not equal to -1, so I've just coded that, check to see if cur index minus start index is a multiple of 3. I'm going to store that difference. I'm going to say int diff gets cur index minus start index. Now you don't need a new variable for that. As you saw in the previous video, you can just say if cur index minus start index mod 3 is equal to 0. But this is sometimes easier conceptually to say if diff mod 3 is equal to 0. That means, and you can see I've already got my curly braces in there, return cur index because it's my answer. So I'm just going to say return cur index. That's what it says here. Check if cur index minus start index is a multiple of 3. And if so, cur index is the answer, return it. So I've got those two things taken care of. And it says, if not, update cur index. So if not, that would be else. And if you think carefully, you might see that although I don't need the else because I've already returned, but it's probably easier to write it that way in terms of thinking about it. It says, update cur index, looking for stop codon again, starting from cur index plus 1. So you can see up there how I looked for it. So I'm going to do the same thing. Cur index gets DNA stir dot index of, I'm still looking for stop codon. And remember, that's a parameter to this method. And I'm starting, according to our comments, at cur index plus 1. So cur index plus 1. And if we exit the loop, we didn't find the stop codon, so we return DNA stir.length. You can see here that the loop is going to continue while cur index is not equal to -1. If it is equal to -1, we've exhausted the string, the DNA strand in which we're searching, and so it says return DNA stir.length. As we'll see later, when we write this code, that's to ensure that when we find the minimum value, that our code works properly. So I'm going to make sure that my method looks right, find the stop codon, and I started at index plus 3, so that's the last comment I have. I'm going to get rid of that comment now. So I've stored in cur index the location of stop codon. While that's not -1, if it's a multiple of 3, I'm done. And if it's not, I need to keep searching. My class compiles, but just compiling doesn't indicate at all that I'm done. I've written some test code down here, test find stop. And you can see, as you saw in the previous coding video, I've created a strand of DNA, and I'm going to look for TAA, which is one of the stop codons. And I've got it in 2 different places. When I run the method, you'll see what it does, and then I'll describe how that testing works. So here's my workbench. I'm going to right-click on this and make a new object. It comes in the object workbench. I'm going to right-click again, and I'm going to run test find stop. And you can see it printed tests finished. That means all the tests worked correctly, because if there was an error, my print statements would have indicated that. Let's look at that testing code so you can see how I did that. In testing find stop, the first thing I did was look for the stop codon TAA starting at index 0. And you can see here I've got the indices printed above the string. So TAA here is at index 9. 9 minus 0 is in fact a multiple of 3. So it should have returned 9, that it found TAA. And if it wasn't 9, I got an error. To see how it might work if it returned the wrong thing, suppose I said if dex is not equal to 10. Now that would be a mistake because we know it returns 9 and it's supposed to return 9. You'll see in this case when I run it that it will print something. Right-click to create the object, right-click to invoke the find stops, and you can see error on 9. Now that wasn't an error because I knew I was supposed to get 9. All these tests print something if there was an error. And if there's no error, they don't print anything. My last print statement prints when the tests are finished. So what we have now is this method find stop codon written and tested, and we're ready to move on to the next method, which was the same method that you saw before for finding just a single stop codon, and now we're going to find any occurrence of a stop codon, any occurrence of 3 different stop codons. We're going to find TAA or TAG or TGA. This will be a very straightforward use of the abstract method find stop codon that I've already done, so I'll do this very quickly. Find the first occurrence of ATG, the start codon, and store that in start index. So int start index gets DNA.index of ATG. If start index is -1, I'm done. There's no start codon, so I can't find a gene. So if start index equals -1, return -1. I did not, return the empty string. That's what it says right here. And this method returns a string, so I'm returning the empty string. Now I'm going to store in TAA index the result of this method call. So I'm just going to copy and paste this method call, even though, as you've learned, copy and paste does not always work as you intended. So store in TAA index that method call. And then I'm going to store in TAG index the same thing, but it says use TAG. And then I'm going to store in TGA index that call with TGA. I'm looking to make sure that my copy and pastes worked properly, because copy and paste can sometimes be your friend, but sometimes it can get you into trouble. So I've done that. I've used TAA index, TAG index, and TGA index. I've got all those variables. The next comment says store in min index, the smallest of these 3 values. So I have to find the smallest of all these values. And one way to find the smallest value is to use the min function in the math library. So I can say int min index gets math.min of TAA index and TAG index. That's the smallest of these 2. Maybe I call that temp. And then I'll store in min index the minimum of temp, which is the first 2, and the last one, which is TGA index. Let me go over that again. I've found the minimum of TAA index and TAG index. That's these 2. And then I found the minimum of that value, which is the smallest of 2, and my last index, TGA index. And it says if this is DNA.length, I return the empty string. So if min index is equal to DNA.length, return the empty string. Otherwise, the answer is the text from start index to min index plus 3. And as you saw before, that uses the DNA substring method from start index to min index plus 3. I'm going to make sure I've got that right. Compile. Cannot find symbol min index. And that's because I spelled that wrong there. Now it compiled and there are no syntax errors. Just compiling doesn't mean my code works. I really need to test it. So we'll leave it to you to test this, just as I found a test method here. You could write a test method to test these. It'd be very similar to the one that you saw in the previous video, but I could use TAA and TAG and TGA. Once that test method is done, I'll be confident that my method worked correctly. One final thing, this use of math.min to store in temp and to store in min index, just to let you see, it would be possible to do that on one line. I could say math.min of TAA index and math.min of TAG index and TGA index. It's possible to chain the occurrences of min index together like that. I'll leave that as a comment so you can look at it and think about it. And that's it for coding with DNA and 3 different stop codons. Have fun. Okay, now you have an algorithm which works with any of the 3 stop codons. However, let's explore how you could make this code work if we decided to have find stop codon return -1 when there's no valid stop codon rather than the length of the string. Note that this is a perfectly valid design choice and mirrors what the .indexOf method does, but we need to learn a new concept to make it work with our code. You'd want to change line 6 of the gene finding algorithm to reflect this choice. You cannot just take the minimum, since -1 is smaller than any valid index. So what you want to do is pick the smallest number that's not -1. Let's look at a few examples. Here, TAA index is -1, and TGA index is 3, and TAG index is 6. What index should you pick for the stop codon? Well, we want 3, because it's the smallest number, which is not -1. Notice we can't just pick the minimum one, because that would give us -1, which is not a valid value here. What if we had 5, -1, and 8? We'd want 5. Likewise, with 10, 4, and -1, we'd want 4. And with -1, -1, and 11, we'd want 11. Let's think about how we can express this decision process algorithmically. In the first example, we compared these 2 numbers first. Even if you think you're comparing all 3 at once, you're really comparing 2 at a time, very quickly, and perhaps without thinking about what you're doing. Of these 2 values, we prefer 3, since the alternative is -1. And then we compare 3 against 6. We choose 3 since it's smaller than 6. In the second example, we'd compare 5 to -1. Then we'd choose 5 and compare this against 8. In this choice, you'd pick the smaller, which is 5. In the third example, you'd compare 10 against 4. You choose 4 because it's smaller. And then you'd compare 4 against -1 and choose 4. In the final example, you're comparing -1 against -1. It doesn't really matter which you pick, they're the same. You then compare -1 against 11, and you choose 11. Note, you should think about what you would do if all 3 values were negative. What would that mean? It would mean that no valid stop codon exists. We'll have to use that in our code. Now, how do we think through how we made these choices? We're only going to look at the logic involved in making the choice between one pair. That same logic will work with the second choice. In the first example, we picked TGA index because TAA index was -1. In the second example, we picked TAA index because TGA index was -1. In the third example, where neither is -1, we picked TGA index because it's smaller than TAA index. And in the final example, it didn't matter which we picked since both were -1. Let's write down what our logic is for making that selection. If TAA index is -1, we'd want to pick TGA index. But that's not all there is to it. We'd also choose TGA index if both TGA index is different than -1 and TGA index is less than TAA index. Notice how we've expressed this logic with or and logical connectives, which let us make complex conditionals out of simple ones. Now let's put that logic into the algorithm we're working on. We'll use that logic to pick between TAA index and TGA index, and we'll store the best choice there is in a variable called min index. Then we'll choose the same logic to choose between min index and TAG index. If min index is -1, there were no valid stop codons, so we'll give back the empty string. Otherwise, we've found a gene. Now let's see how we express these ors and ands in Java. You can express and with 2 ampersands. This is a Shift 7 on most US keyboards. We can see in this example if x is less than y and y is less than z. you can express OR with two vertical bars, also called pipes. On most US keyboards, this symbol is Shift backslash, and we can see an example here. If A is greater than B, or C is less than D. In the particular case of the algorithm we're working on, you could express the step as shown here. Notice how the OR corresponds to the two vertical bars, and the AND corresponds to the two ampersands. AND OR have special rules called short-circuit evaluation, which basically means that if Java can figure out the result of an entire expression involving AND and OR by evaluating only the first operand, then Java will skip evaluating the second operand. Let's look at an example. Suppose x is 8 and y is 1. X is less than y is not true because 8 is not less than 1. So x less than y evaluates to false. There's no reason to evaluate y less than z, because whether it's true or false, the whole AND expression will be false, because false and anything is false. For OR, consider this example, and suppose A is 3 and B is 1. Here, A is greater than B is true, because 3 is greater than 1. So the whole OR expression will be true regardless of whether C is less than D or not. So there's no point in evaluating the expression C less than D, because true or anything is true. Why is short-circuit evaluation important? If you skip evaluating y less than z in this example, it doesn't really matter so much. But it's much more useful when the second operand could crash your program if it's evaluated. For example, here we're checking if x is less than the length of a string and that the character at the xth index of the string is the letter A. If the first condition is false, then x is not a valid index. It's beyond the end of the string. So trying to get the xth character with the .char method would crash the program with a string index out of bounds exception. But fortunately, this line of code is safe because of short-circuit evaluation. The .char method will never be called when x is greater than or equal to the length of the string. Relying on short-circuit evaluation is a great example of defensive programming and one of the tools in your Java programming toolkit. Have fun! Hi, welcome back to gene finding yet another time. In this version of the program that we're writing to find genes, we're going to make one small change to what we return when we look for a stop codon, and that change is going to mean that we have to use some complex Boolean expressions using ands and ors to make our code work properly. So as we've already seen, the one small change we're going to make is that instead of returning dnastir.length to indicate that no stop codon was found, we're going to return -1. That's a good value to return to indicate that nothing was found, because now our code mirrors what, for example, the indexOf method in the string class uses. It uses -1 to indicate that no string was found when searching. Now our findStopCodon method also returns -1. Now that change means that our test function won't work correctly. Remember, we had a test function down here. These functions will now fail because they didn't find that. So to see that very quickly, I'm going to run this new class, create an object on the object workbench, and test the find stop codons. And you can see I got an error 26 twice. And that's because in my program, I had, if it's not equal to 26, so if I change that to -1, compile, and now test my program again, finding stop codons, I can see that my test's finished. So my test program needed to change to recognize this return value of -1 rather than the length of the string. Now I'm confident that my stop codon method with this one small change works correctly, and that it returns -1 to indicate that no stop codon was found. That means my find gene method is also going to need to change. Rather than using math.min, I'm going to need these Boolean expressions that you've just learned about. And I've put here in my comments what those Boolean expressions are supposed to do. So I'm going to simply translate this stuff, the comments from my 7-step process, into code. And what that code says here is if TAA index is equal to -1, or, and we use that double vertical bar for or TGA index is not equal to -1 and TGA index is less than TAA index. Now that's a lot. So let's look and make sure we got that right. It says if TAA index is -1 equals -1, or TGA index is not equal to -1 and TGA index is less than TAA index. In that case, it says set min index to TGA index. So I'm going to say min index gets TGA index, just as it says there. That means I'm going to not use these versions of min index, which were from before. But if I compile this code, I'm going to get an error message, something about temp. So if I comment that out, let me comment all of these out. Now I get that variable min index isn't known. So I'm going to define min index, and I need to give it a value. I need to give it some value. I'll just give it 0. I'm going to put in my else statement here what it says to else set min index to TAA index. Else min index gets TAA index. So what I've got now in my code is a translation of if TAA index is equal to -1 or TGA index is not equal to -1 and this expression, then set min index to TGA index, else set min index to this value. Then I still have yet another Boolean expression to write. I need to write if min index is equal to -1 or TGA index is not equal to -1 and TAG index is less than min index. In that case, my comments say set min index to TAG index. So I'm writing that. I'm simply translating this into my code here. Finally, it says if min index is equal to -1 rather than DNA.length, return the empty string. Otherwise, return this. My program compiles, well, almost compiles. I forgot a second parenthesis up here, but that's an easy thing to fix. Well, maybe not fixing it that way by erasing it all. Maybe I should type in a parenthesis instead. Now when I compile my program, it works. How do I test this? Before, in the previous version, I didn't have a test program, a test method. Now I do. I have my test method, findGene. So I'm going to try that out, see if it works. Right-click to create an object. Right-click to testing findGene, and it just simply printed tests finished, which is what I wanted, since in findGene, I looked for a gene. I found this start codon, and I found this stop codon, TAA. Now, I could change this TAA to a different stop codon, and I would keep testing those to make sure that my method works correctly. I'll leave that to you, because as we've already seen, testing is as important as writing your code, because you need to be sure your methods work correctly. Have fun testing, have real fun programming. Hi. So far, you've written a method to find a gene, and gradually improved it. It's gotten much more sophisticated than when you first started, although it's still a bit of a simplification of what you'd actually do. Rather than continuing to refine this method, let's ponder a different facet of searching for genes. So far, you've only been looking for the first gene in a string. However, strings may have many genes. What if you wanted to find them all and print them all out? You can already find one, although you might want to make some slight adjustments to the methods so you can start looking midway through the string. Since you can find one, and you want to find many, you want to repeat steps using a loop. Loops should be getting pretty familiar by now. Since you might want to repeat things as long as there are more genes, you could make use of the while loop that you recently learned about. However, there's a bit of a difficulty here. We won't know if there are more genes until we start searching for them. This may make it seem hard to write the loop condition. There are many ways to deal with this situation in code, but the one we're going to teach you about is how to use a break statement to leave the middle of the body of the loop. We'll work through a slightly shorter example than we normally walk through in developing the algorithm to print all genes. If you don't understand this completely when we finish, pause the video and work through steps 1, 2, and 3 yourself. We're going to show you how it operates on this DNA string as we write it. First, we're going to set start index to 0. Start index will represent where we start looking for the next gene. Then we're going to repeat some steps, as long as there are more genes after start index. We want to find the next gene after start index. We want to print that gene out, and then set start index to just past the end of the gene we found. To show you how the algorithm would continue working on the string, we then go back to step 2, and keep repeating these steps as there are more genes after start index. Notice, this is the difficulty we alluded to before. We need to know if we will find more genes or not, but we haven't looked for them yet. We'd find the next gene, print it out, update start index, and then realize we should stop repeating steps because there are no more genes. However, we have this difficulty. We need to know if there are more genes in step 2, but we don't look for a gene until step 3, which makes the algorithm a bit awkward to implement. Really, we'd like to make a decision about whether to keep going or to stop right here between steps 3 and 4. Here's a slightly modified version of the algorithm which does exactly that. Notice that our repetition instructions no longer have any condition. They just say, repeat these steps. We'll figure out later when to stop. Likewise, we now have another step in the middle of the loop that says, leave the loop if we did not find any genes. This will be much easier to implement once we learn how to translate these kinds of steps into code. For step 2, repeating steps without checking any particular condition, you can simply write while true. If the condition of a while loop is simply true, the code will always enter the loop body when we reach the top, because true always evaluates to true. The other new piece of Java syntax we'll need is the break statement. This is how you say, leave this loop. In this example, we've translated if no gene was found into an if statement that says if gene.isEmpty. The isEmpty method for a string returns true if the string is the empty string, and false otherwise. Remember, our gene finding method returns the empty string whenever it can't find a gene. Inside the if statement, we've seen leave this loop translated into a break statement. A break statement, which is written in Java simply with the keyword break followed by a semicolon, causes Java to leave the current loop, regardless of whether it's a while loop or a for loop or any kind of loop you might yet learn about, like a do-while loop. Basically, Java jumps past the close right curly brace that ends the loop. Now we know how to implement these steps. Let's turn the algorithm into code and try it out. We'll find every kind of gene there is. Have fun.
All right, so you've been learning about while loops and break statements and working on your gene finding algorithm. And your current task is to write a method which will print out all the genes in a sequence of DNA. So we have here the print all genes method, which takes in a string for the DNA and has the algorithm or pseudocode that we came up with in a previous video. Now, we have earlier here in this code the gene finding algorithm that you developed along with Owen in a previous video. And we're just going to make one small change to it. I'm going to have it take one more parameter to say where to start. And this is going to let us start looking for a gene somewhere in the middle of the sequence of DNA. So once we've found one at the beginning, we can start looking for one after that by passing in this index. And we'll just pass that to index of to tell it where to start looking for the first start codon. So with that small change, we're going to go back here and start translating our algorithm into code. The first thing we said to do was to set the start index to 0. So we haven't made a variable called start index yet, so the first thing we need to do is declare start index. It's going to be an int since we're setting it to 0. It's going to tell us a position in a string, also a good clue that it's an integer. And then we're going to repeat the following steps. So you're used to repeating steps by now. You've done things for each pixel or each of a variety of other things before with for each is a lot. You've also seen some examples of while where you've had a condition for as long as something. But here we want to repeat some steps and then figure out somewhere else inside those steps when we're done. So we're going to write while true and then put curly braces around our steps. And then we're going to go in here and we're going to start doing stuff and then figure out when we want to stop repeating these. Now we want to find the next gene after start index. Finding a gene is a big complicated step. You've been devoting lots of effort and thought into how to do that. Fortunately, we've abstracted that out into a method so we can just call it and let find gene that we've already written do all of that work for us. So what does find gene take? It takes a string for the DNA and an int saying where to start, and then it returns a string. So here we want to call find gene, passing in what DNA? Well, this DNA that we're working with. And where do we want to start? At start index. And then it's going to give us back a string as its answer, so we want to give that a name. I'm going to call it current gene. We didn't say to give it a name in our steps, so we kept referring to it without a name. Well, we kind of know what we mean, but it's good to give things names in your steps anyways. And now we can refer to that gene that we found. If no gene was found, leave this loop. So if something is the case, do some other steps. By now, you should be getting very familiar with if statements. So if no gene was found, how do we know if no gene was found? What does find gene do if there's nothing left? If you don't remember, we can go back up here and look. We can see that it returns this empty string. So we want to know, is current gene the empty string? Fortunately for us, strings have a .isEmpty method, which will tell us if they're the empty string. How would you do that if you didn't know? Well, you could go look at the Java documentation. Are there other ways to figure out if a string is empty? Sure. You could see if its length was 0, for example. Any way that you can find that works is a good way to do it. All right. So if this gene is empty, if current gene is empty and we didn't find it, what do we want to do? We want to leave this loop. That is, we want, Java's executing along and it gets here, we want it to jump down here past this loop. That's exactly what a break statement does, which you just learned about. So we would get here and then come down here. We've basically put the loop condition in the middle. All right, if we don't break out of that loop, we want to print out that gene. System.out.println, hopefully you're getting somewhat familiar with that. We can print out that current gene. And then we want to update start index to be just past the end of the gene. All right, so now this seems a little tricky. Like we wrote a step that's a little bit complicated and maybe we have to think it through a little bit. So let's just go down here to where I've got some testing and think about what we're going to do. So I've written some methods to help us test. And let's think through one of these cases here. So so this test on just prints out that we're testing it, and then does print all genes. So we say, okay, start index is going to be 0. We're going to find this gene right here, which is length 9, right? And so then after that, we would want our new start index to be 9, okay? So we might think, aha, we just want to add the length of the gene, right? That got us from 0 to 9. That's a good first guess. Now let's think about this next one. So then we're going to go and we're going to find this next gene here, which is length 3, 6, 9, 12, 15. But that didn't start right where we left off, right? So if we were to only add 15, we'd end up here in the middle of this gene. And we want to end up over here. So what do we need to do? Well, we need to add the length to the start position of this gene. How can we find that gene? Well, index of is becoming your friend, right? So start index is going to be DNA.index of current gene starting from start index plus current gene dot length. Right? That seems kind of magical. Let me just explain that again really quickly. Right? We want to find where that current gene was in the string. We can do that by looking for it again, starting at start index. So that's going to tell me, this gene was right here. And then we can add its length to end up past here. That'll work for this first one because looking for this first gene from start index of 0 is just going to give me 0. And then when I add its length, I'm going to end up here. All right? If that still doesn't make sense to you, work it out on your own. So now I'm going to hit compile. All is well there. And I'm going to come over here and I'm going to make a new object. And then I'm going to run my test method. And you can see it says, all right, I'm testing print all genes on this sequence of DNA, and it's got 2 of these. Back over in my code, I tried to make this a little easier for us to see. So we've got this gene here, and then we've got this gene here. And these little V's were just for me to keep track of the codons. And those were what it printed here. I tested it on the empty string. I wouldn't expect to find any genes in there, but it's always good to test on these like wacky corner cases where maybe our code would break if we weren't careful. We didn't find any genes, but our code didn't crash either. That's really good. And then on this one, where we have this one long gene here, which we found and printed out, and then this really short gene here, which we also found and printed out. So that worked well. And the important thing here, the new lesson, was this while true, figure out if we want to keep going in the middle, and then break.
All right, now you can iterate over all the genes in a DNA string and print them out. If you wanted to iterate over the genes in a DNA string and do something else to them, the algorithm would be pretty similar. In fact, for whatever you want to do with each gene, it would look pretty much like this. The line in blue is the only thing you would change to do whatever you might want to. Maybe printing only those genes that meet some condition, counting genes, saving them to a file, building a web page with all of them, or anything else you can think of. So, if you wanted to do these other things, you might copy the algorithm you have pasted, paste it into a new method, and edit that line to make small changes. This approach works, but it's generally a bad idea. Why? Well, for one thing, copy and paste is error-prone. You might forget to change some things that you need to. Even worse, if you find a bug in your original implementation after you have made copies, you need to go fix every copy you made. It is also tedious. You have to go find the method, copy and paste it, and change it. This may not be so bad if you want one variation, but if you want to do 5 different things, it's pretty boring. And finally, it indicates bad programming design choices. Whenever you find yourself wanting to copy and paste, there's almost always a better approach. Let's take a moment to see something that we could improve about this algorithm. Why it would make a lot of work if we leave it as is and copy, paste, change, and then we'll understand the motivation for how to fix it. This is our algorithm to print all the genes in a string. We're going to condense it down to a small description at the bottom, and then copy and paste it and change line 5 to print only the genes with a high CG ratio. And then we'll condense that down to a short description. Now we're going to copy, paste, and edit to make several other algorithms to do various things with the genes from our DNA string, like printing genes in HTML, writing genes to an output file, counting genes with the codon CGA, or whatever else you want to do. All of these algorithms are the same except for the details of what they do to the DNA string. So at first, copying and pasting does not seem like a big deal. Later, we end up with some other DNA data which list all of the genes in a file, 1 gene per line. We need to do the same sorts of operations on this data too, but the algorithm will be slightly different. It will have a for each line in the file loop. Then do the same operations for the genes. With our copy and paste approach, we now need to write and test 6 algorithms. They are pretty similar to each other, so it may not be so hard, but it's tedious, error-prone work. Then if we end up with some other source of data, we're going to have to go make all 6 algorithms again for that data source. Likewise, if we end up with a new operation that we need to do, we're going to have to write 3 copies of it, 1 for each data source. Ick! What a mess! What we would really like to do is redesign our algorithm to use separation of concerns. Our initial algorithm does 2 tasks. One is getting all the genes from some source of data, and the other is printing them, or whatever else we want to do to each of them. We would like to split these up by having the algorithms that find the genes put them into some structure that can hold a list of all the genes. Then having the algorithms that print the genes, count the genes, or whatever else we want to do to the genes, they should operate on that list. Now, if you need to add some new source of data, you just write a way to get its genes into our list, and it automatically works with every processing algorithm you already wrote. Likewise, if you need to write a new processing algorithm, it automatically works with every source of data that you already wrote. No copying and pasting is ever needed. So what is this thing that can hold all the genes your algorithms find? We're going to start by using a class from the edu.duke package called storage resource, which is a simplified way of doing this. Later on, once you have learned a few more concepts, you will transition to using the standard java.util.arraylist class, which has similar functionality, but it's a lot more complex. Thank you.
Okay, now you've learned that you want to store your data in a list so you can separate concerns. You learned you'll start out with our edu.duke.storageResource class, which is a simplified way of doing this. What exactly is a storage resource and how do you use it? It's a class that holds a collection of strings. You can call .add to put a string into the storage resource. You can also use .data to get an iterable, so you can iterate over all the strings that have been put into the storage resource you created. There are a few more methods, and you can read about them in the DukeLearnToProgram.com website, where there's a document page for the storage resource class. Let's look at an example of using it. First, we're going to declare a variable SR of type storage resource. Once we've declared the variable SR of type storage resource and initialized it to a new storage resource, we'll see that it's empty. Then we might add a string, such as hello. Then we might add another string, such as world. And then we could iterate over all the strings in the storage resource by writing a for each loop and using sr.data. Let's see what happens when we step through this code. The first line declares a variable, so we'll make a box for it labeled SR, and then calling new creates a new storage resource. It's going to be an empty list of strings, which the SR variable will refer to. we'll add the string hello to the storage resource's list of strings. Similarly, sr.addWorld will add world to the list. Now we're at the for each loop. We're iterating over sr.data. So we'll make a variable we're going to use to iterate and have it refer to the first item in the storage resource object we created. By referring to the first item in the storage resource object, we'll be able to print it. Here it refers to the first item in the storage resource, the string hello. Inside the body of the loop, we print out s, so we print that. Then we go back to the beginning of the loop and refer to the next string in the list, in this case world. So we print world as we enter the loop. Once we've reached the end of the loop, we go back to the beginning of the loop and see that there are no more strings in the list. So we'll go past the loop and we're done iterating over the elements of SR. If you want to learn more about other methods in storage resource, or you forgot about the details of the ones we discussed here, you can find the documentation for this class on DukeLearnToProgram.com. Finally, let's see what our algorithm would look like to find all the genes and put them into a storage resource. It's pretty much what you had before, as we show here, except we've made 3 changes. First, at the beginning of the algorithm, we make an empty storage resource to put the strings we find, the genes, in. After making the empty resource, we do something to each gene we found. We add it to the storage resource. Finally, at the end, we give an answer. We use the storage resource with all the genes in it. Rather than printing them out, this method will return a value to whatever code called it. So the caller can use the storage resource and the data inside it for whatever purpose they want. That could be to print it, or it could be to process that data further. Have fun with storage resource.
All right, so you've learned that what you would like to do now is separate finding the genes from printing the genes. And the way we're going to do this is we're going to take all the genes you find and put them in a storage resource. And then you can iterate over that storage resource and print them out. Or if you wanted to do other things with the genes once you've found them, filter them, calculate properties about them, whatever, you could iterate over the storage resource and do those without reduplicating all of your code to have another thing that finds them all. So I've taken our code that prints all the genes, which we developed in a previous video, and I've made a couple small changes to it. So I changed it from being called print all genes to get all genes, since we're going to get them instead of print them. It returns a storage resource now, because that's what it's going to give back as its answer, one of these things that holds all of these strings. I've altered the comments here with the steps to the ones that we developed in the previous video where we came up with the algorithm. And where these have been the same as before, which is most of the steps, I've left that code. For one of these, where we were previously printing it and are now adding it to a list, I deleted the old code, the system out print line, which we don't want. But otherwise, this is pretty much the same. And then in our test methods, I've removed that code because we're going to have to do something a little bit different. So let's start by turning these steps into code. The first thing we want to do is create an empty storage resource and call it GeneList. So GeneList is going to be a new variable. We need to declare that its type is storage resource. GeneList is its name. And it's going to be an empty storage resource, a new one with nothing in it. So it's going to be a new storage resource. And then these steps are already translated to code until we get down here to where we want to take that gene and add it to our gene list. So that's just going to be GeneList.add and that gene. And then at the end here, our answer is GeneList. As you've seen many times by now, when your method or function knows its answer, it returns that answer to whoever called it. Okay? So now I want to write my method that's going to test this. And we're going to test it by printing things out. So the behavior of our code is going to be just what we did before, but it's going to be more useful, more reusable. We could put it to other purposes than just printing out these genes. So the first thing I want to do is call this method getAllGenes that we just finished writing. and store its result in a storage resource variable. Store, which I'm not sure I can spell. We'll just call this genes equals get all genes on that DNA. Now we want to iterate over the things in it. So I have here the Duke Learn to Program documentation because I'm not very familiar with storage resource. It's not one of the standard Java classes. It's kind of a nice simplification for you. If I didn't remember how to iterate over all of these things, I could look at this and say, okay, add, we just use that, size, .data returns an iterable. Those are the things that we can write for each loops. It even gives us this little example here. So what we're going to do is for all of the strings, all of the genes, which are strings in these genes we just got back, we want to print that particular gene out. I'm going to hit compile. Whoops. Up here, this was called current gene. Java is fussing at me because it has no variable there called just gene. Fix that. And here, whoops, I looked up the method and then I forgot to call it. That was good. Easy to fix. I'm going to get rid of this documentation. I'm going to come over here and I'm going to make a new one of these. And then I'm going to run it. And it ran just fine and gave me the same results as before, but our code is now more reusable. We could put it to other purposes more easily. Hello, and welcome to this introduction to using Java to help find trends, patterns, and make conclusion about information found in data. You see here 2 screenshots of spreadsheet programs that have been used to analyze data over many, many years. On the left is a screenshot of a Google Docs spreadsheet that you can use today. This program analyzes data and runs in the cloud. It is accessible via a browser or a mobile app on all kinds of devices all over the world. On the right is a screenshot of VisiCalc, the first spreadsheet program that launched in 1979 and ran only on Apple II computers. In general, spreadsheet programs work on data formatted in rows and columns, tabular data. You'll be able to write Java code to analyze such data as well. Spreadsheets revolutionized so many industries and launched new ones by taking seconds to model what-if scenarios that had previously taken days to perform. The link here is to a podcast describing the development of VisiCalc and the industries that were transformed by these programs. Today, data that can be analyzed by software programs is often made publicly available through government and nonprofit websites. Typically, data is produced in CSV files, files in which the different data values in each row are separated by commas, thus the name comma-separated values. You're going to learn how to write Java programs to analyze data stored in CSV format. Using spreadsheet software is a great way of finding patterns, information, trends, and visualizing data. But sometimes a spreadsheet program isn't enough to solve every problem easily. There are many different spreadsheet programs, so a common format is useful. The CSV format makes it possible for data to be portable between different types of software used to analyze data. Furthermore, you can write your own Java programs to analyze data using the CSV format. Common formats often have standards. For example, the Internet Protocol, or IP standard, determines the format for the packets that transport information across the Internet. The IETF, or Internet Engineering Task Force, that made the IP standard also created a standard for CSV files. Other groups have made different but related standards for formats used in different software programs. In this lesson, you will learn how to use an open source software library, the Apache CSV parser, as you learn more about Java programming. This software library will allow you to solve problems that would be really difficult to solve using just a spreadsheet. Let's get started with this.
Hi. The code you're about to see will show you how to access a comma-separated values file named foods.csv using Java. To better understand that program, here are 3 views of the data in the foods.csv file. The file itself looks like this, with the first row having labels used for each column. This is the header row. you can see the labels for each column of data. And you can see the data in each row is separated by commas. Here's the view using the spreadsheet program Microsoft Excel. Some of you may have used this program before. The Google Sheets program that runs in a web browser is free software that also allows you to manipulate spreadsheets. Here's the view of foods.csv from that program. You can see the first column has the label name, the second column has the label favorite food, and the third column has the label favorite color. Let's get coding. I'm going to walk through a simple example of using the CSV libraries that we have in our course so that you can understand how to create a CSV parser and how to use it in the most basic ways. More complex ways will be something that you learn in later parts of this course and that you can read about when you study the API. So I have a simple first CSV example. I'm going to open up the code so that we can see a few things, but rather than studying it in detail right now, I'm going to run it very quickly so that we can understand how it works, and then we're going to walk through each piece and make one small modification. So my class is already compiled. I can see that because there's nothing shaded here. I'm going to right-click and create a new object on the object workbench. I already have one, now I have two. I'm going to read the food from that. That pops up a file dialog. This is an example of our directory resource, and I choose foods.csv, a CSV file, and the program comes in and reads and prints Drew, Owen, Susan, and Robert. So I'd like to try to understand why it's printing those names, and then see if we can find some more information in this CSV file other than just our names. Looking at the source code again, I'm going to notice a few things. First, I've imported the edu.duke libraries, which is common in many of the examples we do. Because I'm using the CSV parser, I need one more import, and that's a very complicated one, but kind of something that you'll just be able to cut and paste over a while. org.apache.commons.csv. We're using an open source library for our CSV parser, and we've made it a little more convenient to use in a way that I'll explain. I have one method, readFood. I've created a file resource object that's using our standard library. Because it has no parameters, the file resource object will pop up a dialog and allow me to navigate to the file I want to use. I just showed you using foods.csv. Then I ask the file resource object, fr, to give me the parser, getCSVParser. This is the new class, the CSV parser class, that's part of my Apache library that you can see highlighted on the screen. I now loop over the iterable, that is the parser, getting a CSV record each time. So I have two new classes here, the CSV parser class and the CSV record class. The CSV record class has one method that I'm using, get, and that allows me to get one of the records on the line of that CSV file. As you may remember, CSV files consist of several elements of data separated by commas. One of the elements is named name in this case. Since I've studied the CSV file, I know that one of the other elements is named favorite food. So if I ask the record to get me the field, the element that's favorite food, that will do it. I'm going to print this one with just a space after it. So notice I've changed the print lin to just print. That stays on the same line. Print lin will finish the line. I'll show you how that output works. My class is compiled, no errors. I'm going to create a new object on the workbench by right-clicking, which is what I normally do here. So I'll select, right-click, create a new one. And then on the object workbench, I'm going to read, navigate to the foods.csv file, and notice, now I have Drew's favorite fruit is chocolate, Owen, its favorite fruit is pineapple, Susan really likes cake, and Robert likes pizza. One more example. It turns out that in addition to favorite foods, in this CSV file, there's also a favorite color. So I'm going to print the favorite color. We'll look at those briefly, and then we'll review finally. So favorite color, and I should put a space at the end of that line so it's easier to read. I'll compile that. When I create the new object, it appears on my object workbench. I'll run that, navigate to the foods.csv file, And lo and behold, Drew's favorite color is green. Surprisingly, Robert's favorite color is green too. If you're a very astute observer of the courses that we've done so far, that might make sense to you. Susan loves purple and I like blue. That is running through. Let me review one more time. In this CSV file that this program read, there are 3 fields: name, favorite color, and favorite food. If you tried to get another field, so for example, I decided to say that my favorite number was get favorite number, so I'll say get favorite number. That will compile, and when I try to run this example by making a new object and running by right-clicking, sometimes I can't right-click too well, open foods.csv, and I've got all kinds of illegal arguments except for favorite number not found. My CSV file does not have a favorite number field, and so I could not open that. When we study this in more detail and when you read the API, you'll see that there are ways that you can avoid trying to access CSV elements that don't exist. But for right now, we've seen use a library appropriately, that's org.apache.commons.csv, get the CSV parser from a file resource object, and then loop over the parser, which is an iterable, to get records one at a time. Have fun with CSV and finding information from data.
Welcome back. Now that you know a little bit about the basics of working with CSV files, it is time for you to solve a problem using them. Here we have a CSV file which shows export data for 218 countries. The columns are the country name, the main exports, and the total value of their exports in 2014 in US dollars. A problem you might want to solve with this data is to find which countries export a particular item. For example, you might want to print all of the countries which export lobsters, or all of the countries which export iron. There's a lot of data in this file. Way too much to look at by hand, which would be tedious and error-prone. Instead, you would rather write a program to perform this analysis for you. As always, we will walk through how you write such a program using the 7 steps. Step 1 is to work a small instance of the problem by hand. Here, we've cut the table down to 4 countries and only listed a few exports for each of them. Which of these countries exports coffee? After looking at the table for a few seconds, you can see that Madagascar and Malawi export coffee, and Macedonia and Malaysia do not. Next, you need to write down what you just did. If you just say, I just looked at it and saw the answer, that will not help for step 3. Instead, you need to think through what you did in a more step-by-step fashion. How did you look at the table and see the answer? You probably looked at the first row's export column and saw that it did not contain coffee. Next, you looked at the second row's export column and saw that it contains coffee. So you wrote down Madagascar. Next, you looked at the third row's export column and saw that it also contains coffee. So you wrote down Malawi. Finally, you looked at the fourth row's exports column and saw that it did not contain coffee. Thinking through this in a step-by-step fashion leads to these 10 steps for this particular instance of the problem. Now we are ready to look for patterns and generalize. Notice how you are doing very similar things for each row. This similarity suggests you will eventually want to loop over each row. However, there are some differences in the steps for each row that you need to think through before you can express this algorithm in terms of for each row. The first difference you might notice is that on line 5 you wrote down Madagascar, and on line 8 you wrote down Malawi. Where did these particular words come from? They are the value of the country column for the row you are looking at. The next difference you might notice is that you do not write down the country for the first and fourth rows, but you do write it down for the second and third. How did you know whether to write the country down or not? You made this choice based on whether or not the row contained coffee in the exports column. Now that you have figured out how to operate on each row in the same way, you can write down the generalized steps in terms of for each row in the CSV file, generalizing over how many rows the file has. Now that you have a general algorithm to solve this problem, it is time to test it out. Here is a table of data which contains 2 countries. Use the algorithm to find out which ones export lobster. Is this algorithm correct? According to our algorithm, Brazil is the country which exports lobster. Oops, that's not correct. We should have gotten Anguilla. Did you test the algorithm carefully enough to notice this mistake? The problem is that our algorithm always checks for coffee, not for whatever export we are interested in. We should have thought this through as we generalized, but we missed doing that. This is exactly the sort of problem step 4, testing your algorithm, is intended to catch before you write code. You can fix this algorithm by referring to the parameter, we'll call it export of interest, which indicates which export you want to look for. Making this correction to the algorithm will have it yield the right answer on this test case. Now that you have an algorithm, it's time to write the code. Okay, now that we've developed our algorithm to figure out which countries export a particular item, it's time to turn that algorithm into code. I'm here in BlueJ, where we've created a class and imported edu.duke.star, which you've used for many things, and org.apache.commons.csv.star, which you've learned recently is what you need for the CSV parser class. I've written a method here, list exporters, which takes in a CSV parser, so that's going to be the CSV parser that's already open for the file you want, and a string for the export of interest, and I've written down comments here for the algorithm we just devised. So the first step in our algorithm, which has a slight typo in it, said for each row in the CSV file, you've already learned that that's for CSV record is the type of item that you iterate over in the CSV file, and we'll call it record from the parser. And I'm going to put curly braces around all of the steps that go inside of there. And then we said, look at the exports column. You learned before, I'm just going to call that exports. This is record.get and the name of the column you want, in this case, exports. Check if it contains export of interest. So now we need to check and see if this string export contains export of interest. One way we could do that, which you've seen before, is export.index of export of interest is not equal to -1. Now if you were to look in the Java String API, you could see that there's a little bit more readable and convenient way to do this with a method that just is called contains. These two will do the same thing, it's just a little more clear to someone reading the code what you're trying to do if you write contains instead of index of equals -1. I'm just going to put that back where it goes. And then we said, if so, write down the country from that row. So I need to first get the country, string country equals, and again, I'm going to use record.get country to get the country column from that row. And then if I want to write something down, I would print it out. Okay, and then my curly braces all match up. I'm just going to hit compile. It says it compiled with no syntax errors. Now, as with other things, making a CSV parser in the BlueJ object workbench is a little complicated. So we're just going to make a method here to help us test this, which is going to be who exports coffee. It's going to take no parameters, and it's going to tell us which countries export coffee from a particular data set. So I'm going to make a file resource, which you've seen many times before. And as you may recall, if I create a file resource without passing in any parameters, it will pop up a dialog to let me pick what I want to choose it from. And then I'm going to want to get the CSV parser out of that. That file resource has a way to give me a CSV parser which will parse that file data. And then I want to list exporters from that parser for coffee. And I'm going to compile this again. It tells me invalid method declaration, return type required. I forgot to tell it what type it returns. In this case, I don't want to return anything since I'm just printing things out. So I'm just going to write void there. And then I'm going to try to compile again. That compiled just fine. I'm going to come over here. And I'm going to make a new one of my objects. And I'm going to say who exports coffee. And then I have this export data.csv file, which is going to list a whole bunch of countries. Now, we're trying to test out our code. We don't know if this is correct. How would we know this? Well, we'd have to go through that entire CSV file and check, did we get everything that exports coffee? That would be really tedious and is the whole point of writing the program in the first place. So what we should and can do instead is write a much smaller file. Here's the one that we used in the slides. And we can test our code on that instead. So if I come back here and I do who exports on, this is export small.csv, it says Madagascar and Malawi, which we know is the right answer. So that gives us more confidence in our code, and we can be more certain that we got the correct answer on the larger file. So there's the code for that. And now you can do similar things yourself.
Okay, so now you know how to solve the problem of analyzing CSV data to find out which countries export a particular good. In this lesson, you learn the mechanics of using Apache's Commons CSV package, a library for working with CSV data, using the CSV parser and CSV record classes to operate on the data in CSV files. You devise an algorithm to analyze a CSV file and find out all the rows that meet a particular criteria. In this case, which ones export a specific good. But the same basic ideas would work for other criteria more generally. And, of course, you implemented it in Java, putting your newly gained knowledge of the CSV library to use.
Welcome back. Now that you know a bit about working with CSV files, it is time to learn how to analyze numerical data in those files. For example, here we have a CSV data file about the weather at the Raleigh-Durham Airport for January 1st, 2014. We have this data for every day in a couple years with one CSV file per day. Each row contains information about 1 hour of weather, and there are a variety of columns such as the temperature in Fahrenheit, the dew point, the humidity, etc. If you are studying weather patterns, you might want to analyze this data and ask a variety of questions. Of course, the techniques you will learn are applicable to other types of data too, so you may find them useful in a variety of other fields as well. One question you might want to ask is, what is the maximum temperature? That is, when is it hottest? If you were doing this just for the data on one particular day, you could just look. There are only 24 entries. Or use the max function in a spreadsheet. However, what would you do if you wanted to find the maximum temperature over many days, such as for an entire year? You certainly do not want to look through all of the data by hand, and importing 365 files into your spreadsheet would be quite tedious. For something like this, you would want to write a program to do the work for you. In this lesson, that is exactly the problem you will solve, finding the hottest day of the year. For the purposes of this example, we are going to say that the hottest day of the year is the one with the highest maximum temperature. A related but slightly different problem is to find the day with the highest average temperature. We're not going to walk through that problem, but you could certainly do it after this lesson. The plan to write this program is to start by learning about dealing with numerical data. The CSV parser will read the data as strings, which have to be converted to numbers. Once you know how to convert strings to numbers, we'll start with a smaller piece of the problem, just finding the maximum temperature on one day. We'll walk through the algorithm and the code development with you. You will want to test your code to be confident that it is correct before proceeding. Once you are confident in your code to find the maximum temperature on one day, you'll want to build on it and find the maximum temperature for many days. This will let you find the maximum temperature in a year. So let's get started.
Welcome back. As you work with data in CSV files, you may encounter numerical data, such as this. Here we have a variety of numbers, such as years. However, the libraries you use to read a CSV file will read this data in as a string, the sequence of characters 1493, not the integer 1493. If you want to manipulate this data numerically, adding values, finding the largest, or some other task, you will want to work with the data as an int or a double. So what would happen if you tried to write a line of code like this? Int value equals row.getYear. When you try to compile it, you would get an error message here that the types are incompatible. You are trying to assign a string to an int. Let us look a bit more at this error. If you look at the documentation for the CSV reader, which we show here, you will see information about the get method. In particular, you can see that its return type is string. Because that method returns a string, this entire expression, row.getYear, has type string. Java knows that it will be a sequence of characters. However, that is not the same type as int, which is the type we declared value to be. This raises two questions we will answer for you. First, why is this a problem? Sometimes Java can automatically convert between two types, so why can't it convert a string to an int? It seems like if we have the string 1493, Java could just figure out that that should be the number 1493. However, it cannot do this in this case. The second question is, of course, how do you fix it? To see why Java cannot automatically convert a string to an int, consider what would happen if the string did not have numerical digits in it. For example, suppose our CSV reader read the string hello instead. What would you expect Java to do for this line of code? The rules of Java require the compiler to reject this line of code because there is no guarantee that you can meaningfully turn any string into a number. Another consideration is that the string 1493 has a very different representation from the number 1493. Even though everything is a number, the type of a piece of data describes how that number is represented and interpreted. We will not delve into the details of the representational differences here, but it takes some work to convert between the two. Accordingly, we would have to execute some code to perform the conversion algorithm. Such an algorithm would examine the digits in the string and compute the integer that they represent. We are not going to write this algorithm ourselves because it's already built into Java. You can just call integer.parseInt to convert a string to a number. Even though it's built in, you still have to call it explicitly to tell Java that that is what you want to do. Here you can see an example of how you can use the integer.parseInt method. You pass in the string you want to convert, and it returns the integer value. If you need to work with numbers that have fractional parts, you can use double.parseDouble, which will accept a string like 42.56 and convert it into the corresponding value of type double, the type to use to work with non-integer numbers. For either of these methods, the string could be invalid. It could be something that does not represent a number. For example, if you passed hello to integer.parseInt, the method cannot turn hello into an integer. So what happens? The method throws an exception, which indicates that an error has occurred. If your program throws an exception, then it will crash. There are ways to make your program handle the exceptions, specifying what to do instead of crashing. But we are not going to go into that more advanced topic here. So now you know that you cannot just assign a string to an int, and that if you need to convert a string to an int, you should use integer.parseInt. Likewise, for real numbers, you have learned to use double.parseDouble. Now you are ready to manipulate CSV data with numbers in it. Thank you.
Welcome back. The first piece of solving the problem of finding the highest temperature in a year, which has its data spread across hundreds of files, is to find the maximum temperature in one day, which always has one file. As always, we're going to start by working a small example by hand in a step-by-step fashion. Here we have 6 rows of data to work with. The first thing you might do is look at the first row, and in particular at its temperature, which is 30 degrees Fahrenheit. That is the maximum we have seen so far, which you will want to keep track of. If you were just working this out with a small data set, you might just remember it in your head, but we will draw a red box around it to be explicit. You might then go through the rest of the data in a similar fashion, looking at each row and deciding whether it is the largest you have seen so far or not. After you look through all the rows, you have found your answer, which in this data file is the last row. Okay, now that we have worked an instance of the problem by hand, it is time to write down exactly what we did in a step-by-step fashion. The first thing we did was look at the first row, in particular its temperature F column. Next, we noted that it has the largest temperature so far. The next step was to look at the second row. Its temperature is not greater than the largest temperature we have noted so far. Then we looked at the third row. Its temperature is 30.9, which is larger than the largest we have seen so far. So we updated our largest so far to be the third row. For the fourth row, we did very similar steps. Saw that 32 was larger than the largest so far, and updated our largest so far. The fifth row was not larger than the largest so far. And the sixth row was larger than the largest so far. So we updated our note of what was the largest. That was the last row. So we are ready to give the answer. In this case, the sixth row was our answer. Now that we have all of those steps written down for this particular instance of the problem, we are ready to find patterns and generalize. The first thing you might notice is that you are doing similar but not quite the same things for each row of the CSV file. As you can probably guess by now, you will eventually write code which loops over the rows to solve this problem. However, before you can do that, you need to think about the differences and find ways to make them the same. The first difference you might notice is that for the first row, we just noted that it was the largest so far. But for later rows, we compared the row to what we had previously noted down as our largest so far. The first row is a bit unusual here because we have nothing else to compare it to. We did something implicit that we did not write down. We check if our largest so far was nothing or something first. We'll need to incorporate that into our generalized steps. The other difference you might notice is that sometimes we updated what we recorded as the largest so far, while other times we did not. We marked the first row's update in purple, as we just discussed how it is different from the others, and marked the steps in red where we did not update the largest so far, and in green where we did. What is the pattern? It is when the current row's temperature is higher than the largest so far's temperature. Thinking through these patterns leads us to the following thoughts on how to decide when to update the largest so far. If the largest so far is nothing, meaning we don't have one yet, then the current row is the largest so far. Otherwise, if the row's temperature is greater than the largest so far's temperature, then the current row is the largest so far. After thinking through that, we can express our algorithms in terms of for each row in the CSV file. For each row, which we will call current row, you will want to decide how to update the largest so far variable, as we have just discussed. We have not said anything about what largest so far starts as, so we should be sure to put that in here. We mentally glossed over this while we were writing down our steps, but we implicitly started with it as nothing before we began looking at each row. We should write that down in our algorithm here. The last step, which we did write down, was to give our sixth row as our answer after we finished looking at each row. Is the answer always going to be the sixth row? No. It is always going to be the largest so far, the row that we have been keeping track of as we worked through the data. We should test this out before we try to write our code. Try it out on these 4 rows of data. Does the algorithm give the right answer? Yes, it does. We are now more confident that we wrote our algorithm correctly, so we are ready to turn it into code. In writing the algorithm to find the maximum temperature in a CSV file, we wrote down steps that do not correspond to anything you know yet in Java. The idea of having nothing. How do you turn that into code? This introduces an important new concept in Java, null. In Java and many other programming languages, null means nothing or no object. This concept is very important as it is common for algorithms to need to refer to the value no such thing. One thing you can do with null is initialize a variable to it. For example, CSV record largest so far equals null means initialize largest so far to be no such thing. Another use of null is when an algorithm has an answer of it doesn't exist or there's no such thing. In that case, returning null from a method is an appropriate way to indicate that no such answer exists. You can also check if an expression is equal to null, which is quite useful in many algorithms. In the algorithm we are working on, you want to check if largest so far is nothing. That is, if it equals null. One thing you cannot do with something that is null is call a method on it. Since null means no such object, it does not make sense to try to call a method on no such thing. For example, this code is problematic, even though it compiles just fine. This second line will cause the program to crash when you run it. You would get an error message like this, which tells you what went wrong. The first thing about this error message is that it says exception, which generally means that something went wrong with your program. The last part tells you what kind of problem you had. Java-lang null pointer exception, in this case, means you tried to do something with null that needed an actual object. In this case, trying to call a method on it. While we are discussing null, remember that all expressions have types. You have previously learned that it is important to know the types of expressions as you write and think about code. This raises an important question. What type of thing is null? We wrote CSV record largest so far equals null and told you that was legal. So it might seem like the type of null is CSV record. But does that really make sense? Would Java be designed such that the type of nothing is a CSV record? Shouldn't we be able to have nothing for other types too? Java actually has a special null type. Unlike other types, you cannot write down the name of this type in your program. You cannot declare variables of this null type, nor can you make methods whose return type is this special type. The literal null is a special type, and this type can be converted into any object type. That is, Java will let you assign it to variables of any object type, return it from methods whose type is an object type, or compare it to any other type of object. You may have noticed that we just said any object type, not just any type. Java has two categories of types, primitives and objects. Primitive types cannot be null. You have seen 4 primitive types so far: int, double, char, and boolean. There are also 4 others you have not seen: byte, short, long, and float. These types are all built into Java, and they are just plain data. They do not have any methods associated with them, and they cannot be null. The other category is object type, which can be null. You have seen many object types so far: file resource, string, CSV record, and pixel, just to name a few. In general, anything with a method in it is an object type. Likewise, any class you write is an object type. There are some other differences between primitives and objects, but they're not relevant yet, so you will learn about them later. Now that we've developed the algorithm for finding the hottest hour, we're going to write the code. So I've already set up the class for us with the imports that we're used to having, and the class name, and the method that we're going to write is this hottest hour in file. And we've already started, we're going to start the process with the pseudocode that we've developed by the end of the last video. So at first it says start with the largest so far as nothing. So we now know that nothing in Java is represented as null, so I'm going to go ahead and set largest so far. I'm going to give it an initial value of null. So now it starts out with null as its initial value, and it's a CSV record, which is what we're planning to return. I'm then going to come down and it says for each row in the CSV file, and that again is our familiar pattern of iteration that we've been using throughout this course, and we're going to use the parser that's been passed in as the parameter as the CSV information that we're looping over in the iteration. And I'm going to go down to the bottom here and go ahead and close this loop so that, again, I sort of have the idea of what I'm going to do for each record as we iterate over it. Next, it says, if the largest so far is nothing. So this is the first time that we've seen it, and we're going to check to see if largest so far is null. And again, this is just like we saw in the last video. We're checking to see if the value was null. If it is, we're going to assume that the current temperature, the current record, is the hottest one. So we will call that current row, or we'll assign that largest so far gets current row. That's all we have to do for that if statement. We're just replacing it. Otherwise, and that means else in Java, I'm going to compare the two temperature values directly. That means I need to get those temperature values out of the record. I know that those values are going to be numbers, but I have a decision to make. Should they be integers, whole numbers, or should they be doubles, real numbers? That's right, they should be doubles. Because one of the temperatures was 30.9 in our example, and that's a real valued number, which is better represented as a double. So I'm going to set current temperature equal to the current row dot get of temperature F. But getting that value is going to give me a string, and what I really need is a number, so I need to convert that string from a string into a double. So I'll use double.parseDouble to make that happen. Then, because I need to do the exact same thing again, I'm just going to go ahead and paste that line, and I'm going to call this largest temp, and I'm going to get it from largest so far. And now I have two double values, and I can compare them directly. I'm going to check if the current temp is greater than the largest temp, and if it is, then I'm going to replace that value, the one in largest. So I'm going to say largest so far gets current row. So I've replaced it in the two cases that we had checks for, and I'm done with my pseudocode for inside the loops, and I'm going to move to the next line, which is outside the loop, and it said that largest so far is the answer, so I'm going to return largest so far. Now I'm going to compile my code just to make sure I haven't made any silly errors. It says no syntax errors, so now I'm ready to test my code. Let's take a quick look at how the data is organized on the file system and what an actual file looks like. So we have a data folder, and inside of that data folder it's organized into years, and then within each year we have a weather file for each day. So there's 365 or 6, depending on if it's leap year, of those files for each of the years. So that's how it looks on the file system. And then here's how an individual file looks. So in this case I've chosen January 1st, 2015 as the one that I'm going to test, the data file that I'm going to test. And you can see we've got the column information up top, and we've got the column data for each of those. And we have two files loaded up in a spreadsheet because CSV files are easily represented as spreadsheets. So this is a nice way to visualize them. The other method that I've already included in the CSV Max class is test hottest in day, so that we can test our code to make sure that it's right. The first line in there creates a file resource already set to January 1st, 2015. The second line calls our hottest hour in file method that we just wrote, passing it the parser that we created for that particular data set, and then that returns us the CSV record that is the largest one. And then we print out that hottest temperature and the time that it appeared at, just to see when that was. And that's going to give us a sense of whether or not our program is correct. So I'm going to compile our code, and I'm going to come over to the BlueJ environment and create a new CSV max object, and then call my test hottest day. And it says the hottest temperature was 51.1 at 2:51 p.m. And if I go over to my data file and I look at the temperatures, I see that they are in the 20s, in the 30s, 50, 51.1, back down to 50, back to the 40s, and 42.1. So indeed, the hottest temperature was 51.1, occurring at 2:51 p.m. Let's also check the 2nd of January, just to try it on a second data file to see how we're doing. So I'm going to come over and change that from January 1st to January 2nd. I'm going to recompile. I'm going to go ahead and create a new CSV max and call test hottest day. This time it thinks it was 54 at 12:51 p.m. And again, if I come over and I look at my temperature, I'm in the 40s. I'm now in the 50s, 51.1. I have 54s, and then back down to the 40s. You'll notice that there's actually 4 times when it was recorded as being 54 degrees, and we've recorded the first time that occurred, 12:51 p.m., as opposed to the last time that occurred, 3:51 p.m. So now that I've tested it on 2 separate files, and I've seen that it worked for those, I feel reasonably confident that my code is correct, but I encourage you to test it on more files and try it out on your own and see what you get. Now that we can find the hottest temperature on a single day, let's look over a range of days and find the hottest temperature over that range. For this, I've created a new method called hottest in many days that we'll use to do this calculation. And we'll be using a directory resource for this, which will allow us to select any number of files over at once to compare. As we've done for many examples, we'll create a file, and that will be what the directory resource returns when we say selected files. And we'll iterate over that. And now that we have that file, we'll use that to create a new file resource. And now that we have that file resource, we can actually we can call the hottest hour and file method that we created earlier with the CSV parser, just like we did in our test, actually. And so this code right here that we've already got in our test is exactly what we're going to do, but now we're going to do it inside of a loop so that we can do it as many times as needed. But instead of this one being the largest, this one is only going to be the current temperature, and we're going to have to compare that against the largest so far. So just like in the previous example, we're going to have to keep track of what we think is the largest one so far. So to do that, we will create a CSV record, largest so far. I'll even use the same name. And initially it will be nothing, so I'll set that to null. And then once I get I'm looking through the loop here, I'm going to check to see if the largest so far is empty, meaning we haven't assigned it yet. Then I will go ahead and reassign it to the current one that we just got. Otherwise, I'm going to have to compare the two of them again. And again, since this code is going to be very, very similar, I'm actually going to go ahead and literally copy and paste it from my previous implementation. And I'm going to get the current temp. Oh, I'd call that one current row. I like current row. I'm going to call this one current row as well, again, so that we have a similarity of names. And so I'm going to get the current temperature and save that as a double, current temp. I'm going to get the largest temperature out of largest so far. I'm going to compare them. If it's greater, I'm going to go ahead and replace it. And then I'm going to close my loop. And so now I've iterated over many days. The main difference is I've called hottest hour in file instead of calling it for a particular row in that day. And once again, largest so far is going to be my answer. So I'm going to return that at the end. I'm going to compile my code just to make sure that I didn't make any silly mistakes. And it compiles, so now let's go on to testing. For testing, once again, I've created a test method, test hottest in many days. In this case, I call the hottest in many days method. It takes no arguments, so there's nothing to pass, but it returns a CSV record, largest, for me to use. I've printed out that the hottest temperature was, and I've also printed out what day it was. I've changed the field that I get to date UTC from time EST, since it could be any day, and now I want some extra information. I want to know what day it actually occurred on. So I'm going to go ahead and compile this and come over to the BlueJ environment. I'm going to create a new CSV max object. I'm going to call the test hottest in many days, and I'm going to go ahead and choose the first 2 days from 2015 just to test, because I've tried those 2 times before, so I know that the hottest day for January 1st was 51.1 and the hottest for January 2nd was 54, so I would expect that the answer is 54 on January 2nd, and sure enough, that's what my answer is. Now that I have some confidence that it's working, I'm going to try it on a bigger data set. And so now I'm going to test for many days, and I'm going to see what it was like for the whole of the year 2014, which is the last year for which we have complete data. And now I'm going to go ahead and say open, and apparently that was 98.1 occurring on July 8th at 10:51 p.m. So now I feel somewhat confident that my code is working. I tried it on a small example, just 2 days, and then I scaled it up to try it on an entire year, something that would be very difficult for me to test by myself, but that smaller data set gave me some confidence that my larger data set was working correctly. Technically, my code is done, but I feel a little uncomfortable about the amount of duplicated code that occurred in both of the methods that I wrote. And I know that it was duplicated because I copied and pasted between the 2 methods. And in programming, that's not a good way to create your programs, because if you have a problem in that piece of code, it now appears multiple times and you have to try to fix it in all those different places. So what I'd like to do is I'd like to factor out that common code and put it in its own method, which here I've named getLargestOf2, so that I can reuse that code in all of my other methods. So the part that I copied and pasted was this if-else statement that appears both in the hottest of many days and in the hottest hour in a file. So I'm going to go ahead and cut that code from that method and put it into getLargestOf2, including at the end returning the largest so far, so that I have the right result. And I don't have to make any changes to the code, because in my particular case I had everything named the same. So both of them call the current one current row and the largest one largest so far, and largest so far should remain the same unless it's null or unless current temp is greater. So in those 2 cases I should update largest so far, but otherwise largest so far is the correct value. So that's what my method is going to look like. It's just going to be those 2, the if and the else statement, and a return of its own. And now I can use that here to say largest so far gets get largest of 2, and I'll pass it the current row and largest so far. That will do the work of my if else statement, store the result there. And likewise, I can now copy and paste this one line of code into hottest of many files and replace, again, that same if else with that one line. Sorry, I lost my place there for a moment. So I get the current row from the file, and I get the largest of the 2. And now let's go ahead and compile and make sure that I didn't misspell something by not capitalizing it. And then since I copied and pasted that, I have to fix it twice, which is exactly what I was warning you about earlier. And so now, hopefully, since I fixed both of those, it will compile. And now we have to go back and test it just to make sure that everything is correct. So I'm going to create a new CSV max, because even though I moved code around and it shouldn't have changed the functionality, I want to actually make sure that that's true. So I'm going to test the hottest of the day, and sure enough, it gives 54 for January 2nd of 2015. And I'm going to call get hottest in many days, and I'm going to go back and select those 2 days that we've been using for our tests, and sure enough, it still thinks it was 54 degrees. So with those tests, I feel good that the changes that I made in terms of moving code around didn't affect the functionality, but now I feel more confidence in my code because this large piece of code that was duplicated, now I've taken care of and it only appears in one place. So if I ever find a problem with that, I can go back and fix it just in that one place. Okay, so now you know how to solve the problem of finding the row with the maximum temperature in many CSV files. In this lesson, you learned how to convert strings to numbers with either integer.parseInt or double.parseDouble. You saw another example of breaking a larger problem into smaller problems as you first solved finding the maximum in one file, then built on that solution to find the maximum in many files. You learned how to devise and implement an algorithm to find the maximum element in a set of data. And you also learned about the concept of null, which is how you represent nothing or no such object in Java.
Hi everyone, I'm Susan Roger, and today we are going to make Java cookies. So we're going to start. We're going to start by putting in 2 sticks of butter, and that is a cup of butter. Next up, we're going to add in 1.5 cups of sugar. Now we're going to cream the butter and the sugar together. So I just kind of use the back of the spoon and press it down a lot. All right, we've got the butter and the sugar creamed together really well now. Next, we're going to add 2 large eggs. I'm just going to crack them. And I like to crack them into a cup first. We'll just pour them in there. And you stir it a lot until it's consistency like this. 1 teaspoon of vanilla extract. So you stir that up a lot. You could use a mixer if you want, but I just like using a spoon. Next, we're going to add 3 cups of all-purpose flour. There's 1, there's 2, and there's the 3rd cup of flour. And 1/2 teaspoon of salt, and 1/2 teaspoon of baking powder. At some point, you just have to get your fingers into it and squeeze it together with your hand. And then when it's forming big chunks of dough, you can make 3 dough balls like this. Here's the second one, and here's the third one. Then I get some plastic wrap, and then I wrap the 3 balls, and I'm going to freeze them for about an hour. You can also freeze them overnight. I need the dough to be a little bit harder in order to roll the cookies out. Now we're going to bake the cookies. So I have printed out the Java logo, and then I cut it out. We have the dough here, and I'm going to put down some flour, and then I'm going to also put a little bit of flour on my rolling pin. You might want to cut the dough in half. It might be easier to work with. I'm going to pick up the dough and I'm going to put it on the tray. All right, and then I take my cutout Java logo and I put it there, and I get a knife and I'm just going to cut it out. Here we go. A 3D cookie cutter would be a lot easier, but I used to make all my cookies this way before we had 3D cookie cutters. And then I just pick up the dough. Now I'm going to roll out more dough and make another cookie. That's 2 cookies. And that's 5 cookies. So we've got 5 Java cookies, and we're going to put them in the oven at 350 degrees, and we're going to bake the cookies for about 15 minutes. Ah, the cookies are ready. Let's get them out of the oven. Oh, they smell really good. There's one, and there are 5 Java cookies. We'll let them cool, and then we're going to decorate them. Now we're going to decorate the cookies. We want the cookies to look like this. I'm going to use white icing. Just get a knife, and I'm going to stir it up. I'm going to put a little bit of the white in here, and I'll use that to make red icing. And then I'm going to also put a little bit in this bowl to make blue icing. So now I'm going to make some red icing, and I use the Wilton icing colors. They're gels. I'm going to add a lot more red. You have to use a lot of red. Now that's a good red color. I'm going to make blue. So we'll use royal blue. And that's a pretty color blue. Now with the red and the blue icing, we're going to put them in a bag so that we can squeeze them out. Now if you don't have one of these, what you can do is you can get a plastic baggie, put your icing in there, and then just cut off the corner when you're ready to squeeze it out. And then I use a cup here, and then here's our blue icing. And the blue icing is ready to go. And now we'll do the red icing. And the red icing is ready to go. Now we're ready to ice the cookies, and we'll just get some white icing on it, and we'll just spread it out. And we've got 1 cookie ready to go. And that's 6 cookies. Now I'm going to add the blue icing. And I put the picture in front of me so I can kind of see what I'm doing. And we'll just put it on there. There's 1. All right, we're done with the blue now. So let's add the red. And we are now done with decorating the cookies. And I hope you have fun making your own Java cookies. And if you do, please send me a picture. It's been a couple of hours. There's our Java cookie. And the best part is getting to eat the cookie. These cookies are really good. I hope you enjoyed the video. The end. The cookies are all gone.
Hello, you're going to learn the background and coding needed for the mini project for this course. You're going to write programs to answer questions that are very hard to answer using a spreadsheet, but that you'll be able to approach in a straightforward way using the practices, skills, and libraries you've learned about in this course. You're going to answer the question, what's your name this year, given your name in the year you were born? In other words, what name this year has the same popularity rank as your name did the year you were born? You can answer this question for anyone's name, so you can use a friend's name, a singer you like, or anyone. These pictures we will be using to describe what you're going to be doing are taken from a website that offers something similar to what you'll be doing in this mini project. Suppose you are a female named Jennifer, born in 1994. Jennifer was the 21st most popular girl's name in 1994. So one task you'll need to do is write code to figure out a name's ranking for a given year. If you were Jennifer in 1994, what would your name be today? You'll discover via coding that Grace is the 21st most popular name today, where today is 2014, the most recent year for which we have data on names given to babies in the United States. So today your name would be Grace if you were born in 1994 and named Jennifer. But you can also see what your name would be in any given year. Here we see a summary showing your name in several different decades. Jennifer in 1994 would be Barbara in the 1970s. That means Barbara was the 21st most popular name in the decade of the 1970s when taken together. Because we have data for the United States going back to the 1880s, more than 130 years ago, we can determine your name going back a long time. Here we see that your name in the 1900s would be Sarah if you were Jennifer in 1994. You'll need to write programs to make conclusions about the names that we've outlined here, turning all that data into information. The US government releases baby name data every year. We've collected that data and made it available to you as part of this course. We would be excited to have your help to collect similar data for other countries in the world. We have data for males and females going back many years with a different data file for every year. The files share a naming convention, which is convenient when writing programs to open the files and read them. You'll leverage the common naming convention in writing code to access these hundreds of data files. The file contents are also similarly formatted. That will help you write more general code to solve these problems. We'll look briefly at the data file for 2014, the most recent data provided to you for use. The line numbers in the file are ordered by the number of babies with a given name, so that the most popular baby name comes first, then the second most popular, and so on. As you can see here, 20,799 babies were named Emma in 2014, making it the most popular female baby name that year. All the female names precede the male names in the data file. This means the most popular boy's name, which was Noah in 2014, with 19,144 boys named Noah, comes just after the girl names that the fewest girls have, which were Ziriona and Zariah in 2014. We'll walk through the high-level concepts for accessing data in one file, but you'll need to go through the full 7 steps to solve the problem we're asking you to address in this mini project. You'll use several classes from the edu.duke and org.apache.commons packages in developing your solution to this problem. For example, you'll need a file resource object to access the data in a file for a particular year. You'll need a CSV parser by calling getCSVParser method from the file resource class, making sure that you ask for a parser with no header row. Because there is no header row, you'll need to access the data in each record by indexing. The first data element with index 0 is the baby's name in the file. The gender of the baby is the second data element. Once you've got this, you'll be ready to start thinking about the problem and using our 7-step process to solve the entire problem. Have fun! Now that you've learned about the problem that you're going to be solving for your mini project, let's take a look at the data files and some code for working with those data files to get us started in working through the problem. For this first example, I'm just going to go ahead and print out some basic information about what's in the data file so that we can get to know it and make sure that we understand what's going on. So I'm first going to make a file resource, and I'm going to choose which file I want to go ahead and open. And then I'm going to create a CSV record. And I'm going to iterate over all of those records in the file by using the CSV parser that we've seen several times. But in a new twist, as we saw in our video, we're going to put the data value false when we create the CSV parser, and that means that this CSV file does not have a header row. In other words, the very first line of the file is actual data that we're going to be using instead of a header row. For each record that we iterate over, right now we're just going to print out the basic information about it in a nice format so that we can kind of read it and make sure. So I put spaces in between the names. And again, which is different than we've seen before, we're going to be accessing our information using numbers instead of names. And that's because, again, we don't have a header row, so that we're doing it by value, where 0 is the first one, and 1 is the second one, and 2 is going to be our third one, which is all of the fields that we're going to have in our data. So that's it for our first version of this program. We're going to compile it and run it on a data file that I've created that is meant to be a very simple example just to get us started. And you can see that Emma is the name right here. Emma's gender is female, and there were 500 girls named Emma born in this example. The second one, Olivia, female, 400 born, all the way down to Ava, who was the last ranked girl with 100 born. Noah is the first male born with 100 born, so he was the most babies born, so he's ranked number 1 in terms of male births, even though he appears as the 6th name in the file. So it's all females first, and then all males following that according to their rank. So 1, 2, 3, 4, 5 in our example file, 1, 2, 3, 4, 5 in our example file. So we have 5 girls and 5 boys. You can see the actual data file that I've created here in this spreadsheet where I've loaded the data up. And again, there are 5 females and 5 males. And this is what the data file would look like on a small scale so that we have some numbers we can test with. Here's an actual data file where this is for the births in the year 2014. And you can see that Emma, again, is the most popular, but with 20,799 births instead of the 500 that I made. In this particular example, I've gone ahead and calculated the totals just to give us a sense of how large this file is. And you can see from the total names, there are 33,044 different names in this file. That means there are 33,044 different lines in this file because each name occurs on a separate line. Of those, 19,067 are girls' names, so that means the first 19,067 lines in the file are the girls' names, and then the 19,068th name in the file is Noah, who is the highest ranked boy for this year, and he would be first of 13,977 boys' names that appear throughout the rest of the file. So we're going to be working for our examples with this small file right here, just so we can get a handle on it, because 19,000 and 33,000 are big numbers that I can't really work with and test very easily, but we're going to use these for our testing purposes. So just again as a simple little thing to try, we're going to go ahead and only print out the names if the number born is under a certain value. So I'm going to go ahead and create an integer from the string that we get back for the number born, and so that's going to be the second piece of information. And then I'm going to check if that number born is less than or equal to, say, 100, and then print out those names, only those names that are smaller than 100, and so let's see what those are going to be. So now when I compile it and run it with that same small data, I see that I get Ava, who was the last ranked girl, and all of the boys' names that were in there, because all of the boys' names had num born less than 100. Now that we've seen the basics of working with these files, let's go ahead and solve a real problem, calculating the total number of babies born, total number of boys and total number of girls. In this case, I've created a new method, total births, for us to work in. In this case, I'm taking a file resource instead of having us choose. That'll make it easier for us to test and work with later. But I'm still going to use the same basic idea that I used in the previous one of looping over, in the previous problem of looping over all of the CSV records in the file. And I'm still going to pass false because it has no header row. So now what we're going to do is we're going to check out the number that were born each time, but we want to add that to a running total of how many were born. So we're going to create a variable called total births, and we're going to add to that the number born at this iteration of the loop. The problem with writing this piece of code here is that we can't both declare a variable and add on to it for this iteration of the loop in the same line. So we have to declare the variable someplace else, and the right place to do that is at the top of the method before the loop is ever started with an initial value of 0, meaning we haven't seen any births, and then at each iteration through the loop we calculate the total number that was born, or add to the total births the number that were born for that particular name. And then at the end we're going to print out the total number of births to see and verify whether or not we got the right thing. So let's just, again, run our simple little function just to see if it's going to work. Now in this particular case, since we've been passed a file resource, we need to have a test method that allows us to choose which resource we're going to be using. We're not going to have a dialog box pop up this time because we already know what we want to work with. We've got that nice small example file that we're going to work with. So I've already put that information in there, and I've already called total births to make sure that we're going to be able to see our output. Since our code compiled, I'm going to go ahead and create a new instance and call test total bursts, and I get that the total bursts were 1,700. And again, if I look back at our example file, I'm adding 500 plus 400 plus 300 plus 200 plus 100 plus 100, 40, 30, 20, and 10. I've added all these numbers up. I don't trust myself to do math on the fly, so I've created in this spreadsheet, I've created a formula that will do the calculation for me, and it came up with the number 1,700 as well. So I feel pretty confident that this basic piece of code is doing what I want. Let's revisit this code and look at the total for total number of boys born and total number of girls born. In order to do that, we're going to have to divide up the children based on their gender. So the way that I'm going to do that is I'm going to check and see if the gender is a certain one. So I'm going to say if the current one dot get of 1, because again the second field is what represents the gender, and if that equals male, say for example, then I want to add to a total for the total boys. So equals the number born And otherwise, I want to add 1 to the total girls instead. Obviously, I need to create those variables, and again, on the assumption that only whole numbers of babies were born each time, I'm going to go ahead and make those ints, and I'm going to initialize all of the variables up here. And then again, I'm going to add a print statement down here to make sure that we're checking our information. I'm going to compile quickly to check that I didn't make any silly mistakes and try testing this again. And now I get 1700, 1500, and 200. 1700, 1500, and 200. So I think again that I feel somewhat confident that it seems to be working. But just to make sure, I'm going to try it on a larger data file. So instead of example small, I'm going to try it on the year 2014 and try running that one. And in that case, I get 3,670,151, 1,768,775, 1,901,376. I've done the same trick in my spreadsheet over here with letting it do the sums, and I see that I get the same numbers for total births, girls' births, and boys' births as what I calculated in my program. So again, I feel relatively confident that my solution is correct. In this code, an interesting question is, does it matter how the boys' and girls' names are organized in the file? That's right, it doesn't for this code. For this code, since we check the gender each time, I could have the boys' names first and then the girls', or I could even have the names interleaved. But in your files, all the girls' names are going to be first and all the boys' names are going to be second, and that's going to determine how you figure out what their ranking is. Since we weren't worried about ranking for this particular program, we didn't have to worry about that distinction, but you will in your code. Good luck with the mini project.
Welcome back. In this lesson, you're going to look at the problem of converting images to grayscale. This is an example of solving a real problem by writing two programs and combining them into a single program. Why might you want to convert an image to grayscale? There are several reasons. You may want to see how images would look if you print them in grayscale. Grayscale printing is much cheaper than color printing, and some publications require that all images be converted to grayscale. Or you might be planning to do some other, more complex image processing. That processing could be simplified or even sped up by working with grayscale images. If you just need to convert one image to grayscale, the easiest thing might be to use an image editing program you already know. You'd open the image, the one you want to convert, and then you'd use the program to create a grayscale copy. But what if you need to convert many images to grayscale? It can be quite tedious and time-consuming to open each image up, transform it to grayscale, and then save it. For a few images, this may not be a big problem. But what if you need to operate on 1,000 images? It would take days to do this by hand, if you could even make yourself complete this repetitive task over and over and over. Instead, you could write a program to convert many images to grayscale. In particular, you might ask the user to select some group of images to convert. Perform the grayscale conversion on each of the selected images, and then save the results using file names which were similar. In our example, you'll add a gray dash prefix to the beginning of each image file name to distinguish the new grayscale copy from the original. This is exactly what we're going to work with you on in this lesson. In particular, we're going to break this large task down into a few smaller tasks. One aspect of the problem is to allow the user to select a group of files and to do something to each of the selected files. While you ultimately want to convert image files to a grayscale version, we'll start out by simply printing the selected file name, a small step toward the solution to the larger problem. Next, you'll work through how to convert one image to grayscale using our 7-step process. After that, you'll combine these first two ideas and programs into a single program that allows the user to select many files and converts each of these files to grayscale. Finally, you'll make your program save the results to new files with the appropriately named file names.
Welcome back. You're currently learning how to convert a bunch of images to grayscale. An important component of that process is the ability to convert one image to grayscale. In particular, you want to take a color image and produce an image that looks like it, but only uses shades of gray, not any colors. As with all programming problems, the way you want to approach this problem is with the 7-step approach you've learned previously. The first step is to work an instance by hand. As always, we must work with a small, manageable problem size. Here, we picked a 2x2 image to work with. We're going to want to make a 2x2 image for the output, but how do you figure out what shade of gray to use for this pixel? You need domain knowledge before you can proceed. In this particular problem, the knowledge you need is about colors or graphics. The first thing we need to know is what precisely is a shade of gray. A color is a shade of gray if its red, blue, and green components are all the same. However, this knowledge by itself is not sufficient to tell you how to come up with the shade of gray for a particular color. Just that the result needs to have the red, blue, and green all the same. One way you could do this is to average the red, green, and blue components. Or you might decide you want a weighted average because the human eye does not perceive all colors in the same way. There could be more complex alternatives. However, just taking the average works pretty well and is simple. Now you have the domain knowledge required to do this problem yourself. You can look at the RGB for a pixel, compute the average, and color in the output pixel appropriately. Then you would go through looking at the RGB values for each input pixel, computing their average, and coloring in the output pixel accordingly. Once you have colored in all of the pixels, you've worked an instance of the problem yourself and are done with step 1. The next thing you need to do is write down exactly what you just did. I started with the image I wanted, which we called inImage. Then I made another image of the same size, which we called outImage. I computed 255 plus 0 plus 0 divided by 3, which was 83, and I made the first pixel of outImage have red, green, and blue values of 83. And then I went through each other pixel, computing the average of the R, G, and B, and coloring the output pixel accordingly. Once we finished this, we had these 10 steps that we used to solve this particular instance of the problem. Now you are ready to move to step 3 and look for patterns and repetition. You can see that we are doing very similar things to each pixel, but they are not quite the same. We need to find the patterns in the number to generalize these steps to any image. Let us look at the particular numbers we need to generalize. Why did we use 255 here and 0 here? These numbers were all the corresponding pixel in inImage's red component. What about these numbers? Similarly, these were the green component of the corresponding pixel in inImage. Lastly, these numbers were the blue component of the corresponding pixel. Next, you should give a name to the result of this math. It won't always be these particular numbers, and you will want to be able to refer to it precisely. We'll call it average. Okay, now that we've thought that through, you can write the general algorithm. Notice how we thought about what we do for each pixel and wrote down general steps. Now we can write this in terms of steps to do to each pixel in the output image. It will work for any size image with any colors. The last thing you should do before you write code is to test your generalized algorithm out on another small input. Here is a small image and the RGB values for each pixel. Take a moment to execute the algorithm and see if you get the correct answer. Yes, the answer is right, so you're ready to implement it in code. Now that we've developed our algorithm to convert to grayscale, we're ready to write code. We've started here with a class for the grayscale converter, and we've already imported edu.duke.star. And before this video started, I went ahead and wrote in the steps that we came up with as comments in our code to guide us as we write. The first thing we did in our algorithm was we started with the image we wanted, inImage. In this case, that's going to be a parameter that we pass to our function so that this function can operate on any image we want. The next thing we did was we made a blank image of the same size as inImage. So if I want to make a new image, I'm going to declare an image resource. We called it outImage in our algorithm. And since I want to make a new thing, I'm going to say new. The type of thing I want to make is an image resource. And when I create this image resource, I need to pass in information, in this case telling it how big I want my image to be. This is going to be the width of inImage and the height of inImage. The next thing we did in our algorithm was we said we wanted to do something for each pixel in outImage. That's going to be a for loop, which you've seen before. Pixel in outImage.pixels. And we're going to put curly braces around all of the steps of our algorithm that we want to do for each pixel. And you can see that BlueJ put this all in pink so we can easily see that these all are going to happen for each pixel. In our algorithm, the next thing we did was we looked at the corresponding pixel in inImage. So what we're going to want to do is inImage.getPixel at the same location as pixel. So pixel.getX and pixel.getY. Now, when we do this, we need to give it a name so we can use it again. That's going to mean we're declaring another variable. So it's going to be inPixel equals inImage.getPixel. The next thing that we did was we said we wanted to compute inPixels red plus inPixels blue plus inPixels green, divide that by 3, and call the result average. So I want inPixels red, which is going to be inPixel.getRed, plus inPixels blue, inPixel.getBlue, plus inPixels green, inPixel.getGreen, and then I want to divide by 3. Now if I write divide by 3 here, I've made a small mistake because order of operations is going to make inPixel.getGreen divided by 3. I want to divide the whole thing by 3, so I need parentheses. And we want to call this average. We're declaring a new variable. What type is this variable? Well, it's going to be just a plain number, so int average equals all of that math. Now I want to set pixels red, so pixel.setRed to average, and similarly pixel.set green to average, and pixel.set blue to average. Those are all of the steps I wanted to do for each pixel. And then our last step at the bottom here says outImage is our answer. Whenever we know the answer to a function, we return that answer. So in this case, outImage is our answer. We just return outImage. So now I'm going to come up here and click compile. At the bottom it says class compiled, no syntax errors. You've frequently been testing your code by just making an object in the BlueJ main window and calling it its methods, but making an image resource there is a little bit tricky, so we're going to write another method to help us test this out. Public void, let's call it test gray, which is going to take no parameters. It's going to make an image resource, we'll call it IR, with new image resource. And that's going to pop up a dialog and ask us what image we want. And then we're going to make gray on this image resource. And then we're going to draw that. Now if we'd forgotten the name of the method we just wrote, we could scroll up and look, but I just remember it's called makeGray. I'm going to compile, again, no syntax errors. We obey the rules of the language. We don't yet know if our code works. Now I'm going to come over here to the main window. I'm going to hit New Grayscale Converter. It's going to give me this object in my BlueJ. Now I'm going to hit Test Gray. It's going to pop up a dialog asking me what image I want. I'm just going to choose these nice colorful Easter eggs. But when I run it through my grayscale converter, I get Easter eggs in gray. Since my code passed this test case, I'm more confident that it works. And in general, the more test cases we run, the more confident we'll be in our code's correctness. Having written the code to convert one image to grayscale, we'd like to go one step further and convert many images to grayscale. We've started here with the class we wrote in the previous video, in which we implemented our algorithm in code. I've added a method at the bottom, select and convert, which is going to let us select a bunch of files and convert them all. You've already seen this code before, which iterates over a selection of files and just prints out their name. Now we're going to combine these two ideas to give us code which is going to iterate over a bunch of files and convert them all to grayscale. So we're going to start with a very similar structure here. We're going to make a directory resource, which is going to be a new directory resource, and we're going to say for file f in directory resource dot. And if you don't remember this name, you can look at the API or look at the code we did before. It's going to be selected files. And what we did last time was we just printed out f. What we're going to do this time is we're going to convert the image corresponding to that file to grayscale. So I want an image resource in file, which is going to be a new image resource, and I'd like to create this from f. That is, make an image by reading in this file. Then I would like another image resource, which we're going to get by calling makeGray, the method we wrote before, passing in, I called it in file, but I'd really prefer to call it in image since it's actually an image. And then the last thing we're going to do is just draw this file so we can see something happening. So I'm going to compile this, and it told me it cannot find the symbol class file. What we need to do to use file is import java.io.star because that's the package in which files are. Now it compiles fine. And now I'm going to go back over here to my main BlueJ window. I'm going to make a new grayscale converter. And now I'm going to click on this and I'm going to choose select and convert. And it pops up this dialog. And if we navigate through here back to somewhere where there are images, we can now pick some selection of pictures that we would like to convert each of them to. And you can see that it went through and converted each of these pictures into grayscale and drew the resulting image. I think it's still converting one of them. The last one was really big. All right, so now we've put those two ideas together. We've converted any set of images you select. The next step is going to be to save these images to a file.
Welcome. Today what we're going to do is I'm going to show you how to make copies of images by writing a program to do so. I've got a file of images on my computer, and I'd like to actually read some of those images in and make copies of those files. So we're going to do that with a program. So I'm going to create a new class, and we'll call it Image Saver. And we'll go ahead and open the editor. And let's make it bigger. And what we'll do is we'll create a method in here called doSave. So and what we're going to do is we're going to use our directory resource that we learned about. So I'm going to create, if I can spell it right, I'll create a variable called dr of type directory resource. And I'll have to create a new directory resource. And then we will like to loop over and select files from there. So we'll create a for loop and a variable f, which is of type file. And we'll use the selected files method from the directory resource. And let's see what we're going to do with our files. So now what we're going to do is create an image resource. I'm going to create a variable type image resource called image. And that we will have to do create a new image resource. And we'll use the variable f that we read in our for loop. And I want to just make sure this works. So what I'm going to do now is just go ahead and have the image just draw. And so we'll just draw it on the screen and see if this works. All right. So let's see if this works. I'm going to try and compile it. And nope, I've got an error. So let's see what it is. So I forgot to put another curly brace. Whenever you get this reach end of file while parsing, and it's got this highlighted, so I'm going to try and add another curly brace. I need one for my method doSave. So let's put that in there. That looks better. And you can also tell the way the colors are lined up that I was missing that. So we'll compile it. Okay. So it's still not compiling because it doesn't know what directory resource is. So I have to import the edu.duke library, so I'll add that right here. Import edu.duke.star, and that should fix that error. So let's compile again. Now it can't find file, so I'm also going to have to import from the Java I/O library. And I'll just go ahead and specify that I want to import the file class. And let's see if that compiles. Yay, no syntax errors. Okay, so now we can come over here and we can actually run this and just see all this is going to do, hopefully if it works, is it will just display some images that I'm going to select. So we will go ahead and create a new image saver. And then we will go ahead and run our doSave method. Now I have to find on my computer where I've got some images, so I'm going to navigate to here. And I've got it on my desktop. I've got a folder of images. There it is. And now I can select several images. I'll just go ahead and select the dinos. And I'll select another one, Easter eggs. I could select as many as I wanted to. And I'll go ahead and open, and our program should just draw these images. And it did. We saw the two images, so that's great. That seemed to work. So I'll just get rid of those. And let's go back to our program now, and now what we would like to do, we know that we can get the images and we can display them, and so now what we'd like to do is we'd like to make a copy of them. So we're going to add some more code in here. And let's see. Okay, so now what we're going to do is, first what we have to do is we're going to get a file name from the image file that we have just grabbed. So I'm going to create a string for that file name, and we'll just call that fname. So the image, we can use the image resource method that is called getFileName. And if you didn't know about that, you can look in the documentation and you'll see all kinds of methods that you can use with the image class, image resource class. So just getFileName should get me a string. And then what we want to do is we want to create a new name, which is going to be like copy with the old name. So let's create another string variable. This will be called the new name. And it's going to be, make the string copy dash, and then we'll add that to the front of the file name, and the rest of the file name will be the old file name. So let's see, we will call this, fname is the old name. So we've created, all we've done so far, well, let's try and run this. Let's see if this works. So if I will just compile this, it compiled with no errors, so let's just run it. We'll come back over here. We will create a new image saver, and we'll come over here and run our doSave method. We can now go pick some files. We have to navigate over to the desktop where my images are in the images folder, and I can grab, let's see, dinos and Easter eggs again. There we go, and we open them, and we got them. And now I also have the images folder right here, so we can just look and see. We created a new name that was copy of, and if we look in the folder, I don't see any image that's called copy dinos. So we created a string, but we didn't actually use the string to create a new file yet. So let's do that. So we have the name, but now we need to use it. So we're going to actually, there's another method called setFileName. So let's use that. So we'll say image dot set file name. And what we want to set it to is this new string that we created. So let's do that. It's called new name. So that should do it. And now we also, what we didn't do is we didn't save the file. So we have drawn the file, but there's also a method in the image resource class called save. So let's do that too. We'll draw it and we'll save it. And that should save the new file. So let's run this and see if this works. We'll compile it. And then we will come over here and run the program. So we'll create a new image saver. And then we'll run our doSave method. We have to find some images. Okay, and so again, I'll just pick dinos and Easter eggs, and let's open them. Okay, so they're displaying again, but how do we know if it worked? Let's go look in the images folder, which is right here. And if you look in there, you'll see there are two new files in there. One is called copy dinos, and the other is called copy Easter eggs. So it looks like they copied them. Now let's see what happens if we run our program again and we select one of those, or both of those even. So let me get rid of these old images, and let's just run our program again. So I'm running the doSave method. I'm going to the desktop, picking some images to make copies of, and I'm just going to make a copy of copy dinos. And let's make a copy of copy Easter eggs, and we'll also make a copy of, let's see, Roger. All right, so we're going to make a copy of those three files, and let's see what happens. Okay, so we had all those pictures pop up, and we'll just get rid of them. And if we look over here in the images folder, let's see what we have. We have copy dinos, and we have copy Easter eggs, because we made copies of copies is what we did. And then we also made a copy of Roger, so we also see a copy Roger. So anyway, that's how you make a copy of an image, where we grab the file, we have to create a new file name, and then we save a copy of it with the new file name, but we have to give it a new name because there's already a file with that name. So we added copy dash onto the front of it. Hope you enjoyed that. Thanks.
Hi, we're now done with this lesson, in which you've written a Java program to convert many image files to grayscale, batch processing. During this lesson, you learned how it can be really useful to break a large problem down into smaller pieces, into smaller programs that you can then develop incrementally, making each program work and then putting the correct working programs together. You got more practice writing code which iterates over data. First, iterating over files that the user selected using the directory resource class. And then iterating over the pixels in an image, where you wrote code to actually convert an image to grayscale. Converting the image to grayscale gave you more practice in solving a programming problem using our 7-step method. Finally, you put the finishing touches on your batch grayscale conversion program by making it save the new images with file names that were similar to the old file names. This is a reasonably complicated program, and you should be proud of having made your way through this lesson.
This is Duke University.
Hi, I'm Susan, and I'm really excited to be working with our team at Duke to introduce this course, Java Programming, Arrays, Lists, and Structured Data. We've designed a great set of problems and programs that combine real-world data analytics with lessons that introduce security and cryptography. Whether this is your first course with our great team, or you're coming from our previous courses as part of Java Programming, an Introduction to Software Specialization, you'll use a 7-step process to help you design and implement Java programs to solve problems and hone the skills that will help you become an effective software engineer. In working on the problems we've designed, you'll learn about arrays and maps, 2 standard data structures that are used to create efficient and robust programs to solve problems. As part of our cryptography lesson, you'll learn how the words melon and cubed are related by the number 16.
Hello, I'm Drew. In this course, you'll be using the edu.duke library of classes we've designed to write programs that solve interesting problems, like analyzing weblogs and generating random stories from templates. But you'll also use the standard java.util library of classes that will help you grow your knowledge and skill in using Java to create solutions to these problems. Understanding APIs so you can use code from libraries is an important part of this course, as is beginning to develop an understanding of object-oriented programming. In this course, you'll learn how classes are structured and how programs are created by strategically combining classes together. You'll also learn about how the words fusion and layout are related by the number 20.
Hi, I'm Robert. For this course, we've designed an exciting mini project as part of this course to help you learn more about classes, object orientation, and data structures. You will use standard techniques and libraries that are part of nearly all Java programs designed to solve problems at scale. We've structured the module in this course to introduce topics and then explore them in more detail and with more robust, scalable solutions that improve upon an initial program. This allows you to learn the new techniques while solving a familiar problem. We hope that this learning approach will facilitate success for all learners. Also in this course, you'll learn how the number 19 connects the words jolly and cheer.
Hi, I'm Owen. I'm excited about the approach we've taken in this course to introduce 2 important programming structures, arrays and maps. These are not simply Java structures. They are used in every programming language to create efficient solutions to programming problems. By exploring how these structures are related and encountering them in familiar contexts, you'll be able to practice using them as you develop mastery with both concepts and the Java libraries that anchor these concepts in code. You'll also learn why having 14 fake toys would be an enormous cryptographic coincidence. Welcome to arrays, lists, and structured data.
Welcome back. Today, you're going to learn a little bit about security, which will show you the importance of the problems you're going to solve in this module. Suppose you want to buy something online. You use your computer, which is connected to the internet, so it can communicate with the servers at the online store from which you're making your purchases. To complete your purchase, you put your credit card or other payment information into your computer. When you purchase the items in your shopping cart, for example, your computer sends that information with your credit card information across the internet to the online store. But what if a thief is looking at the data going across the internet? This thief might be able to intercept your credit card information and use it to make fraudulent purchases. You certainly don't want that, and neither does the online store. It wants your business. So what makes online shopping safe? What actually happens is that your computer encrypts the information before it sends it to the web servers for the online store. The two computers agree on a special piece of data called the key, and then use that with an encryption algorithm to transform the data so that only another computer with the key can decrypt the data. Now your computer sends the encrypted data across the internet, and any potential thief is thwarted. The thief can only see the encrypted data and cannot understand what the message says. The receiving computer, which has the key, can then decrypt the data and understand the original message. When you are doing anything online, your web browser will tell you if you have a secure connection. For example, Chrome displays the HTTPS in green and shows a green lock icon next to it. The S in HTTPS is for secure. It's a different kind of connection to a web server than the standard HTTP. If you were to click on the lock icon, it would tell you the technical details of the encryption used to secure the connection. There are many algorithms involved in securing your internet connection. An algorithm called AES is typically used to encrypt the data that is sent to the server once the connection is set up. However, your computer and the server must agree on the key in a secure fashion before any information can be sent. While this may sound quite difficult, there are algorithms that can make this happen. In this example, my computer used two algorithms to securely set up the connection with the server. One called elliptic curve Diffie-Hellman and one called RSA. These algorithms are very important to the secure operation of the internet, but the math involved is a bit advanced to go into here. To implement these encryption algorithms, you would need to spend several days or months just learning that math, which is not the focus of this course. If you are interested in advanced cryptography, Coursera has some excellent courses on the subject, which you could take after you've mastered basic programming. Even though modern cryptography requires some advanced math, you can, however, learn a lot about cryptography by looking to the past. Classical cryptography, the cryptographic algorithms used in past centuries, involve simple mathematics and even predate computers. These algorithms are not secure today. They can be easily cracked by computers, but learning how they work and implementing them will teach you some important lessons. Furthermore, learning how to break them will teach you a critical lesson. Do not try to make up your own cryptographic scheme. If you need security, use a well-tested implementation of a modern cryptographic library. So how far into history will we need to look to find the first use of cryptography? The first known use of something resembling cryptography comes from ancient Egypt 4,000 years ago. However, historians believe that the hiding of messages was not a serious attempt to guard secrets. If you look forward a few hundred years to Mesopotamia, around 1500 BCE, you will find records of craftsmen using simple encryption schemes to guard their secrets when they recorded them on stone tablets. Going further forward to the Roman Empire, the Caesar cipher, which you will learn about in the rest of this module, is named after Julius Caesar, who used it extensively. Looking forward another 1500 years, you will find the Vigenère cipher. Giovan Battista Bellosa actually described this algorithm in 1553, but it is named after Blaise Vigenère in the 19th century. This algorithm is historically very important as it was long regarded as unbreakable. However, in the mini project, you're going to write a program to break it. Continuing forward to the 1940s, cryptography was a critical part of World War II. The Allies devoted significant resources to breaking the German codes, with the core of that effort taking place at Bletchley Park in England. Alan Turing was a leader in this code-breaking effort and made many important contributions to computer science. In fact, he is so important that the highest honor in computer science is called the Turing Award. So now that you know a bit about cryptographic history, what will you be doing? In this module, you're going to learn about the Caesar cipher. You will implement it and then break it. In the mini project at the end of this course, you're going to learn about the Vigenère cipher and will also implement it and break it. Of course, all of these problems are going to teach you several important skills that can help you solve a wide variety of other problems.
Welcome back. Now that you know a bit about the importance of cryptography, it is time for you to learn a bit more about the concepts of the Caesar cipher, which you will implement in this lesson. Suppose you were in a battle and you wanted to send a message to your sub-commanders to tell the 1st Legion to attack the east flank. You don't want your enemies to know your plan, even if they intercept this message. So you encrypt it with your cipher, as shown on the second line. The Caesar cipher algorithm is named for Julius Caesar, the famous Roman emperor who used it. The basic idea of this algorithm is to substitute each letter with the letter obtained by shifting the alphabet by a fixed amount, that is, a specific number of letters later in the alphabet. The amount you shift the alphabet by is the key for this cipher. Julius Caesar used a shift of 3 letters prior, which if you think of the algorithm in terms of shifting to a later letter, would be the same as 23 letters later. To see how this algorithm works, we'll walk through an example of encrypting this message. We'll use the alphabet to show how letters are encrypted. The first letter of the message is F. We find the letter F in the alphabet here, and then we go backwards 3 letters, E, D, C. So you would write down a C as the first letter of your message. The next letter is I. We find the letter I in the alphabet here, and then we go backwards 3 letters, H, G, F, writing down F as the next letter of the message. The next letter is R. We find the letter R in the alphabet here. Again, go backwards 3 letters, Q, P, O, writing down O as the next letter of the message. You would continue the same way through the first word, and then you would get to a space. Doing this by hand, as Caesar would have done, the easiest thing to do is leave the space unchanged and write down a space in your message. The next word and space proceed in the same way. However, what happens when you get to A? We find A here. It is the first letter in the alphabet, but how do you go 3 letters backwards? You have to wrap around to the end of the alphabet. From there, you go 3 letters backwards to Z, Y, X, writing down X as the next letter. You continue through the rest of the message in the same way and end up with something that is unintelligible under casual scrutiny. However, if you know or can figure out the key, you can decrypt the message. The process is the same as encrypting with a key of 26 minus n. So how do you actually do this? One way is to do math on the numbers. If you took our Coursera course, Programming and the Web for Beginners, you should remember that everything is a number. If you're not familiar with this concept, it is very important in computer science, as computers can only work with numbers. In this case, that principle says that these letters are actually represented as numbers, so you can do math on them. In particular, you could tell Java to subtract 3 from the letter F, and it would compute the letter C. However, what if you subtracted 3 from the letter A? Java would not know that you want to wrap around and stay only within the alphabet. So you would have to include some more mathematical operations or a conditional statement to wrap around and get X. Another way you could do this, which makes the wraparound case a bit cleaner, is to pre-shift the entire alphabet. That is, compute the shifts of each letter at the start before you try to encrypt anything in the message. For example, you could take the alphabet and for a shift of 3 to the left, compute a string like this one. We will see the details of how to do this in a future video. However, once you have computed these strings, you can use them to look up the encryption of each letter. For the F at the start of the message, you want to find F in the original alphabet. Think for a moment about what you have learned about strings in the past. What method might you use to find F? Once you have found F, you look at the letter in the same position in the shifted alphabet, which is C. Then you write down that letter in your encrypted message. For A, which wraps around the X, you do not have any special case. Again, you just find A in the original alphabet, look at the letter in the same position in the shifted alphabet, in this case that letter X, so you write down X in your encrypted message. Great. Now you know the basic ideas behind a Caesar cipher. However, before you implement this algorithm, you will need to learn a few new Java concepts. You're going to learn some new ways to manipulate strings, as well as for loops which count over a range of numbers. For loops which count over ranges of numbers are particularly important, as you will use the numbers you count to index into data, manipulating particular locations in a sequence. You are familiar with strings, which are sequences of characters, but we'll learn about the new types of sequences in the rest of this course, so you will use for loops a lot. Thank you.
Welcome back. Now that you know a little bit about how a Caesar cipher works, it is time to expand your Java knowledge so that you can implement one. You should know something about strings already. If you took our previous course, Java Programming, Solving Problems with Software, you learned how to manipulate strings. If you are unfamiliar with strings, we recommend you brush up on them before proceeding. However, to perform encryption, you need to do something with strings that you did not do in the previous course. In that course, you analyzed the contents of strings and operated on pieces of existing strings. However, you did not build up new strings. If you carefully re-examine what you saw about how a Caesar cipher works, you will see that you are making a new string by adding one character at a time. One way that you can build up a string is with concatenation, which is a fancy word for sticking things together. In Java, you can perform string concatenation with the plus operator, whenever at least one operand is a string. If one operand is a string, but the other is not, then the concatenation operator figures out the string representation of the non-string operand and concatenates that. For example, if you were to write these two strings with the plus operator between them, you would be telling Java to perform string concatenation. The result would be the string you see here, which was formed by sticking these strings together. Exactly what concatenation means. To illustrate the usefulness of this operation, think about the Caesar cipher you are working on. You might want to take the original alphabet as a string and make a rearranged alphabet based on the key. You could do that by taking two pieces with substring, which you are already familiar with, and concatenating them together. First, you would take the substring starting at 23. Remember that substring with only one argument returns the substring starting at the specified position and going all the way to the end of the string. Then you would concatenate the substring from 0 to 23 onto the end of that string. Now you have two strings which describe the mapping from each plain text letter to the appropriate ciphertext letter. We did this for the key of 23, but you should think for a moment about how you would generalize this for other keys. As you learn more about manipulating strings, it is important to know that they are immutable. You cannot change an existing string once it has been created. Instead, if you want a different string, you must make a new one with that change. This concept may seem a bit confusing and subtle, so it helps to see it with a picture. Here we have declared a string and initialized it to hello. Nothing new or surprising here. A common practice is to draw a picture of the effect of this statement by drawing a box for the variable s and making an arrow pointing to the letters that make up the string hello. If you declare another string x and initialize it with s, you would have a picture that looks like this. Both x and s refer to the same string. Now suppose you did s equals s plus space world. That is, you compute s concatenated with the string space world. You are not changing the existing string, but rather making another string, which involves copying the existing strings like this. Notice that x is still hello because you did not change the existing string. You made a different string and assigned it to s. If you do a lot of string concatenation operations, on large strings especially, the required copying can be quite slow and inefficient. Even though we are not terribly focused on the most efficient way to do things yet, it is still a good practice to develop good habits. If you are building large strings by adding many small pieces, you want to use a different approach. In fact, Java has a string builder class specifically for this purpose. It provides a mutable sequence of characters, meaning it is like a string, but you can modify it, changing and inserting characters in an efficient way. When you create a new string builder, you can pass a string in to specify its initial contents. There are also many useful methods. We will name just a few of the most important ones, but recommend you consult the API documentation for a full list and more details. One useful method is append, which lets you put a string on the end. You could also pass in other types of data which will be converted to a string before being added to the end. You can insert a string or the string representation of other types of data at any location you want. You can get or set individual characters by their index, the numerical location where they are in the sequence of characters. When you are done manipulating the string buffer, you will often want to use toString to get the string you have made. As before, it helps to see a picture of how these methods operate. Here we have started by creating a string builder and passing in the string hello. We have drawn this picture with SB having an arrow pointing to the sequence of characters in the string builder. Now, if you call sb.append and pass in world, you will modify the existing sequence of characters. Notice how we changed the existing sequence rather than copying them into a new sequence. You could also insert or put the characters into the middle, which would still modify the same sequence of characters like this. Great! Now you know how to build up strings from smaller pieces.
Hi. As you get ready to solve problems that are slightly more complex, you'll learn some new programming constructs to help. In this video, you'll learn about counting loops. You've used different kinds of loops in solving problems before. You used a while true loop in finding codons in DNA or tags in a web page. And you've used a for each loop with an iterable many times, as in reading lines in a file or processing pixels in an image. You've also used indexes to access and reference parts of a string. You know that indexes start with 0 in Java and with many other languages. So when you use .indexOf, you know it returns 0 when a match is found at the first character in a string. Both .indexOf and .substring use indexes to access the elements or characters of a string. We'll look at code to access individual characters in a string. We'll do this in the context of looking at the reverse of a string, where the reverse of CGATTA is ATTAGC, and the reverse of TIP, TIP, is PIT, PIT. Scientists studying genomes often have to look at a string backwards to analyze the DNA. It can also be a source of fun or wordplay to look at phrases that are palindromes, the same read backwards as forward. Here's a sentence in Russian that you can see reads backwards and forwards if you understand the Cyrillic alphabet. It means, the boar pressed the eggplant. In Spanish, we have a palindromic sentence that means, there jogs the tortilla. While in French, the sentence, et ça va la vache, means, and how is the cow? Finally, we see an English sentence, draw, O Caesar, erase a coward, which is particularly appropriate as we implement a Caesar cipher in this module. We'll use a new loop, the counting loop, to reverse a string. Indexing a string in a loop can be done in several ways, but we'll look at a very common approach. We must understand a loop with 3 parts. Each part is separated from the other parts by a semicolon, as you can see in the code on the slide. The first part of the loop is called the initialization. Here the variable k is assigned the value 0, and this happens once before the loop guard and the loop body are executed. The loop guard is evaluated each time before the loop block or body may be executed. When the loop guard is true, the body is executed, and when it's false, the loop executes. Sometimes the loop guard is called the loop test. The increment here happens after all the statements in the loop body are executed. After the increment, the loop guard is evaluated again to to see if the loop continues or exits. We'll look at this more closely. To understand the for loop, we'll compare it to the while loop that you've seen before, though not with this precise style of counting in a loop. The for loop does not provide more power than a while loop, or allow you to solve different problems. The for loop is simply syntactic sugar, or a dressing up of a while loop. The for loop puts all the parts in one place, and many programmers think this makes the loop easier to write and to read. As we've discussed, the initialization happens once before the loop guard is tested. You can see in the comparison here how initialization happens before the while loop too. The loop guard is evaluated to see if the loop body will execute. When the loop guard is false, the loop is over. Both the while and the for loop exit when this loop guard or test is false. When the guard is true, the loop body executes, and as the last statement in the body, we see the increment statement, which will execute. We'll trace through the execution of a for loop in a particular example of a reverse function to better understand the loop. And to trace this, we'll look at the call reverse pit. This means the value of parameter s is the string pit. The local variable r, or ret, will accumulate the reversed string. It's initialized to the empty string before the loop. As we trace through the code, the green arrow indicates the statement that will execute next. The loop index, or control variable k, is initialized to 0. Remember that the loop initialization only happens once in a for loop, and the variable k is only accessible within the loop, but not after the loop. Its scope is limited. When the loop guard is checked, the value of k, which is 0, is less than s.length, which is 3 since pit has 3 characters. The loop guard evaluates to true. Loop guards are always Boolean expressions. The loop body now executes, and the string method char@, acts as a character at a specific index. We should point out here, some people say char@, the way I do, and some people say char@. Either one is fine. Since k is 0, the expression s.char@0 evaluates to p. We've shown the character p with single quotes, which is used in Java to indicate the primitive type char. The value of ret is shown as the empty string in double quotes, because these double quotes in Java indicate a string literal. Concatenating the character p to the empty string yields a new string p. The variable ret will be assigned the value p. The string variable changes, and it's no longer pointing to the empty string as it used to. Remember that strings in Java are immutable. We can create new ones, but we can't change a string. The increment executes after the loop body. This changes k so that it has the value 1. After the increment statement, we're ready to trace the next iteration of the loop. The local variable ret has the value p. The loop control variable k has the value 1, and we're ready to continue the trace. K has the value 1. The length of s, the string pit, is 3, and so the loop body executes since the guard evaluates to true. Remember that the .char@ method accesses the kth character. Here that's the character I, whose index is 1. The character I is prepended via string concatenation to ret, which is p, and this creates a new string ip. The assignment statement changes ret so that it references this new string. And now the loop increment will execute. The value of k is 2, and the loop will continue to execute. We'll now trace through the last iteration of the loop. The local variable ret has the value ip. The loop variable k has the value 2, and as we can see here, the loop guard will be evaluated. Since 2 is less than 3, the guard is true, and the loop body executes. s.char@t evaluates to t, as you can see here. The character t is prepended to the string ip to form the string tip. Variable ret now references tip, and the loop continues. The increment statement executes, which changes k to have the value 3. Now the loop guard will be evaluated again. As the loop guard is evaluated here, you can see that the value of k is 3, and the length of s is 3 as well. Since 3 is not less than 3, the loop guard is false. Control in the program continues to the statement after the loop. The value of ret is tip, the reverse of the string parameter s. So tip will be returned. It's good to know that you'll see others write code, and you should understand that. Many programmers use I as a loop control or index variables. Some programmers think the letter I is hard to distinguish from the number 1, but I is more common than k in reading other code. Many programmers use the post-increment operator I++ instead of I plus gets 1. We won't explain the nuances of I++ here, but it's a very common idiom in using loops, and it's fine to use I++ by itself in the loop increment. Sometimes it's useful to define the loop index variable before the loop, rather than inside the parentheses of the loop. This allows the value of I to be referenced or accessed after the loop is over. When the variable is defined within the parentheses of the loop, that loop control variable can only be referenced within the loop body, but not after the loop. Have fun programming and programming and programming as you loop and loop and loop. Hello. We'll introduce the class character, which you can use to determine properties of character values in Java. The type char is a primitive type, like int, boolean, and double. Some people pronounce it char, some people pronounce it car, and some people say care. But everyone says the word character the same way, so I typically use the careful pronunciation. Char values are specified with single quotes. For example, you can see quote a quote, and quote one quote, and quote space quote here. These are character values. The value double quote a double quote is a string value. It's usually much easier to write the code than to say all these quote values. The character class has several methods you can use in writing code. You may remember the methods integer.parseInt and double.parseDouble. These were methods of the classes capital I integer and capital D double, respectively. The method capital C character dot to lowercase returns a lowercase equivalent of its argument. For example, this call will return a lowercase g, since an uppercase g is the argument to character.toLowercase. If you pass a character that's already in lowercase, the same value will be returned. The table shows Boolean valued functions like isLowercase and isDigit, as well as conversion functions like toLowercase and toUppercase. Using the Java documentation, we'll show you more Boolean and conversion methods. Have fun building character and writing code. We have the character demo class here in BlueJ, and we've got two methods that I'm going to run through and illustrate, and I'll add one very quickly. This first method, digitTest, creates a test string that has uppercase characters, lowercase characters, digits, and punctuation, moves through every character of the string, and calls the character.isDigit method, a Boolean method, and the character.isAlphabetic method, another Boolean method. So let's run through digitTest and see what it does. I'm going to create a new object on my workbench by right-clicking, and then I'm going to run the digitTest method by right-clicking on that. And we can see here pretty clearly that A, B, C, uppercase characters, little a, little b, little c, those are all alphabetic characters, and then the digits are labeled as digit characters. Notice that no punctuation was printed, so that when I go back to my editor, we can see that the uppercase characters were all alphabetic. The characters that look like digits were all labeled as digits, and the punctuation wasn't any character in that it didn't have the label alphabetic and it didn't have the label digit. I just want to illustrate one quick thing here. I can also say if ch is equal to the character hashtag, then I can print a message that it's a hashtag. Highly enlightening. And now if I compile this program it compiled without any errors. And I'll make another object. I'll invoke the digit test method. And we can see that, lo and behold, hashtag is a hashtag. That's just a reminder that for characters, we use single quotes to differentiate the values, whereas strings use double quotes. We can see that here, where I've created another string test in the method conversion test. I've created a similar string with uppercase characters, lowercase characters, digits, and some punctuation. I'm going to loop through by using the string char@ method to store a character variable, ch. I'm creating an UCH variable and an LCH variable, both of type char. I'm creating them calling character.toUppercase, which will return an uppercase character, and character.toLowercase, that will return a lowercase equivalent. Remember that converting a digit to upper or lowercase doesn't change the digit at all. And if a character is already lowercase, converting it to lowercase leaves it alone. So running that method, I will right-click on my class and call conversion test. We can see that I get the characters in my string on the left column, the function that you get by calling toUppercase, and the results that you get by calling toLowercase. So I get character, uppercase, lowercase. You can see that in each column I have all uppercase characters or digits and punctuation, all lowercase characters or digit or punctuation. And as one quick review of that code to remind you of where that came from, you can see that I called toUppercase, toLowercase, and then printed them as the character, the uppercase version, and the lowercase version. Using the Java documentation for characters will help a lot in making your program run smoothly when you're using character values. Have fun building more character than you did last time.
Welcome back. Now you have all the concepts required to implement a Caesar cipher. So let's get started developing the algorithm. As always, you should start with step 1, working an instance of the problem yourself. Even though we have seen some instances worked, it is good to work a small instance so you can write everything down and think it through. Let's encrypt the message I am, which is really I space AM, with a key of 17, meaning you will shift each letter 17 positions through the alphabet. You might want to start by writing down the alphabet, and then writing down the alphabet shifted by 17 characters underneath it. For example, A has R beneath it, where R is 17 characters to the right of A in the original alphabet. Next, you would go through and replace each character in the message with the appropriate letter from the shifted alphabet. When you are done, you have the encrypted message Z space RD. Great, you have finished step 1. Now it is time to do step 2 and write down exactly what you just did. The first thing you did was write down the alphabet. Then you computed the shifted alphabet. The third thing you did was to look at the 0th letter of the message. Don't forget, when you index into sequences such as strings and string builders, the first element is at index 0. That letter was I, so you looked in the alphabet to find I. Then you found the letter in the shifted alphabet at the same position, which was Z. So you replaced the 0th character of the message with Z. Next, you looked at the first letter of the message, which is a space. If you looked for space in the alphabet, you would not find it, so you would not change the character at index 1 of the message. Next, the second character is an A, for which you perform a very similar process as you did for the 0th character, and end up changing it to R. Finally, you do the same thing for the third character, which is an M that you turned into a D. Now that you have thought through all of that, you have a list of the 17 things you did for this particular message and this particular key. However, there's one more thing that is good to note here before you proceed. Notice that your algorithm calls for replacing characters in the message. If your message is a string, you cannot do that. As you recently learned, strings are immutable, meaning you cannot change them. If you recognize this issue now, you can adjust your algorithm to reflect the fact that you want to work with a string builder. Here we've added a step at the start to create a string builder from the string message. And then we updated the algorithm to work on the string builder. If you do not realize you need to do this now, you would figure it out at a later step. But the earlier you can figure it out, everything you need to do, the better. Looking at this algorithm, you can see that the first few steps are an initial setup before you begin performing repetitive steps for each letter in the message. If you focus on the steps after the initial setup, you can see that you are doing almost but not quite the same thing for each character in the message. One significant difference is what you decide to do based on whether or not you find the letter in the alphabet. Replacing the current character if you find it, or doing nothing if you do not. If you look at the steps for one particular character where the letter is in the alphabet, you will notice that the character you looked for in the alphabet is the current character in the string, and that the letter you used to replace the current character is what you found in the same position in the shifted alphabet. Now that you have thought this all through, you can write down a much more general algorithm. Notice that the step number 2 here requires a little thought and a couple of statements, but you have already seen how to do it. When you are looking for patterns, you should examine any constants, such as 0 here, and ask if you always use that constant, or if you need to look for a more general pattern. Here you always want to start from 0. What about 3? Do you always want to count, or do you always want to stop counting at 3? No. How high you count depends on the length of the message. Here we've written that you want to count to the length of encrypted, but noted that you want to count to less than it, not less than or equal to it. In our example, encrypted was 4, and you only want to count to 3. Now it is time to test out the steps. Pause the video now and try to encrypt the message A space bat with the key of 19. Did you catch the subtle problem with this algorithm? Even though it computed everything you wanted, we never said what the final answer is. You want to be sure to explicitly say this so that you know what to return from your method when you translate to code. Your answer is the string inside of the string builder you called encrypted. Now that you've fixed this detail of your algorithm, you are ready to turn it into Java code. Thank you.
Okay, now that you've developed the algorithm for Caesar Cipher, it's time to turn it into code. We've started here with the Caesar Cipher class, which has an encrypt method which takes the input to encrypt and an integer for the key to use to encrypt it. I've written here the comments with the pseudocode that we just developed in our algorithm, and I've gone ahead and written the first 2 lines of code. The first step is to make a new string builder with the input and call it encrypted, and the second is to write down the alphabet, which is a string. The next thing is to compute the shifted alphabet, so we're going to make a string, shifted alphabet. And remember, we saw in previous videos that we can use substring to do this. Alphabet.substring key concatenated with, that's what plus means for strings, alphabet.substring 0, key. That will slice the alphabet up into 2 pieces and concatenate them back together to give us the shifted alphabet that we want. Now we want to count from 0 to being less than the length of encrypted, and we want to call each number that we count I. So this is going to be a counting for loop for int I equals 0. I is less than encrypted.length, the length of encrypted, I++. And what do we want to do? Well, we want to look at the ith character and call it curchar. Curchar equals encrypted dot char at I. Then we want to find the index of curchar in the alphabet. Int idx, we said over here call it idx, equals alphabet dot index of curchar. And then we want to see if that's in the alphabet. As you've seen before, index of will return -1 if something is not there, and some other number if it is. So it would not be there if idx is index or is -1. We want not equal to -1 to mean it is there. Now we want the idx char of shifted alphabet, and we want to call that new char. Equals shifted alphabet dot char at idx. And now I want to replace the ith character of encrypted with new char. So encrypted set char at, and then I want the ith character to be new char. That's everything I want to do inside of that if. Otherwise, do nothing. I don't need to write an else if I don't want to do anything otherwise. This curly brace closes my counting for loop. And at the end here, I said I want my answer, so I want to return something, to be the string inside of encrypted. So encrypted.toString. I'm going to compile that. It says no syntax errors. And I've written here already this method testCaesar, which is going to make a new file resource, so it'll prompt us for a file, read it all in as a string, encrypt it. It will print out the encrypted message, and then it will also decrypt it and print out the decrypted message, because if we just saw a jumble of random characters, we wouldn't really be able to tell if we did it right, but being able to tell that we got the original back makes us more confident that what we did was correct. So I'm going to go over here to BlueJ. I'm going to say new Caesar cipher. I'm going to say testCaesar, and it's going to prompt me for a file, and I have here this message in a file called message1.txt that says free cake in the conference room. Maybe I want to send this to Robert without Owen seeing it and being able to get all the cake. And so I'm going to choose message1.txt. And we can see the encrypted message here, WIVV, etc., etc. It's been made more difficult to read. And then we can see down here where it decrypted it correctly. So I'd be a little more confident in this. I'd want to go through and check by hand that this actually came out with the correct key before I'd be completely certain that this test case worked correctly. Now, we've written and tested our Caesar cipher class. We tested it out on one message, and it looked like it worked. Does this mean we can be sure our code is correct? Of course not. Remember, when you're testing software, each test case makes you more confident in your code, but no number of tests can guarantee that your code is correct. You want more and more tests to be more and more confident, and one test case generally isn't enough. So here, I have a different message. Dear Owen, no matter what you may have heard, there is no cake in the conference room. The cake is a lie. Please keep working on Coursera videos. So I want to encrypt this and send an encrypted message to Owen to fend him off from the cake in case he intercepted my message to Robert. I'm going to use my testCaesar, and now I'm going to do message2.txt. And when I look at this, I'm going to see that the D in dear turned into a U, that's good, but then E, A, and R were left the same. Then the O in Owen turned into an F, but then W, E, N were all left the same. And in fact, most of this is unchanged. So my code isn't quite right. If I look back at it, I'm going to see that it's only going to work with capital letters and not with lowercase letters. This was the problem in our first test case. It only had capital letters, it didn't have lowercase letters, so we didn't really test all the cases enough. We're going to leave this to you to fix. There are a couple different ways you can do it, and we hope you can figure one of them out. So good luck, and happy fixing of your code.
Let us wrap up this lesson, where you learned a lot. First, you learned a bit about the historical as well as modern importance of cryptography. Then you learned some more concepts about strings, as well as how to use a string builder to efficiently construct a string. Then you learned about counting for loops, adding another important tool to your programming repertoire. Finally, you implemented a Caesar cipher, a classical cipher dating back thousands of years. As you will learn in the next lesson, this cipher is not secure by modern standards, but it is a good starting point to understand the ideas of cryptography.
Hi, I'm Jeff Forbes, a computer science professor at Duke University, and a friend of Susan, Owen, Robert, and Drew. I do research in computer science education and learning analytics, but I also teach the data structures and algorithms course using Java. I'm really excited to be able to give a guest lecture about using arrays to break or crack a Caesar cipher, a method of encryption I know you've been studying. You, or someone else, has implemented a program to encrypt text using a Caesar cipher. This is a very basic and historically interesting form of decryption, though it's not secure given patience or access to a computer and your skills at programming. The concepts in cracking the cipher are useful in solving other problems too. A key is used to encrypt, to shift all the letters in a message. But how do we decrypt? We know that decryption must be possible, since the intended recipient must be able to decrypt and read the encrypted message being sent. Because a shift of 26 is the same as a shift of 0, encrypting with the shift of 7 followed by decrypting with the shift of 19 will result in the original message, just like a shift of 26. How does knowing this help us crack the cipher? A thief, or hacker, could find the key, which is a number. Keys are often numbers, both in the Caesar cipher and many other forms of encryption. The hacker simply subtracts from 26 and will be able to decrypt the message. If the hacker or thief doesn't have the key, is it possible to use brute force or some other way to crack the cipher? Brute force means trying every possible key. With a human helping, using brute force with a Caesar cipher makes it relatively easy to decrypt the message. Suppose we intercept this message, which is too difficult to pronounce. Can we tell what this message says simply by looking at it? That seems unlikely. If we know the key used to encrypt this message, we could easily decrypt it. But how many keys are there? Perhaps we can simply try them all. That's what a brute force approach is. The basic idea is to try every key. We already have the code to encrypt the message. We'll use every key from 1 to 26 or 25 to encrypt the message we're trying to decrypt. Since the decryption shift is just 26 minus the original encryption shift, if we try all 26 shifts, we'll find the original message. We can try every key using this brute force approach because the number of keys is small, and trying each key is fast. The same approach won't work for other forms of encryption because there might be too many keys. It's also possible that using each key to encrypt could take a long time. Before we talk about an approach that's more sophisticated than brute force, let's work to understand brute force and what we call eyeball decryption. Our goal is to unlock or decrypt an encrypted message. We don't have the key used to decrypt. We're not that fortunate. However, we do have the key used to encrypt, from the class Caesar cipher. Using that, we can try all 26 keys. To decrypt using a human or eyeball approach, we'll create a Caesar cipher object. We'll try all 26 keys from 0 to 25. We'll use our Caesar cipher object, named cipher, to shift the message with each of the 26 keys. Then we'll print the result of the shift. As we'll see, we can decrypt the message if we recognize words. How do we find the original message? When we run the code we just discussed, we'll be able to view, or eyeball, the result of encrypting 26 times. We'll scan all 26 strings produced by 26 different keys, and we'll do this methodically. As we eyeball each string, we look carefully to see if the string is recognizable as English, since we're looking for an English language message. This line isn't recognizable. This line doesn't look like English, but let's look closely. No, it's not English. We'll look at the next line. Let's examine this line closely. This line is easily recognized as English text, and we see that encryption and security are fundamental parts of today's internet.
Hello. You're going to learn the basics of a powerful programming construct, the array. Nearly every programming language in widespread use uses a similar structure to be able to represent many items with one variable. When you wrote code to help a genome scientist solve a problem, you could count the number of occurrences of each C, G, T, and A in a strand of DNA. This is a real problem that helps find protein coding regions rich in CG content. As a programmer learning about encryption and decryption, you'll need to count the number of occurrences of A, B, C, and every letter of the alphabet through X, Y, and Z, 26 counters, to be able to break a Caesar cipher or decrypt a message encrypted with a Caesar cipher. Although you could do this with 26 variables, you'll learn a new concept to help with the coding. You'll learn about arrays, which are homogeneous collections of values. Here you see post office mailboxes. They each look the same, but each is numbered differently. You can access box number 344 or box 345, and you can either store letters and packages in a box or take them out of a box. Arrays are similar concepts in programming. As you'll see, one array could represent 26 or 1026 counters if your alphabet was huge or if you were solving a different problem. Let's look at code to help a genomic scientist. We'll look at code that counts occurrences of C, G, T, and A to understand and motivate the problem of counting 26 letters. As you can see, we've created 4 counters, initialized each one to 0, and then incremented the appropriate counter as we process every nucleotide in a digital strand of DNA. This solution works, but it's very hard to scale to having 26 counters, which we would need to count every letter, A through Z, as part of decrypting a message encrypted using a Caesar cipher. This isn't conceptually hard. We could use CA, CB, CC, and so on, up through variables CY and CZ to have 26 variables, and we could have 26 if statements to increment the appropriate variable. But writing the code and changing what we do with 26 values is time-consuming and difficult to change if we want to print something different, for example, when looking at the output. We'll use an array, an indexed collection, to use one variable in place of 26. We'll break the Caesar cipher by counting occurrences of each character in an encrypted message. A message in English would typically have the letter E as the most frequently occurring character. So once we've found how many times each character occurs in an encrypted message, it's likely that this character is E, and we can determine the shift used in encrypting the message, making the decryption process easy. In general, counting and collecting values is an important tool in writing programs, so learning about arrays in the context of breaking a Caesar cipher will help in solving many other problems. You've seen the class storage resource, which was helpful in storing string values. That class was useful, but its use was limited. We'll expand on the idea of arrays and the storage resource class later. For now, we need an indexed collection, like the collection of mailboxes we saw, in which a number is used to access a specific location. This is the same concept you've seen with strings, in which an index is used to access a particular character in a string using the .char or .substring methods. Arrays can store any type of value, not just the type char that's used in strings. We'll look at the concepts in code in using arrays and see how they're similar to what you've seen before with strings. You define an array similarly to defining a string. When defining a string variable, as you see here, you indicate the characters that are in the string and assign these characters to a variable. With an array, you must specify how many storage locations there are and use the square brackets with the variable name to indicate the variable is an array. This code allocates 256 memory locations, each one holding an int with the value 0, which is the default value for integers in an array. The concept of indexing is used to access elements of a string and an array. With a string, the .char method is used with an index to access a specific character. The first character is 0 because we used zero-based indexing. With arrays, the bracket operator accesses a specific element, again with zero-based indexing. When writing code, you often need to know the number of characters in a string or the number of elements in an array. With a string, you use the .length method to determine how many characters there are in the string. With an array, you use the value stored in .length to access the number of storage locations allocated for the array. Note that .length is not a method for arrays. This is sometimes a source of confusion when writing code. We'll look at the code to count the number of occurrences of every character A through Z. You'll see this code and the concepts in it will help you solve many problems when programming. In this code, you'll see a variable named counters that will represent 26 different counters. The code will store the number of occurrences of A in counters sub 0. We use sub as a shorthand for subscript, a term coming from mathematics. We'll see that counters sub k is the number of occurrences of the kth letter. By this we mean that the number of B's is at counter sub 1 and the number of Z's is at counters sub 25. As you look at the code, you'll see there are 3 parts, just as there were with the code that counted the number of occurrences of C, G, A, and T in the string representing DNA. In that code, 4 counters were defined and initialized to 0. Here, there are 26 counters defined and initialized to 0. The array referenced by variable counters takes the place of 26 different variables. In the DNA counting code, we used a sequence of 4 if statements to determine which counter to increment. Here, we use the location of a character in the string alpha as the index of the appropriate counter to increment. Note that A has index 0. We even use both upper and lowercase a's using the character.toLowercase method so that the index value returned by alpha.indexOf helps us increment the appropriate storage location in the counters array. Finally, to print each result, we use the loop index k to both access the kth value stored in alpha and the kth value stored in the counters array. You'll gain experience in solving problems with array. Here's a quick summary of what we've just introduced. Arrays are indexed collections of values. When defining an array, you will typically provide an integer value indicating how many elements can be stored in the array. It's possible to define a variable like x, as you see here, with no storage allocated for it, simply to define the type of the variable. This could be useful, for example, as a parameter in a method. If you define an array by calling new, you must provide an integer value for the number of array elements. In an int array, all locations will be initialized to 0. For a string array, all array locations are initialized to null. That's the value we've seen before that indicates there is no object being referenced. Array locations are read and written using indexes. You can store a value in an array, as shown here, with s sub 3 getting the string hello. This is writing a value into an array location. You can also access or read an array location, as shown here, where on the right-hand side of the assignment statement, we see x sub 3 is used to assign or write to a value on the left-hand side of the assignment statement, x sub 2. Once the storage is allocated for an array, the array size does not change. This may be why .length is not a method, but a value. When an array is passed to a method, the contents of the locations referenced by the array can change. This is subtle, and you'll see examples of it when we use arrays to solve problems. Have fun coding!
Computers are very good at modeling and simulation, in part because computers can perform billions of mathematical operations every second. Often, simulation and modeling relies on generating random numbers. In this coding example, we'll see a simple use of arrays to help determine how really random the java.util.random class is. Computers don't use natural random phenomena, but model randomness with what's called pseudo-randomness, using mathematics to model what might be random events in nature. In this example, we will simulate rolling a pair of dice many times by generating random numbers. We would like to know how many 2s do we roll, how many 7s do we roll. We will count how many times each type of roll occurs. So I've got this code right here called Simple Simulate, and I can run it and say how many rolls I want to do. And right now it counts how many times I get 2 and how many times I get 12. So let's run it and see what it does. So we'll come over here. It's already compiled. I'll create the object. And we'll run Simple Simulate. And here we actually get to choose how many times. So I'll say 10,000 times. And we'll just run it. And you can see I got 2 298 times, and I got 12 271 times. It'd be nice to run it and count all the possible rolls you could get from 2 to 12. So let's look at doing that. So what I'm going to do is I'm going to cut and paste this, and we'll write a different method. So we'll just copy this whole thing. And then we'll put it up here. And we'll just call this one Simulate. There we go. And so now we're going to have to modify it. So the first thing is we have generate rand. And then we need counters for 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's a lot of counters. So what I would like to do instead is to use an array of counters. So that's what we'll do. So we'll replace this here with an array. So we want an array of counters. So it'll be int array instead. We'll have to give it a name. We'll call it counts. And then we'll have to create the array. It's an integer array. And then what size is it going to be? So 2 through 12. We need at least 11 counters. But it would be kind of nice if we set it up so that when we threw a 4, we would count 4 in the 4th slot of the array. So what we'll do is we'll create the array with size 13, which will allow us to use from 0 to 12, and really we'll just use 2 through 12, and we'll ignore the 0 and 1 counters. So I'll make my array of size 13. I don't need this 12 counter anymore, so we'll get rid of that. Okay, so now we're going to have to adjust the code to handle using this array of counters. Okay, so we're still rolling whatever number of times we type in for rolls, so that's the same. We're still throwing 2 dice, D1 and D2, and we are going to add them together. But as you can see here, we have this if statement where we had to check and see, was it 2? Was it 12? And we could add all these other if statements. Was it 3, 4, 5, and so on? But instead, we can just notice we just add the 2 together. That's also the index position of the counter, and that's all we have to do. So we can get rid of this if statement. And instead, we're just going to add code. So we're going to update our counter at that position by 1. So our array is called counts. We're going to add in the D1 plus D2 slot. We're just going to add 1 plus equals 1. That's it. That replaced a huge if statement. Let's see. So now we're going to output. So you can see we have 2 lines of output for 2s and 12s. What we're going to do instead is we would be nice if we just had 1 print statement and we used it over and over again for each position in our counter array. So we're going to add a for loop here. And remember, our counter started at 2. So we'll have our case start at 2, because the lowest thing you can get is 2 1s from each dice, and that's 2. So that'll be the lowest. And then it'll be k less than or equal to 12, because we're going to go from 2 to 12. And then we'll update it the same way, k plus plus. Okay, and then we just need one of these output statements to modify. or I'll just type a new one. We'll just say here, so system.out.println. And what we want to do is we want to print k, because that'll be the counter, so k for 2 through 12, right? So we will print k, and then we'll print, we can still do the quotes, equals, and a tab, /t is the tab, plus, and then we want to know what was the, how many like 2's were there, or how many 10's were there, etc. And that's just counts k. That's how many of type k there were that we counted. Plus, we can add another tab. And then we can add the rest of this, 100 times counts of k divided by roles. And I'll just put that in parentheses. I guess it doesn't matter. We do need to add a semicolon at the end. And then I can get rid of these two print statements here. There we go. Okay, so I think we have everything now. So we've got, we now have our loop that prints for each one, 2 through 12, what it does. Let's see if we have it compiling. We're missing one right paren right here, so we can add that. Oops. We'll add it and then put our semicolon. There we go. Let's try compiling it again. And it says it compiles. There's our code. So now let's run it and see what happens. It's already compiled. We can create our object. And then we can run it, simple simulate. This is called simulate. And then let's run it again, like, oh, let's run it 100,000 times. There it goes. Okay, so now you can see we're getting lots of numbers, lots of counts for 2's, 3's, 4's, and so on. How do you know it actually works? We just got lots of numbers. It looks pretty good in the sense that if you roll 7, you're going to get that more likely than any other thing, because 7 is 2 and 5, 1 and 6, 3 and 4. And it does have the highest number. But to really be sure, what we'll do is we'll run a simple example and we'll add a print statement. Like, let's run it 10 times and let's see what the actual rolls are, and we can see if our counters are really working correctly. So let's do that real quick. We'll go back to the code here. So this is really adding just for testing it to make sure that the counters are really the counters we think they are. So whenever we roll a dice, which is right here, I'm just going to add a print statement here. So what I'll do is I'll print out roll is D1 plus D2, which equals D1 plus D2. And so that's all we're doing. We're just printing out the roll. Then we're going to just run it a very small number of times so that we can see our counters are actually working correctly. So we'll compile that, and that worked. So let's run it now. Okay, so I'm just going to run it 10 times, throw the dice 10 times, and let's see what we get. So we got, it looks like 1, 2, 3 7s, and if you look, it counted 7 3 times. we got 1, 2, 3 tens, and it counted 10 3 times. We got a 4 once, we got 4. So it looks like it is counting them correctly. So this is the way you can kind of test it on a small amount of data, and that seems to work. All right, so anyway, I hope you enjoyed dice rolling. Thank you. What are the most common words in the English language? There are many ways to find common words. Using search tools to find shared data that has been curated from thousands and thousands of available text helps here. Others have already done such to figure out what the most common words are. For example, they have determined that the word the is used more than any other word. Did Shakespeare use common words? We can use our edu.duke classes, public domain versions of Shakespeare's plays, and some simple array code to help answer this question. In this example, we will examine several of Shakespeare's plays and count how many times he uses the most common words. All right, so I've started the code for counting the most common words in Shakespeare's plays. So here's the code. Let's look at it. I've got this method called count Shakespeare. And you can see here, actually this is a new thing. This shows you how you can initialize an array. Right here you can, we've got the array plays, which is an array of strings. And we can just put curly brackets and list the items in the array. And so what I've done here is I've listed 6 data files that we've gotten that have text from 6 of Shakespeare's plays. We've also got another string array called common, and there's a method called getCommon. Let's go look at that and see what that does. Here's getCommon. And here you can see there's another data file. This one's called common.txt, and that's where I've already put 20 common words. The most common words that somebody else has determined are the most common English words. We're just going to read that in, and since I happen to know there's 20 words in there, that's important, I can create the common string array of size 20, because arrays have to know the actual size. So I'm reading that in, just reading, and this loop here, all it does is it goes through and just reads them in one at a time and puts them in there. So we read in the 20 most common words. That's all getCommon does. Let's go back down here. So we've got the plays, we've got the common words, and now we have a loop which is going to go over and it's going to read in each play. I've got the plays stored in a data folder, so you can see I'm adding data slash right before the name of the play. And then I'm going to call count words, which is going to count for each word in the play, whether if it's going to check and see if it's one of the common words, and if it is, it's going to count how many times each common word appears. And then we just print a message that says, hey, we're done with the plays. Once we've counted all the common words, then we go through and we're going to print for each common word, so for example, the, we're going to print the and then how many times it occurs in all 6 of Shakespeare's plays. So let's go ahead and run this and see what happens. We'll compile it. It's compiled. We will create an object and we'll just go ahead and run it. Count Shakespeare. And you can see it doesn't work quite right. It's only counting of a lot. So let's go back and look at the code. It turns out I haven't given you all the code. We still have to write one of the methods. All right, so let's go see. We are going to have to write index of. So what index of does is it takes a list of words and a word, and we would like it to look for the word in the list of words, or the array list of words, and see if it's in there, and count how many times it appears. Or actually we want it to give you the location, the index of where it appears in there. So what we're going to have to do is we're going to have to loop over all the words in the array list and check to see if word is equal to one of them. And if it is, we'll return the location of where it is. So this, let's go ahead and start that. All right, so we will start with a for loop. So in order to loop over the array, we'll need a for loop. So let's say we'll need a variable, int k, We'll start at 0. And then as long as we don't go off the end of the array, so we'll say k less than list.length. And then we need to update our counter k by 1. Okay, so we'll go through, and then what we need to do is for each kth slot, we need to check and see if the word matches the word that's in that slot. So we'll ask if, what is the word in list k? And we need to compare it to word, so we'll use dot equals. And if it equals it, we found it. So we can return the location of it. Return k. So this loop will go through and check to see, does word equal this word, this word, this word, and if we find it in slot k, we return k. If we don't find it, we need to indicate we don't find it, so we need to fix this return that's after the for loop, after we've looked at everything. We'll change this to -1, which is not a position in the array, and that will indicate that we didn't find it. Now let's see how index of is being used. We come over here. Index is being used in count words, which is right here. And you can see here, we call index of for each word. We're getting each word out of the file. We pass the common words, and we pass the word, and then we check to see, does it match? If it matches, then we're going to use the counts array to update that count. So for the word the, we'll keep track of how many times we find it. Every time we find it, we will update the counter counts, which is in the same slot as the word the, which is in the common array. All right, let's try and run this now. We'll compile it. No syntax errors, that's good. We'll come over here and we'll run it. So we're going to run count Shakespeare. There we go. So what this does is, first of all, you can see I've got 6 data files: Caesar.txt, errors.txt, Hamlet, Like It, Macbeth, and Romeo. And we've read all of those in, and for each word in that file, we've checked to see if it matches one of these common words. Here you can see the common words are the, of, and so on. And you can see that the appears in one of those, or in the combination of those 6 texts 4,237 times. And then you can see another one, 4, appears 1,071. So you can see how many times each of these common words appear. So it looks like Shakespeare did use a lot of common words. Now, how do we know this is actually correct? They're just big numbers. How do we know? So what I'm going to do is I'm now going to modify my program so I can run it on a really small file just to make sure and convince myself that I'm counting these numbers correctly. So I will come back over here. And you can see here I have this file called small.txt where I just put a few words in there. And what I want to do now is modify my code so that I look at this file small.txt. So back here in Count Shakespeare, what I'm going to do is I'm going to comment out this line here, these 2 lines, and I'm going to create my string plays just to be that one file. So I will say string plays is going to equal just the one file, which is small.txt. That's all I have to do. And now I'm going to run it. And this time it will just look at that one file. So let's compile it. We got it compiled. We need to run it. And there we go. So let's see. So if you look in small.txt, you can see the word the appears 1, 2, 3 times. If you look over here, you can see we counted the 3 times. That looks good. Of appears twice. We got 2, and appears twice. We got a appears once, a. So it looks like it worked. Now I'm really more convinced that I counted the Shakespeare words correctly. All right, that's it. Thanks.
We'd like to automate the cracking or breaking of the Caesar cipher. To do this, we'll rely on frequencies of letters in English text. If you're encrypting a message in another language, you'll need to use the frequencies from that language, but the approach will be the same. We'll write code to find the character that occurs most frequently in the message being decrypted. We'll assume this is the letter E, since E occurs more frequently than any other letter in English text. In Russian, for example, the letter O occurs more frequently than E. If our assumption about E is wrong, we won't decrypt the original message. It's possible to use more than just E, but to rely on the frequencies of all the letters and use statistical approaches to break the Caesar cipher. In some cases, these approaches will break other encryption methods, though not the methods used to encrypt data for online shopping and secure transactions. Let's look at the code for decryption in 2 steps. We need to count the occurrences of each letter A through Z in the message we're encrypting. We'll have code to scan each letter of the text and increment a counter for each of the 26 different letters. Initially, all the counters are 0 since we haven't started scanning the text letter by letter. Each counter is numbered from 0 to 25 because the counters are array elements. The index from a string of 26 letters will help us find the right index for the counter we'll increment as we scan the text. As we scan the message, looking at each character, we'll increment the counter at index 7 for H. Then as we scan I, we'll increment the counter at index 8, which is the index of I in our alphabet string. We won't increment for the comma or for the space. Then we'll increment the counter at index 3 for the D. The counter at index 14 for the O. We won't increment for the space because space doesn't occur in the alphabet. Then we'll increment the counter at index 24 for Y. And we'll set the counter at index 14 to 2 when we scan the second O in the message. When we're done scanning every character, we'll have these values for each counter. If you look carefully at these values, you see that our decryption method is likely to fail. The value of the counter with index 4 is 0. There are no E's in this message, but this is a very unusual message. Now, we'll look at the code for this idea. We scan the message character by character using a standard for loop. We find where the character occurs in a string of each letter in the alphabet, so that E will be found at index 4. Notice that we converted the characters in the message being decrypted to lowercase. We use the index in the alphabet to increment the corresponding counter as part of decrypting the message. If the character wasn't in the letters of the alphabet, the .indexOf method returned -1, and we don't increment any counter. The code that uses the idea of E occurring most frequently is straightforward to develop from the ideas, algorithm, and code you've just seen. As you can see, the code isn't very long, though we've created 2 helper methods and relied on this Caesar cipher class to help. We've called a method countLetters, which we just discussed. This method will count the occurrences of every character in the string encrypted, with A being stored in the first or index 0 location of the array, returned by the function, and referenced here by the variable freaks. Then we call a method matchIndex, which will return the index of the entry in freaks that is the largest. The location we will assume is where the E was shifted. We'll find the distance from this location to E E has index 4 since we start with 0 for A and then get B, C, D, E for 1, 2, 3, 4 respectively. If the maximal index is less than 4, we'll need to wrap around from 26 to find the shift used for E. If the value D key was used to encrypt, then 26 minus D key is used to decrypt, and we return the decrypted string. You'll be ready to use your programming knowledge to finish the task of decrypting and then apply this knowledge in the mini project with a different cipher. But there are some details we want to highlight. The array freaks in the code we just saw has a relationship between the index and the value in the array. For example, freaks of 8 is how often I occurs since I is the 9th letter and has index 8. Remember, we start with index 0. When looking for a maximal value, as with the method maxIndex that we called, and whose implementation you see here, we return the index of the largest value, not the largest value itself. We use the index to find the distance from E. Using the existing Caesar cipher class made decryption much more straightforward. In general, it is a good idea to use code that has already been developed and tested rather than reinventing it. Have fun coding!
Hello. In this module, you learned about arrays and how to use arrays to crack a Caesar cipher. You'll continue to solve problems using arrays. They're a powerful programming tool. Arrays are indexed collections. In Java, you use brackets to indicate an array variable, and arrays can store strings, or ints, or even storage resources. Almost anything can be stored in an array. The power of an array is that one variable name can represent 2, 1,000, or 1,000,000 different values, and each value can be accessed separately from the others. This access is done by a numeric index, a value that starts at 0 for the first element in the array, just like you did with strings. Just as a group of mail or post boxes can be found quickly using a number, accessing an array element by its numeric index helps in storing and accessing values. Here's a quick overview of how arrays work in Java. In Java, arrays are created using new, and once an array has been created, its size does not change. However, the values stored in each indexed array cell can change, and that's what makes arrays useful and powerful. Arrays are created using new, and brackets are used both to indicate that a variable like names is an array of strings, and as part of the syntax in new to specify the number of items in the array. You can define arrays of int values in Java just as you can define arrays of string values. Int values in an array are initialized to 0. String and other object values are initialized to null. You can assign values to an array using an index, and you can access an array to update the contents as well. You've used indices to access array elements, and loops are typically used to access all the elements in an array. Here's a loop that starts at the first index, 0, and loops through the last valid index, which is 1 less than the length of the array list. This is typical code that loops over array elements. In the loop body, the loop control variable is usually used to access each element in the array. In this loop, the value of k is used to indicate the index at which a word is found in the array parameter list. In general, this pattern of looping over all elements using indices is very common in solving problems using arrays. We used arrays to solve several problems, including cracking code. You saw how arrays were used in cracking the Caesar cipher method of encrypting messages, using frequencies obtained from the message by using indexing and arrays made it possible to crack a Caesar cipher. Indexing was also used in both encrypting and decrypting, as well as in cracking the code. It's good to know that the encryption used on the internet to protect your transactions is far more secure than a Caesar cipher. Scientists and mathematicians don't think that today's internet encryption can be hacked or cracked using brute force or even smart algorithms. But you should be careful online with your personal information in any case.
Welcome back. Now that you are becoming proficient at solving problems in Java it is time to talk about some aspects of Java that will help you solve larger problems. You have probably heard that Java is an object-oriented language, but what exactly does that mean? As the name suggests, your code works with objects, which you have already been doing with objects from a wide variety of types: strings, image resources, and CSV records, just to name a few. One of the important characteristics of objects is that they encapsulate code and data, putting them together into one logical unit. You have already written methods, which are the code in an object. However, you have not yet made your own fields, which describe the data within an object. As a familiar example, think about strings, which you have worked with a lot. A string is an object and it encapsulates code and data together. For a string, the data is the sequence of characters which it represents. These characters are logically inside of the string object. You can also call a lot of different methods on a string to operate on it, and thus on the data inside of it. You are familiar with many methods in string, such as index of and substring. As you learn a bit more about object-oriented programming, it is useful to be precise with terminology. A class defines a type, specifically what fields and methods are inside of objects of that type. Objects are instances of a class. You can make many different objects from the same class, which you do with new. You have seen new before and learned that you use it to make things, but now you can be a bit more precise. New creates a new instance of an object. So why use an object-oriented language? What is the point of classes and objects? A long time ago, programming language designers realized that it was helpful for programmers to be able to think in terms of objects as they correspond more naturally to how you think about the world. They designed object-oriented languages around this idea, along with a variety of features which help programmers design and write large programs. You're going to learn some basic features of object-oriented programming here so that you can create your own classes with both code and data. If you continue onwards to take our Java Programming Principles of Software Design course after this, you will learn some more principles and techniques of object-oriented programming. So let's dive right in.
Welcome back. To start learning concepts of object-oriented programming, it is useful to take an existing piece of code and see how you could write it differently in a more object-oriented way. Here is the code you wrote in a previous lesson to perform encryption with a Caesar cipher. As you may recall, one of the parameters to this method is the encryption key that you want to use. And the first thing you did with this code was to compute the shifted alphabet based on this key. Here is a different way to write the Caesar cipher class, which does exactly the same thing but makes better use of the object-oriented nature of Java. This class has two fields. A field is a special kind of variable which lives inside of an object instead of inside of a method. Here the two fields are the strings for the alphabet and the shifted alphabet, and they have been moved outside of the encrypt method. Notice that they are now declared inside of the class but outside of any method. These are now data that are encapsulated in your object. When you make a Caesar cipher object, it will have these two fields, which any code inside the class can refer to by name. Next, notice that there is some code here which looks like a method where we forgot to write the return type and named it the same as the class. This code is actually a constructor, which means code that gets run to initialize an object when it is created using new. This constructor takes in the key as a parameter and initializes the alphabet and shifted alphabet fields using the same approach you used before. If you look further down in this implementation of the Caesar cipher, the encrypt method looks mostly the same as before, but it no longer takes the key as a parameter, nor does it compute the shifted alphabet, but the rest of the code is the same. In fact, the code uses the alphabet and shifted alphabet fields in the object, even though these are not declared inside the method. This code is allowed to use them because it is inside the object, so it can use any fields within the object. An illustration helps understand the differences between these two approaches. In the old code, a Caesar cipher object held no data. When you do new Caesar cipher, you pass in no arguments and create an object with nothing in it. When you call encrypt, you pass the message and the key, and the method returns the encrypted message. In the new way, each Caesar cipher object contains a key. Now when you do new Caesar cipher, you pass in the key and the object you have created stores that key inside of itself. When you call encrypt on such an object, you pass in only the message. The key is already in the object, and it still returns the same encrypted message as before. So, if these two implementations produce the same result, what are the benefits of an object-oriented approach? When you encapsulate the key inside of the cipher object, you have one thing that is capable of taking a message and encrypting it. That makes a nice logical unit to think about, a thing that does a task. You do not need to separately track the key and pass it in. For small programs, such as the ones you have written so far, that may not seem like a big deal. However, as you solve larger programs with more complex code, this design idea will help you immensely. Now that you have seen an example of these ideas in action, the rest of the lesson will teach you about the details of the technique you just saw.
Hi. Now that you know a bit about object-oriented concepts, it's time to go a bit deeper into the idea of fields, which are also called instance variables. Remember that when we redesigned our Caesar cipher to be more object-oriented, we created two fields, one for the alphabet and one for the shifted alphabet. These fields are declared inside of the class, but outside of any method. They belong to the object and are created when new is called to create an object, either in code you write or when you create an object in BlueJ that's shown on the object workbench. These fields are part of the object and exist as long as the object exists. What does all this mean? Every Caesar cipher object you create has its own alphabet and its own shifted alphabet. This is why fields are also called instance variables. They act like variables where there is one variable per instance of the object you create. What does this really mean? Let's look more deeply at fields and instance variables. Every Caesar cipher object has its own copy of the alphabet and the shifted alphabet. You can make different Caesar cipher objects, and each will have its own instance variables. These variables are specific to the instance. If you create 3 Caesar ciphers with 3 different keys, each has its own copy of these fields with potentially different values. One cipher might have a shifted alphabet of QRS, for example, based on the integer shift value passed to the constructor, while another object might have MNO as the shift value. And a third object could have HIJ as its instance variable, set again when the object is constructed. To call a method like encrypt on an object, you'll typically use a variable name, like cc, and you'll write cc.encrypt. You can also call a method from an object on the BlueJ object workbench. These objects have names too. And when you call .encrypt, for example, the method will use the values of the fields in the object you use to call the method, like cc if you wrote cc.encrypt. Calling encrypt on this Caesar cipher will use its QRS shifted alphabet. So when we call .encrypt and provide the message First Legion attack east flank as the parameter, the QRS alphabet is used to create the encrypted version that you see here. In the same way, calling encrypt on this Caesar cipher object will use its MNO shifted alphabet. This is the principle of encapsulation. The method and the data are logically inside of the object, and the method acts on the data inside the object that it lives in. As you can see here, calling encrypt uses this shifted alphabet, and we see a different encrypted version of the same message, because the field shifted alpha that starts with MNO is used here. Finally, using this object with HIJ as the field will result in a different encrypted message. When encrypt is called, the encrypt code uses this shifted alphabet of this instance, and the encrypt code creates the encrypted message you see here. Fields, or instance variables, are very important concepts in designing and using classes, since they can be accessed by every method in the class, like encrypt that you see here, and the constructor as well. As you begin to design your own classes, and think about the fields and methods to put in these classes, here are a few design principles you should keep in mind. The first is that a class name should correspond to a noun. Classes describe things. Each object you make for a particular class is one of that thing. Let's think about the classes you've seen so far for this course. Strings, pixels, CSV records. Each of these is a noun. It describes a thing. A class could be a car, for example. That's a noun. And then the methods and fields would correspond to things that a car can do. Methods, on the other hand, are verbs. They're what you do to or with an object. Things like getPixel, setCharAt, or encrypt. Sometimes method names don't sound like verbs, such as substring or index of, but these describe actions. Get a subscreen or find the index of. The program has just shortened the name. For the car, a method might be accelerate or brake. These are things a car can do. For example, invoking a method would make the car go faster or stop suddenly. Fields, or instance variables, are important class concepts. Fields are also nouns and should describe things that the class has. The string class might have a field for a sequence of characters. A sequence of characters is a thing, and a string has one of these things. Similarly, an image might have many pixels. Fields can also be adjectives, as they describe the properties of an object. For example, a pixel might have a field, or fields, describing its color. That could be an adjective giving more information about the properties of the pixel. For cars, fields could include things a car has, nouns, like an engine with a certain number of cylinders, or wheels of a certain size. For cars, adjectives might describe the color of the car, or the kind of engine the car has, or the type of wheel. As you get started making more complex classes, we will provide guidance on fields and methods you should make. But think about these design principles as you write your code. As you gain more experience, you want to start designing classes on your own based on these ideas. Happy coding acceleration!
Welcome back. In this lesson, you are going to learn about the two visibility modifiers that you saw in the object-oriented version of the Caesar cipher. Public, which was used here, and private, which was used here. There are two other visibility modifiers. However, explaining them requires some more advanced concepts, so you will only learn about these now. When you declare something, whether it is a class, field, method, or constructor, as public, it means that any code anywhere in your program can access that thing. Code from any class can call a public method, read or update a public field, use a public constructor when making an object, and make use of a public class. By contrast, when you declare something private, it tells Java that only code inside of this particular class can see the thing you declared private. These two fields are declared private, so all of the code inside of the Caesar cipher class can read and update them, but code outside of the Caesar cipher class is not allowed to access them at all. So what happens if you write code that tries to access private fields or methods from outside the class? The Java compiler will give you an error like this, which says that you are not allowed to do that. In general, when you get this sort of error, it either means that you are improperly using a class, especially if it's a class that is part of an existing library, or that you have designed a class and made something private that should not be. So why do you want to declare things as private? After all, it seems like it would just be easier to make everything public. So you can just access whatever you want, wherever you want. Remember the idea of abstraction, the principle that you want to separate the interface from the implementation? Restricting the visibility of the implementation details helps you enforce abstractions you design. You can make the interface of a class, all the methods that other classes are supposed to call, public. And then you can make the implementation details private. No other class should know about the implementation details directly, and declaring them private lets you enforce that rule in your code. In our Caesar cipher example, you want other classes to be able to call encrypt, but they should not know about the implementation details, such as the fact that you made a variable called shifted alphabet. Keeping these details private means that you can change them and be sure that no other code relies on the private implementation details. As you start to think about designing your own classes, there are a few general pieces of guidance to get you started on how to choose public or private. First, fields are generally part of the implementation of an object, so they typically should be private. For methods, it depends on what the purpose of the method is. If the method is part of the interface you want your class to have, that is, part of the behaviors you want it to provide to other pieces of code, you should declare that method public. On the other hand, some methods are helpers. You write them to abstract out specific complex tasks, which are not meant for other classes to call. They just help accomplish the public interface. These methods should be private, so that only the code in your class can call them. For classes, you should always declare them public. As you become more skilled in Java, you will learn some more advanced topics that lead to situations where you might want non-public classes. But for now, always use public. Likewise, for constructors, you should always make these public for now. Typically, constructors are part of the public interface of a class. They specify how to make an instance. There are situations where non-public constructors are appropriate. But as with non-public classes, these only come up when you have learned some more advanced topics. So for now, you should just make constructors public. Great. So now you know what public and private mean, why they are useful, and some general guidelines for how to use them in your own classes. Thank you. Welcome. The last object-oriented concept you're going to learn in this lesson is constructors. Recall that the object-oriented Caesar cipher we wrote had a constructor, which took the key as a parameter and initialized the fields on the object. When you want to write a constructor, there are certain rules for declaring it. The first is that its name has to be exactly the name of the class it is in. Here, the constructor's name must be Caesar cipher, because it's in a class called Caesar cipher. The second rule is that the constructor has no return type, not even void. Normally, you would write a method's return type here, between public and the name of the method. But for a constructor, you do not need to write anything between them. Like a normal method, a constructor has its parameter list in parentheses. You can make constructors with any number and types of parameters you want. You can have no parameters to a constructor or several. Here we have one parameter of type int, the key. Finally, a constructor has a body, like a normal method. You can write whatever code you want in the constructor's body to specify how to initialize the object. Constructors are not quite like normal methods, however. You do not call them directly. Instead, they are automatically as part of newing an object. When you create a new object, the constructor is invoked to initialize that object immediately after the new object is made. This is one of the great benefits of constructors. They allow you to specify how an object should be initialized, and you can be sure that code will always be run for every object as soon as it is made. You do not have to worry about bugs in your code from forgetting to call some initialization code. What happens if you do not write a constructor for your class? Whenever you write no constructors, as you've been doing up to this point, the Java compiler will provide a default constructor for you. The constructor that the compiler provides looks like this. It is public, which you should recall, means any piece of code may use it to initialize an object. It takes no arguments, so you would pass no arguments when you create new objects. And it does not do anything. There is no special initialization of the object. Now that you know the rules about constructors, let's see how a constructor works. Let's suppose you had a line of code somewhere else in your program like this. Caesar cipher, CC, gets new Caesar cipher 22. This line of code asks Java to make a new instance of the Caesar cipher class and initialize it by passing 22 to your constructor. Let us see what this does by starting when Java is just about to execute this line. The first thing it does is create a new variable CC. Then it creates a new instance of the Caesar cipher class. That means you have a new object with its own copy of the fields of that class, alphabet and shifted alphabet. Then it calls the constructor, passing 22 for the key. Once inside the constructor, Java begins executing the code you wrote to initialize the object. This code initializes alphabet. then initializes shifted alphabet. Having finished the constructor, Java returns back to where you are creating the object. The key was just a parameter to the constructor, so it only exists during that call. However, the fields are part of the object, so they continue to exist in it. And then finishes the assignment statement by initializing the CC variable to the newly created object. Great! Now you know the basic rules of how to write constructors, what they do, and how they are used to initialize objects. Thank you.
In this lesson, you learned some of the basic concepts of object-oriented programming. You learned about encapsulation, the idea of putting code and data together in an object, such that the methods of the object act on the data that's inside the same object. You learned about fields, which are also called instance variables. They let you declare data that should be inside of objects. And you learned about visibility modifiers, private and public, which let you expose or restrict access to fields and methods so you can enforce abstractions and provide the interface you want. Finally, you learned about constructors, which let you write code specifying how to initialize the objects you create. When you do object-oriented programming, it's called OO programming, giving you 007, license to code. Hello, welcome to this module, in which we'll use the idea of creating random, hopefully entertaining stories to motivate and explore important Java concepts. Here's an example of a randomly generated story. We'll use a couple of these stories to introduce our Java concept. Let's look at this first story. My name is Albert, and I live in France. One day I'd like to travel to Mexico because I've never seen a tiger. And I read that they have gigantic slippery ones there. However, because 55 orange gigantic wheelbarrows make it difficult to travel, I may have to travel to Ecuador instead. That would be okay, but it might take 305 minutes to get there. We'll look at another story with the same pattern. Perhaps you can see some of the similarities to the previous story. My name is Vivian, and I live in India. One day, I'd like to travel to the United States because I've never seen a pangolin. And I read that they have furious and funny ones there. However, because 95 purple slippery houses make it difficult to travel, I may have to travel to China instead. That would be okay, but might take 445 hours to get there. There are many similarities in these stories, which isn't surprising since they were generated by a common template. You'll be exploring and modifying the Java program that reads the story template, finds replacement words where those are needed, and generates a story. The similarities in these stories are captured in parts of this template that are replaced with words chosen randomly from lists of words of different types. For example, your program might choose a name like Albert or Vivian, and choose a country like India, France, China, the United States, and more. Animals chosen could include tigers, pangolins, and whatever dragons you might imagine, for example. Your program can choose nouns, and as you'll see, the choices can make for interesting stories. You'll be able to share words that are chosen at random with other learners as you explore these new Java concepts. Let's get started.
You're going to think about the design and implementation of a class for generating random stories. This problem is a bit larger than the ones you have solved so far, so you will need to think about the methods that you need and how they work together. The same ideas that you're used to from the 7-step process will still guide you through this. You will not only need to think about the algorithm, but also the data involved and how to represent it. In Java, thinking about the data and methods guide you through designing a class. As always, you want to work the problem by hand before you do anything else. You could use a story template like this with pencil and paper by yourself or with friends. This template is similar to one you've seen before. It uses words and labels to create an interesting story. Let's look at how you might create a story from this template. This story template starts out, my name is, then the template requires a name. Remember that a label in angle brackets requires replacement. Here we want a name, so I'll pick my own, Drew. After that, it goes, my job is to, and then we need a verb. I'll let my friend pick a verb.
Ride.
And a noun.
Dinosaurs.
If you have ever seen one of these, you know that this job is really adjective.
Entertaining.
Because they are so adjective.
Fluffy.
Yep, that sounds like a great job to do when I retire. Ride fluffy dinosaurs. Now, if you started developing the algorithm for this random story program, you might end up with something along these lines. We read each word, saw if it had angle brackets around it, and then, if it did, picked a random word from that category. If there are no angle brackets, we just kept the word. But as always, you need to be careful, as it is easy to mentally gloss over things that happen naturally for you. In particular, we picked random words for each category, but how did we do that? More importantly, for this problem, how would you make a computer program do that? If I ask you to think of an animal, you can just do it, and it may seem hard to explain an algorithm to think of an animal. As a human, you just know what animals are. You implicitly have a mental list of animals in your head and can just name one of them. It may not be truly random, but maybe you just saw a cat recently or were thinking about your pet dog, but picking some animal is easy. For a computer, however, you need an algorithm and it needs to have data to operate on. The program will need an explicit list of animals to choose from, which could be written into the program source code or read from a file or from the internet. So if you think about these steps, there was a step that was implicit for you but needs to be explicit for the computer, making a list of animals. More generally, making a list for each template label, not just for animals. You should also think about this step, reading each word in the story template. Where did these words come from? This should be some sort of input, like a file or a website. Your program will need to read that file or website, which makes use of familiar classes like file resource and URL resource. You might also notice that some of these steps are a bit complicated. Making a list of words in each category might require more than a few lines of code, though using a file resource or URL resource will help. Picking a random word might also require some planning and programming. It is perfectly fine for your algorithm and thus your program to end up with complicated steps. These steps may be names of other methods you will need to write. For example, you might write a method to pick a random word from a category. Suppose the method were named pickRandomWord. If you had this method, the corresponding step in the algorithm is now just one line of code. You just call the method pickRandomWord and it does the work for you. Working through the algorithm development helps you figure out what methods to write. As you write each of these methods, you may in turn find you need yet more methods. Don't let this worry you. As you break the large program down into many smaller problems, the methods you find you need to write will often be simpler than the ones you started with. To make the list of words, you will need some variable to hold the data. But how should you store this data? What type are each of these lists of words for template labels? You have seen two types that would work, an array of strings and a storage resource. But neither one is ideal for this problem. Each of these structures has benefits and drawbacks. The storage resource class is relatively simple to use. Your code can add elements to a storage resource without knowing how many elements are going to be added. That is, without knowing the number of colors or nouns or names that will be added. Accessing storage resource elements requires using a for loop to iterate over all of them. This will make choosing an element at random a little tricky to code. On the other hand, string arrays have almost the opposite benefits and drawback. It's simple to choose an element at random. Pick a random index less than the size of the array and return that element, like the element at index 2 or 7. However, declaring an array variable requires knowing how many elements would be stored. That makes arrays not always the right choice. We could use either a storage resource or a string array to implement this program, but we'll see that a new concept, the array list, combines the best aspects of both arrays and storage resources. Happy coding!
Welcome back. In this lesson, you'll learn about a new class, a very important part of Java that combines essential features of the storage resource class and an array. In fact, this new class, the array list, is the foundation of how the storage resource class is implemented. To motivate the problem, think about counting how many different words there are in a file or a web page. But the same problem is encountered in finding the number of unique IP addresses that visit a website in a day, a key part of charging a company for online advertising. You've seen how to count the number of each type of nucleotide in digitized DNA. And you used an array to count the number of occurrences of each alphabetic character in cracking a Caesar cipher. These are first steps in counting how many times each word occurs in a file, how many times the occurs, or cat, or the word albatross. One important part of solving that problem is finding how many different words there are, so that the counts as one word rather than 573 if it occurs that many times in a document. In the image below, there are only 3 different digits, 4, 6, and 7, even though there are hundreds of digits shown. We'll look at storage resource as a way of solving this problem. First, we'll count the total number of words in a file or web page. The class storage resource makes this easy. To count the words in a file or web page, you'll iterate over either a file resource or a URL resource. As you can see in the highlighted code, iterating over a file or web page using these resources uses nearly identical code. And here you see that simply calling the .add method adds each word to the storage resource instance variable myWords. When done, the .size method will provide the total number of words read. The method .getCount returns this number when called again using the instance variable myWords, which was initialized in the constructor and added to in the method readWords. As you'll see, it's easy to use storage resource to count the number of different words, not simply the total number of words. This code can be easily modified to find the number of unique or different words in a file or web page. The field myWords, whose type is storage resource, can store all the words as you've just seen and as shown in the code here. The .add method adds every string read to myWords. But it's simple to guard the call to .add with code that only calls .add when the word is seen for the first time, when it hasn't been stored in myWords yet. The .contains method returns a Boolean value. In the code here, this value is used to ensure that the .add method is called only when the storage resource object myWords does not contain a word. However, the storage resource class is not a good choice for choosing elements at random, a key part of the storytelling code GladLibs we're working on. To choose an element at random, we must use the iterable interface that storage resource provides. This means we use a loop to access every element in the storage resource object myWords. In the loop here, we'd really like to iterate as many times as the value stored in variable choice, because we want to choose a random element of the storage resource. The code here returns a random string when the value of counter reaches 0. As you can see in the code, the value of choice must reach 0 since it starts as a value less than the size of myWords and is decremented by 1 each time through the loop. However, the Java compiler analyzes a loop with an if statement and doesn't know that it's possible the if statement must be true at some point. The compiler indicates it's an error to be missing a return statement after the loop, even though that part of the code is never reached. It would be simpler to code and much faster to use a string array to get a random element as shown in the code here. We simply generate a random integer and use that as an index into the array. Unfortunately, we must specify the capacity of an array when we declare it. Arrays do not grow in the way that a storage resource object grows. The class ArrayList provides a solution and combines the best feature of storage resource and arrays. The class ArrayList is from the java.util package, the same package that contains the random class we've used. An ArrayList expands its capacity as needed when its .add method is called, just like a storage resource object. An ArrayList also provides access via indexing, so that the 0th or 101st element can be accessed without iterating over all elements, just like an array. The storage resource class uses an ArrayList internally. In fact, it's simply a little easier to use than an ArrayList, but as you become more experienced, you're now able to use ArrayList, which stores any kind of object, not just strings. The basic syntax of the ArrayList class is shown here, but you'll see it used in a coding example in the next lesson. To declare an ArrayList variable, you must include the type of object, stored in the array list using the angle brackets as shown here. Like any object, creating one requires calling new and providing the class name as a constructor to create and initialize the object that's shown here and assign to the variable words. Then you can call the .add method to add strings to the array list object. And you can call the .get method to access a particular element via indexing, just like the bracket notation used with an array. But with an array list, you'll use the .get method. The .set method can change or set the element at a particular index in the array list object. Here, the first or 0th indexed element is set to the string goodbye. We'll see more examples as we go through a coding example with ArrayList. The ArrayList class is more powerful than storage resource and can store any kind of object. It will be an essential class in solving many problems with Java. Thank you.
Hi, we're going to show an example of how the ArrayList structure works. We'll show code that keeps track of how many times each word in a file occurs. The file, or it could be a URL, could be a large file, like text from Shakespeare's Romeo and Juliet, or like the sayings of Confucius. We don't know how many different words there are before we start reading the file, so we can't easily use an array. Instead, we'll use two ArrayList structures, one that holds strings and one that holds integer values. We'll need integer instead of int. We'll explain why. The kth value of the ArrayList, whose name is myFreaks, will store an integer, the number of occurrences of the kth value in the instance variable ArrayList myWords. The names are names of instance variables that we'll see in the code. As shown here, we see two occurrences of the, with a string and an integer stored in the location with index 0 in the two different array lists. Similarly, there are three occurrences of the word dog and one occurrence of the word green. Let's write code. We've got a class, word frequencies. I'm going to open it up and take a look to see how it works. And one way we can easily see how it works before we look at the code is simply to run it. So I've created an instance of it on my object workbench, and I'm going to right-click and run the tester method. I'm going to open the file romeo.txt, the entire text of Shakespeare's Romeo and Juliet. And I can see that there are 5,895 unique words. What I'd like to do with array lists is count how many times each word occurs. So I'll find out how many times the occurs, Montague, Capulet, all the words from Romeo and Juliet. Just going through this code very quickly to highlight the key features before I add the counting. I have an instance variable, myWords, which is initialized to be able to hold strings in the constructor. In tester, I call the function findUnique, which creates a file resource, and because it had no parameters, that allowed me to open up any file I wanted. It loops over every word, converts each word to lowercase. If the word has never been seen before, which I find out by using the ArrayList method .indexOf, which is a method whose same name we've seen in the string class, if it has never been seen, I add it to myWords. Now what I want to do is have a parallel array. I will call it myFreaks for my frequencies. So I need another instance variable. This has to store integer values. And unfortunately with array lists in Java, I must use integer. You've seen this before with integer.parseInt, similar to the class double.parseDouble. I'll explain this as I go. I need to store integers. I'm going to create place for it. I'm going to initialize that in the constructor to a new array list of integer values. And then, if I've never seen the word before, that means this is the first occurrence. So I'm going to add to the end of the array list the value 1. This is just like the idea of the first time you see a word, it's occurred once. But if I've seen it before, this is in my else statement. If I've seen it before, I know where it is because index tells me. So what I'm going to do is find the value that's in myFreaks. This is the number of times it's already occurred. I can get this value using the get method, and then I can set the value in myFreaks to value plus 1. So let me make clear what I've just done there. I've accessed the value at the location specified by index, which was returned to me by the .indexOf method. And the idea here is that if the word the occurs in location 500 of my words, the frequency or number of times that occurs is in location 500 of my freaks. They match up exactly. This will, I hope, compile. Cannot find my freaks. So I've looked up here and I can see my freaks, my freaks, my freaks. That's because I forgot to say set. The name of the method to set the value is set. Now I'm ready to run it, but I haven't printed any values. After I've printed them, so after I've tested them all and found them, I will literally print every single word and how many times it occurs. So I'm going to use the standard for loop that loops over array values or array list values. Size is the method that tells me how many there are. And I'm going to print the number of occurrences, which is in my freaks, a tab character, and then the word itself. That compiled. I'll create a new one by right-clicking and creating a new object. And then I'm going to run the tester method on this object by right-clicking. There's the right-click, run tester. Let's count Romeo. And you can see how many times different words have occurred in Romeo. For example, the has occurred 677 times, Romeo 48, and Juliet 23. Another word that occurs often is Juliet with a period. I haven't taken into account punctuation at all, and from occurs 86 times. Let's make sure that part of the code is clear. I've accessed the value in my freaks and stored it in the int value. And then I've set the value at index to value plus 1. Because array lists use integer rather than int, this is a two-step process. Find the value and then store the value. That's what we need to do with integer, which would be a little bit different than we had with int. We'll see that in a later video. Let's look down here. MyFreaks.getK returns the kth value of the frequency array list, and MyWords.getK returns the corresponding word. The 23rd frequency is the number of times the 23rd word has occurred. Now that you know a little more about array lists, let's write some code.
Hi, you've seen array lists at work and how useful they are? Arrays are extremely useful too. So we're going to go through a quick walkthrough of code to show where arrays don't work so well. Creating an array is easier in terms of syntax than creating an array list. Far fewer characters to type, for example. It's much easier to access values in an array since a sub k can work to either read from an array location or write to the array location given the index k. In contrast with array list, you use .get and .set for reading and writing respectively. With int values, arrays often have more benefits in some ways than array lists do. Although most conversions between int and integer happen automatically, occasionally these conversions can lead to hard-to-find bugs if you don't have a thorough understanding of how the int and integer conversion works. It's easy to increment the value in an array given the index. However, in an array list you have to call .get and .set since the code to simply increment the result returned by .get does not work. However, arrays don't grow, and that's a really large concern. Let's write some code. Now we want to find the number of unique words in a file, but we want to use, or at least try to use, an array. So that's what we're going to do here. I've started this program. The class is called Words with Arrays. And the first problem we run into is we want to read in all the words from a file, but we don't know how many words there are in the file. So we don't know how big to make our array. So we can't really use an array for that. So we'll use a storage resource for that part of the program. So I've already started here. We've got my words, which is a storage resource. We have created the storage resource in our constructor. And then we have read words, which is going to read all the words from the file and put it into our storage resource, my words. Note it's also going to add them in as lowercase, so all of the words have been lowercased. We have a method called contains, where we're going to pass in an array of type string and a word, and we want to know, is that word in our array? So what contains is going to do is it's going to look through the array and see if the word that we're passing in matches anything, and if it does, it returns true. If we go through the whole thing and we don't see it anywhere, we're going to return false. Now, we have number of unique words, and the first thing we've done is we are going to create an array here to store all the words that are unique. So you can see I've started that here. I've gone ahead and putting words as an array of type string. I have to create a new one, so I do that. And then I get to the part about the size, and I don't know how big to make it. So I don't know how many unique words there are going to be. So the only thing I can do is just make it as big as my storage resource. So I made the size mywords.size. That's the only safe thing to do, because all the words could be unique. Now we're going to iterate over my words, and we're going to check and see for each one, is it in words, which is going to be just the unique words. So is it already in there? If it's not in there, we found a new unique word, and we're going to put it in there. So you can see here on this line we add it in, and then we're also keeping track of how many unique words we have, because this method is going to return the number of unique words. And so every time we find a new unique word, we're going to add 1 to that count. The next thing we have is we have a tester method, so we can test this out right down here. So we're just going to call it and test it out. So let's compile this. It's already compiled, it looks like. And so we'll go ahead and run it. We have to create our object, and then we'll call the tester class. And we have to pick a file, so I'm going to pick confucius.txt. Oh dear, we got an error. So it says down here, we got a null pointer exception. Also over here, this is our output here, you can see that it did read in all the words from the file. It says there was 34,582 words read in, but you can see also it got a pointer exception. And you can see where that exception is. It says in the tester on line 45, and then in number of unique words, there's a line for that, and then contains on line 23. And so that top one is probably where the error is. And if we click on that, it goes to where this error is highlighted here. And you can see our errors in contains. So what is the problem? Well, the problem is we're using this array to put all the unique words, but we don't have any in there yet. And then we're actually iterating over the whole thing, which is all empty. It's initialized to null. And so we're checking, does a value that's null equal a word? And that's why it crashed, because you can't compare null to a string. So we need to fix this. So what we really want to do is we want to keep track of how many unique words we have in there, because we just want to check the unique words that are actually in there, that we've actually put in there. And so what we'll have to do in order to fix that is, first of all, we'll have to add another parameter so we know how many words we've actually put in there. So I'm going to add a parameter here called number, and we actually have to give it a type, so it's going to be an integer number. And then when we iterate, we just want to iterate over the words we put in there. So we want to replace list.length. Instead of looking at the whole gigantic array, we want to look at just the ones that are already in there. So number tells us how many are currently in there. Now, we also have to fix where we call contains, which is down here. And we have to put a value here. That value, remember, we're keeping track of how many words we put in there that are unique words. that is the variable num stored. So we'll pass num stored here. Let's compile that and see if that works. We got no syntax errors. Let's try and run it. And it works. So you can see here we've had a lot of trouble trying to use an array. This problem really should use an array list, because here what's happened is this is a file that has 34,000 words, of which only the unique words are 6,558. So that means the array we're using is of size 34,000, but there's only 6,500 unique words. So we have a lot of extra space. That's another reason why an array list would be better for this problem. All right, happy coding.
Hi, as you get ready to start the program to create stories from templates, let's summarize what you've learned about the ArrayList class in Java. Array lists are like arrays. Both are indexable collections, allowing you to access elements with an integer index. ArrayList can grow as elements are added to it. This means you don't need to know in advance how much space to allocate for an array list like you did for an array. Like arrays and individual string elements, indexing in an array list starts with 0. It takes the same amount of time to access the first element of an array list or an array as it does to access the 10,000th element. It might help you to think of array lists as a collection of boxes, each addressable with a number. To use the ArrayList class, you must import it from the java.util package. You can import just the ArrayList class, or use the asterisk and import java.util.star to gain access to all of the classes in the package, like the random class. When you create an array list, you specify the type of elements stored in the array list, using the angle bracket syntax that Java uses for generic or general elements. Here you see an array list that can contain string objects. But array lists can also store integer objects too, though the list must store integers or strings, not the same type in one list. The integer class allows int values like 0 or 57 or negative 352 to be stored in the array list. The integer class automatically converts an int value like 57 into a value stored as an integer object. You've seen several methods used in array list objects. The .add method adds an element to the end of an array list. The array list grows as needed. The .size method returns the number of elements stored in an array list. Typically, this is the number of elements added via .add. You can write code to access individual elements with an integer index using the .get method. And you can change the value stored at a specific index using the .set method. Array lists are typically processed and accessed using loops. Here's a typical indexing loop that processes each element of an array list. These for loops typically start at 0 and loop to less than the size of an array list, which is exactly .size elements. Within the loop, each array element is accessed using the .get method and the loop index variable. When accessing array elements in a loop like this, do not call .add or .remove, which will change the size as the loop iterates, typically causing a problem in your algorithm because you will either skip elements or access invalid elements. You can also access the elements in an array with an iterable loop, the same kind of loop we used with the edu.duke iterable classes. In an iterable loop, your code indicates the type of value stored in the array list. Your loop takes on each value stored in the array list one at a time, just as with the file resource or image resource classes. You can use this kind of loop when you don't need the index of each array list element, but just the element itself. Just as with an indexing loop, do not call .add or .remove with an iterable loop. In this case, Java will generate a runtime error if you try. Array lists are a very useful tool when used properly.
Now that you've learned about array lists, it is time to work with the gladlib.java program. You'll learn how it works and how to modify it to create stories with new kinds of data. You'll need to understand the program so that you can modify it. As a programmer or software engineer, sometimes you'll be creating programs from scratch, and sometimes you'll be modifying programs, enhancing them, making them more robust, and more. In this program, there are many pieces, many methods, each of which you could write yourself. This means you'll be able to understand each method and be able to modify the program in different ways. Since you'll start with a working program, you'll be able to make improvements and additions while testing your program to see that it continues to work correctly. You'll be able to understand class design, method design, and the limitations of the gladlib.java program you start with as you make improvements to the code. As you work to understand these aspects of software design and engineering, you can tell stories about it. As you modify the program, you'll be creating reusable program components and reusable ideas that you'll be able to use as you develop software experience and expertise. We'll take a tour of the program before you begin to make enhancements and improvements. As with all Java classes, a constructor will initialize a gladlib object. The constructor will create the array list instance variables that hold replacements for nouns, colors, and more. It will also create the java.util.random object used for choosing a replacement at random. The general control flow of the program after initialization will be to read a story template and process each word. If the word is a label like country or time frame indicated by angle brackets, the code will find a replacement at random. After the story is created, the program will print it. Let's look at these pieces in more detail. First, let's take a quick look at creating stories from the template you just saw. There is one public method in the class, makeStory. Calling this method will use a template to generate a story, as we'll see when we look more closely at the code. In Kenya, a long time ago, nearly 245 decades ago, there lived a pink, funny tiger. It so loved to sing and dance, but there was an angry, gigantic lion named Lance that scared it so much. In Ecuador, a long time ago, nearly 105 months ago, there lived a jovial, yellow polar bear. It so loved to sing and dance, but there was a furious, angry rabbit named Albert that scared it so much. Reading words from the template and printing the story will be code you likely won't need to modify. Calling makeStory will read a template from a file or URL and loop over each word in the template. If the word is a label with angle brackets, it will be replaced. Finding labels is a straightforward use of .indexOf and .substring in the private method processWord. We use these methods to ensure that punctuation or letters before and after the angle brackets are preserved. Printing the story will display the final result in the console window of BlueJ or a different programming environment. The private method printout has a parameter to specify the line width, so you can create a story and use 80 or 40 characters or any other number. You could modify the printout method to write the story to a file too using the edu.duke.fileResource class. Changing the gladlib.java program requires understanding how the ArrayList instance variables are used. There is one array list for each possible label in a story template, like noun or color. These instance variables should be named appropriately so that programmers will be able to easily understand their use in reading and modifying code. As with all instance variables or fields, they'll be created and initialized when the gladlib constructor is called, either using new or from within BlueJ when you create an object. The program could use all the fields when replacing words as part of telling a story. The field adjective list will hold replacements for the label adjective. The field noun list will be for nouns, and the instance variable color list will hold colors to be chosen at random. Each field holds replacements for the label that's part of its name. This is a convention in the program, not required by Java, but following the convention will make it simpler to create a new instance variable like verb list for a new label. We'll look at each use of these fields. One is finding a substitute for a label like color. Based on the word that's part of a label like color or noun, the private method getSubstitute will access the appropriate instance variable to find a random replacement. For example, if the label is color, then a replacement will be chosen from the field color list. If the label is noun, then noun list is used. You can see in the method getSubstitute that adding a new label will require adding a new if statement to access the appropriate array list. A value is chosen at random using a private method randomFrom. Both randomFrom and getSubstitute are private. They're called as a result of calling the public makeStory method. When getSubstitute calls randomFrom, getSubstitute will always pass one of the instance variables you made, such as adjective list, noun list, etc., as the value for the parameter source. Initializing the array list is straightforward, but you'll need to understand it to create a new field for a new label. All the array lists must be created and initialized when the constructor is called. The constructor will call a private helper method initializeFrom. The source for the data for colors, nouns, and so on could be a URL or a file. Calling initializeFrom will result in reading files or URLs to store strings in each array list. If the parameter to initializeFrom begins with HTTP, then eventually a URL resource object will be used to read data. Otherwise, a file resource object will be used. You can't see that in the code here because the parameter source is simply passed to the helper method readIt, where the reading code is located. Let's summarize how the instance variables for replacing labels are used. You'll need to understand this to enhance the program by adding a new label. For example, to create a label like verb, you'll need a new instance variable. You'll name it appropriately, like verblist. You'll need to modify code in two methods with the addition of verblist. You'll modify the method initializeFrom, a private method called from the constructor. You'll modify the code in the method getSubstitute, also a private method, called by the public makeStory via the private methods FromTemplate and processWord. The program documentation should include information like this to help you, the software engineer, make modifications and enhancements. Have fun telling stories and writing code.
We'll outline some of the design features of the GladLib class and talk about software design in general. Adding a new label like verb means modifying the gladlib.java implementation in several different places and requires following a naming convention used in the class. You'll need to create a new instance variable for the array list that stores examples of verbs like run, think, or swim. You'll need to initialize the array list using the method initializeFrom, called from the constructor. You'll need to get a random verb when needed by modifying the code in the method getSubstitute. You should follow the naming conventions used in the class, where the label noun is associated with the instance variable noun list, just as the label country is associated with country list. This means you should use the name verblist for a field that's the array list that stores strings that are verbs. As you modify and extend programs and classes, you'll gain experience with many kinds of programming and design. You'll gain experience that will help you make good decisions when programming and create good designs. But you'll see that sometimes experience comes from bad judgment or bad designs that nevertheless allow you to reason about the trade-offs in doing things in more than one way. So you might realize that a choice that works can lead to code that's not easy to maintain. Some software designs are called brittle, meaning that the software or design breaks when you try to extend it or use it in ways that is a little bit different than what's initially intended. Flexible designs, on the other hand, are better able to cope with changes in the software. When you learn about object-oriented design, you might come across a principle that says code should be open for extension but closed for modification, the open-close principle. The idea is that you should be able to extend software without extensive modifications to the existing code. That's more possible with object-oriented design ideas that we won't be able to cover in this course, but you can still create designs that are more open than others. You'll be able to understand a better design after working with this design and implementation. The GladLib class does have some good features. It's relatively easy to understand, each method, and the code works. It is possible to extend the code, as you'll see, even if the extension requires changing the code in several places. You'll be able to create a better design after learning some new Java concepts we'll introduce soon. But those concepts will be more clear because you'll have this experience with this code and class, and you'll understand why the new Java features can make the code simpler. The new Java features will let you keep changes in one place rather than being sprinkled across 3 parts of the class. The new features will also minimize the duplicated code that's in the current implementation. Have fun making new stories!
Hi, we're going to walk through the process of adding a new label to the gladlib.java program in the gladlib class. A new label might be something like verb, which would go along with noun, color, and the other labels we have. To do that, you've seen part of that process outlined in one of the previous lessons. What I'm going to do here is show you that to add a new label, we need a new template file. So I've taken the standard template file that we had before, which was called madtemplate.txt, and I've replaced sing and dance, the two things that a creature would do in the stories we generated, with verb and verb. So I'm adding the label verb to replace sing and dance in the original story. I've still called this madtemplate.txt. You'll use whatever text editing software you have, which is usually something like TextEdit on a Mac or Notepad++ on a Windows machine, but you can use any text editor. Now I'm going to take the gladlib program that we've used before, and I'm going to walk through the locations where we need to make changes. I need to create a new array list to store my verbs. I'm going to go along with the same conventions that have been used before and make sure that I use verb list to go along with adjective list, noun list, etc. As I scroll through my source code, I see that these array lists are initialized in the initializeFromSource method. It's called from our class's constructor. I need to initialize verb list, and it's going to be initialized by calling readIt, passing the source, which is either a place on my computer where it can access files or a URL. This is verb.txt. I'm going to also have to make one other addition because now my label might be an adjective or an animal or a name, but I'm going to need to copy and paste these so that in addition to using time frame, I'm going to use verb. So I'll replace that, make sure I get the syntax right. If the label is verb, I'm going to replace the label from verb list. I'm going to compile my program. I know that in this program it's reading the template from madtemplate.txt, which I've modified to include the angle bracket, verb angle bracket label. I'm going to create a new gladlib on my object workbench, and then I'm going to run the makeStory method. It's so loved to unknown and unknown. There was a funny slippery lion named Vivian that scared it so much. So if we go back and look at our source code, we'll see that it must have found verb but failed to replace the verb with the objects that it was replaced with. In this case, I've got verb list here, my instance variable. I've initialized it from verb here. I've made sure that if label.equals verb t, I had a misprint when I spelled it. Now it's got verb. So I'm going to go back and recreate that, create my gladlib object, open it up and make a story. Hey, it's so loved to think and contemplate, but there was a gigantic tiger. Let me run that one more time and see if I get something besides think and contemplate. It's so loved to ride and surrender. One more time and I'll be convinced that it's actually reading verbs. It's so loved to surrender and surrender. We've done nothing to make sure that it can use the same word or verb more than once. So, just to remind you what we've done, I've used this location to change when the label was found. I've made sure that the label was read from the source, and I used verb list here, which is the name of my instance variable here, verb list, using the same naming conventions we've used in all the other programs. I compiled my program, I tested it, I created a new text file to hold verbs, and a new text file for the template. Happy verbing.
Hi, it's time to learn about a new way of structuring data. This also helps in structuring classes. You've seen some of the concerns with the design of the GladLib class. The design has flaws, but you still were able to add a new label and create new stories, so the design works. Larger programs with the same flaws might be harder to modify. You've also seen code to count nucleotides in a strand of DNA and letter frequencies to break a Caesar cipher. We extended this idea to counting word frequencies in any file with 2 parallel arrays. To count nucleotides, we used 4 int variables to count each time a C, G, T, or A occurred. To count letter frequencies, we used an array of 26 int values, 1 for each letter, A through Z. To count words, you saw code that used 2 parallel array lists. These contained as many values as there are different words being counted. Now you'll see how to use the concept of parallel array list to help understand the java.util.hashmap class, a new way to structure data. Using a hash map will make it much easier to modify the GladLib class. The hashmap class is also very efficient compared to using 2 parallel array list. We'll explain the hashmap class using the parallel array list class to help. You've had a chance to see this code that uses 2 array lists to count how many times each different word occurs in a file. The method .indexOf finds the location of a word in the array list of strings named myWords. If the value returned by the .indexOf is -1, then the string read from the file hasn't been seen before, and it's stored in myWords with a corresponding count of 1 in myFreaks. If the string has been seen before, the integer value in myFreaks at the same index is incremented by 1. This code works, but using a hash map will make the code much faster, and the hashmap class will make it easier to modify the GladLib class as well. Let's work to understand the concepts in the hashmap class. A hashmap object associates keys with values. In many languages, this is called a map. You might think of the key or legend in a map as you can see here. The key helps in understanding the map. You can look up the color in the key or legend and understand what the color means in the map. In programming, the concept is more mathematical than geographical. The word map has meanings in both math and geography. The key is an element in a domain that's being mapped to a value in the range. In math, a function is sometimes called a mapping, and this expresses the ideas in the hashmap class as well. In a hash map, you look up a key and you get the value associated with the key. In an example illustrated here, we are counting word frequencies. The word rainbow occurs 41 times, so the integer value 41 is associated with the string key rainbow. In Java, the value returned by the call map.getRainbow is 41. The value returned by map.getTruth is 17, indicating the string truth occurs 17 times. If football occurs 23 times, then 23 is the value associated with the key football and is returned by the call map.getFootball. Wonderful occurs 23 times in our hypothetical example. The keys in a map are unique, but it's possible to have the same value associated with different keys. To use a hash map, you'll need to understand the operations it supports. We'll use one hash map to replace the 2 parallel array list. Here's the code that uses one array list of strings and one array list of integers, with the .indexOf function used for associating integer values with strings. The hash map code also associates an integer value with the string key. The key in the hash map will be a string. The value is an integer. That's the number of times the string occurs in a file being processed. To define a hash map variable, you'll need to specify the type of both the key and the value. When calling new, you must specify the key and the value types as well. The key is the first type and the value is the second type. The code will determine if the key has never been seen before, whether it's stored in the hash map or not. The method .contains key on the map object returns a boolean indicating whether that key is in the map. If it's not in the map, the value 1 is put in the map with the key, using the map method .put. If the string is a key in the map, meaning the string being processed has been seen before, the value associated with the key is found using the .get method, and then a new value is stored for the key by calling map.put with an updated value of 1 more. In addition to accessing individual map keys and values, you'll also need to access all the keys and values in a map. Printing the strings and frequencies when parallel arrays are used requires a typical indexing for loop, with the index used to access both strings and integers as shown here. Printing all the key value pairs in a map requires looping over all the keys and getting the value associated with each key. The method .keyset returns an iterable you use to access each key in a loop. This is similar to using .words or .lines with a file resource or URL resource to access elements, or the .data method to access each string in a storage resource. Iterating over the key set and calling get for each key allows you to print the contents of a map. Maps will allow you to modify the GladLib class more easily, but maps are incredibly fast too. When files are large, efficiency matters more than when they're small. This concept of using efficient structures or code is important. Computers are so fast that simple concepts lead to code that's fast enough given how fast computers are today. As you can see in the first row of the table, counting how many times each word occurs in Shakespeare's Julius Caesar is fast enough on a laptop computer, even using the parallel array list. With a bigger file like the sayings of Confucius, the code for array list is still under half a second, whereas the hash map code is incredibly fast. For the novel The Scarlet Letter, there are many more unique words and total words, but the hash map code is still roughly 10 times faster than the array list code. For a large file like the King James Version of the Bible with over 800,000 words and 32,000 different words, the array list code takes more than 20 seconds, while the hash map code is under half a second. That's more than 40 times faster. Looking up keys in a map takes time that's independent of the number of keys. Roughly speaking, this means getting the value for a key in a map with 1,000,000 keys takes the same time as looking up the value associated with a key in a map of just 10 keys. With an array list, you might have to look at all 1,000,000 elements in the array list, so a hash map is incredibly fast. In later courses, you'll study how the hash map class can be so fast. In this course, you'll use hash maps in many examples. Happy coding!
Hi, today we're going to write some code to find out how many times every word in a file occurs. So we'll find out how many times the word the occurs, how many times the word wonderful occurs, and we're going to start with a working program. Let me show you very quickly what that looks like. This countWords function that we have here, this method countWords, simply creates a file resource, loops over all the words in it, and counts how many total words there are. If I take this program, make an object on my workbench, right-click and call countWords, it will ask me to enter the name of a file. I will use Confucius, and it will tell me that there are 34,582 words in the works of Confucius. Rather than knowing the total number of words, I'd like to find out how many times each individual word occurs. To do that, I'm going to use a map. So I'm going to need to add another local variable here, a hash map. I'm going to map strings to integers. Each string will be a word that occurs in my file. That's the key in this map. And the value in the map is how many times that word occurs. So I need to create a new one. I'm allowed to make a hash map because I've imported java.util. That's the package in which we find hash map. Now, as I read the words, rather than incrementing the total, I'm going to ask, have we seen W in the map before? So I'm going to ask whether the key set associated with the map contains W, the word I'm looking for. And if it does, I've seen the word before, I'm going to put the value W back in the map. It's already there. I'm going to get the number of times that word occurs and add once. I'll go over again what I'm doing in a minute. If I've never seen the word before, then what I'm going to do is put it in my map with the number 1, because the word will have occurred one time. Let me compile and make sure I've got that right. So let me go over very quickly what I've just done. I've looked to see, does this word W that I just read and converted to lowercase, is it in my key set? Have I ever seen it before? If I have seen it before, let me get the integer value associated with it. That's the number of times it's already occurred. Add 1 to that, and put that in the map as a key value pair with the word and an incremented count. If I've never seen it before, this is the first time. I've now added all the values to the map, and I'd like to print them out. The way I'm going to print them out is to loop over the key set. That's all the words that are keys in my map. And I'm going to get the value associated with it. That's the number of occurrences. That's the value associated with my word. And if that value is big, and here I'm going to say if it's bigger than 500, I'm going to print the words that occur a lot. So I'm going to print the number of occurrences, a tab character, and the word itself. So I'm looping over the key set. That allows me to find every key. I'm getting the value associated with that key in the map. And if that's big, I'm going to print it. Big in this case is bigger than 500. So I'm going to right-click and create a new object. And I'm going to invoke the method countWords, which before used to count the total number of words, and now it's going to count all the individual words in Confucius. And here we can see that in the file Confucius, there are not that many words that occur more than 500 times. The occurs more than 2,000 times, and occurs 762. If I want to see a little more in the way of words, I'll say 200, just to make sure that I'm getting something more. And I'll make a new version of this that sits on the object workbench. I'll right-click and call countWords. I'll once again count Confucius, and you can see there are more words. Master occurs 484 times. Confucius was the master of many things. You are now going to be the master of programming as you use maps to map keys to values to solve many problems. Have fun coding.
In this lesson, we'll look at how we can use the HashMap class to make our GladLib class easier to extend, have fewer lines of code, and be a good example of how to become a more skilled and experienced software designer. As a reminder, extending the class to use a new label, like angle bracket, verb, angle bracket, requires modifying the code in 3 places. You'll need to create an ArrayList instance variable, initialize it properly, and use it as the source for your random replacements. You should also follow a convention of using field names like verb list for the label verb. This makes it difficult to use text files or URLs for the source of word replacements unless all such sources follow the same conventions, such as using a file named noun.txt for the label noun or the field noun list, or color.txt for color list and the field color. Let's take a look at the concepts behind these requirements for extending the GladLib class to look at a new way of structuring data in classes. Each label is associated with an ArrayList instance variable. You see the label noun associated with noun list, the label color with color list, and so on. These named instance variables make for a poor design. Adding a new label, like verb, requires defining an instance variable by name, initializing it by name, and using it by name. That's 3 places in which the program must be modified. Instead, we'll use a hash map to help create a better and more flexible design. The hash map will allow us to label or align the label to an array list without ever having to name the array list itself. Given a label, the code will look up or find the associated array list in the hash map structure. As you've seen, this is similar to how index of works for finding a value in an array list or a character in a string. Getting the value associated with a label will return an array list. Let's take a closer look at how using a hash map creates a more flexible design. One hash map will replace 7 or more instance variables. The hash map will reference as many array lists as needed, rather than us having to define separate instance variables and following a naming convention as you see here. The code will use a single instance variable, a hash map named myMap. This will associate an array list with each label. So the keys in the map are strings, the label in the GladLib program. The value associated with each key is the array list of replacement words for that label. This means that to add a new label and a new array list, we don't have to add a new instance variable. We simply need to store new values in the single hash map instance named myMap. Let's look at how the method getSubstitute works with the hash map. In the original program, a sequence of if statements was used to identify the instance variable associated with a particular label. The naming convention of using country list for country allows a programmer to extend the code, but there will always be as many if statements in the getSubstitute method as there are labels and instance variables. The last if statement is different. You can see that the label angle bracket number angle bracket generates a random number instead of finding one in a list of numbers. When using a hash map, the getSubstitute method is much more simple. The hash map associates a label with the array list of replacements. The array list for a label is accessed using the hashmap.get method to get the array list associated with a string label like country or noun or color. Adding a new label doesn't require modifying this method at all. And that's an example of the open-close principle we talked about in a previous video. Using a hash map makes for a more flexible class that's easier to extend, but there's room for even more improvements using hash maps again. The original program reads a file or URL to store information in each named instance variable, the array list of replacement values for that label. That was done in a sequence of statements that call the helper method readIt. The hash map version still associates a label with a file name, and that file name must be specified in the program. But the code is different because we use a loop to associate each label with a file name. This wasn't possible in the original program. Note the private helper method readIt is still called. What changes if we want to add a new label like verb? The program will still associate the name of the file of replacement values in verb.text with the new label. We could store a new string like quote verb quote in the local string array of variable labels. We could add that just after the string timeframe, for example. Unfortunately, we still have the limitation in that the code uses a naming convention for files like verb.text for the label verb. We could use a hash map in a different way to associate file names with labels without modifying the program. The program could be designed to read a file of information that specifies where to find the words to replace the labels, rather than requiring the code to be modified, compiled, tested, and run to simply find nouns in a different file or website. This kind of file is often called a .properties or property file. As shown here, it simply associates a label with the source of replacements for that label. Hello, let's summarize what you've had the opportunity to learn studying our GladLib example of creative storytelling. The gladlib.java program read templates from files or URLs to create engaging stories about any topic you chose. We used the program to motivate the need for and study of the ArrayList class. Array lists are like arrays in that they support indexing to individual elements, but an ArrayList object can grow as needed rather than being a fixed size. We also use the program to motivate the study of the hash map class. Hash maps are very efficient structures that can be used to associate keys with values. You saw two examples of this in the study of the GladLib class. We also use the GladLib class as a small case study to understand that creating code and programs that are extensible is a good idea, but requires thinking, planning, and experience. We use the GladLib class to study the ArrayList class. An ArrayList object is an indexable collection of elements. ArrayLists store primitive types, so you can store integer objects but not int values. This means you often need to update ArrayList integer values in 2 steps. First, getting the value and updating it, and then putting that value back in the map. To use the ArrayList class, you must import it from the java.util package. In contrast, you don't need to specify a package for arrays. Useful methods you've seen include add, to add a new element to the end of the array list, size, to determine the number of elements in an array list, get, to access an element by its index, set, to update an element using its index, and index of, to determine where an element is stored in an array list by index. You can write code to loop over all elements in an array list by either using an array list object as an iterable or using an int for loop, starting at 0 and looping up to, but not including, the size of the array to access each element by its index. We also studied the hashmap class. A hashmap object is a collection of key-value pairs. The keys serve as mappings for accessing the values, hence the name hashmap. Both keys and values are objects, so you would use integer rather than int, just as you did for the array list. Keys are best as immutable objects, like string or integer. Keys must be unique. Values can be any object type, including string or array list, as in the examples you saw. You import hashmap from java.util just as you do for the ArrayList class. In the examples, you saw the methods put, to add a key-value pair to the map, size, to determine the number of pairs or keys in a map, get, to access a value by its key, keyset, to iterate over all the elements, and contains key, to determine if a key is in the map. Looping over all elements requires an iterable over the key set of the map. You can't access individual elements one at a time by an index as you can with the array list. 2 different collections with 2 different sets of strengths. We hope you'll have fun using them.
Now, you're going to write some programs to analyze web server log files. Most major web servers log each access to a file, which records who made the request, when the request was made, what the request was, and how the server responded. So why would you want to analyze web server logs? A web server's log file lets you understand a lot about how your website is being used. You might want to know how many people are visiting your site. Is it popular or not? If you have many different pages, are they all getting traffic or only a few? Understanding how your site is being used is particularly important if you're trying to make money off of it. Popular pages bring in revenue, while pages that nobody looks at are not helping your business. The log file can also be useful in diagnosing problems, as it will tell you when your server is experiencing errors. If one of the pages isn't getting traffic because a link to it is broken, you want to know so you can fix it. In the rest of this lesson, you're going to work on code to read the contents of a log file. Being able to read the contents of a log file will set you up to solve a variety of problems, such as figuring out how many different visitors have come to a website or how many times each visitor has visited the site. Welcome back. Now that you know about the importance of web server logs, it's time for you to start thinking about writing code that deals with them. The first thing you're going to want to do is to be able to read in a web server log file and represent the information in it in Java objects. To do this, you need to think about 2 things. The first is, what does all of the information in the web server log mean? And the second is, how do you represent it in a Java class? Here, you can see one entry from a web server log file. It has a lot of information, and it's not readily apparent what each piece means. To find out what it means, you would want to read documentation about this web server. This particular data came from the web server log for an Apache 2.4 web server. So to find out more, you could go to Google and search for Apache 2.4 web server log file format. If you do that, you'll end up with a lot of hits. And this first one here gives you a link to the Apache documentation site. If you scroll down a bit, you'll find the information on the access log, that is the log of accesses to the web server, which is what this web log is, and you will see that it has information about each of the pieces of this entry. The first is the IP address, that is the address of the device on the internet which made the web request that is logged here. The next two pieces are both dashes. That indicates that they're missing information. The first dash is for some information about who made this request, which you'll see the documentation says is unreliable. The user's computer could lie about who they are. The second dash is for the username if they're logged in with HTTP authentication, if they've typed a username and password on the website. The next piece of information is the date and time when the request was made. Next, you have the request itself, including what type of request it was, in this case GET, where they're asking for a particular web page, and then what page they asked for. Next is the status. Here, it says 200, which indicates success. There are many other statuses which indicate success or failures. You may be familiar with 404, which is the very well-known status code that indicates that the requested page was not found. Finally is the number of bytes that the server replied with, how much data it sent back to fulfill this request. Okay, now that you've read the documentation and understand what each of these pieces of information mean, it's time to think about how to represent them in a Java class. The first thing you need to think about is what type of information each of these is. For the IP address, you could use a string since you're interested in just the text of that field. Java does have a built-in class for IP addresses, which would give us some more features if we wanted to actually connect to that address, for example, but we don't need that functionality, and we don't need to worry about the complexity that would introduce right now. We don't need to represent the two fields that we've omitted that have no useful information. We do, however, want to represent the date. You could use a string for that, in which case you would just have its text, or you could use the built-in Java date class, which understands what dates and times are and how they relate to each other. So you could check if one time is before or after another time. For the request, you can just use a string. And for the status and number of bytes, those are both numbers, so you can use an int. Now that we've thought through these types, it's time to turn this into some Java code. Here, you can see the start of a Java class for a log entry. We've declared a public class log entry and written fields based on the types that we just discussed. You should now think, should each of these fields be public or private? Remember that if a field is public, any piece of code can access it, and if a field is private, only code within this particular class can access it. In this particular case, it makes sense to have each of these be private and to design your class to be immutable. Remember from earlier, when we learned about strings, that immutable means you cannot modify an object once you create it. So you're going to write this class so that each of these fields will be set in its constructor, but can only be read. To make anything able to read these fields, you'll write a public getter or accessor method, such as these, which will just return the value of that field, but there will be no way to set the value of the field once it's constructed. Speaking of constructing, you need to write a constructor for this class. There are two ways you could do it. The first is to take in this entire string and then have the constructor pull it apart into each of these individual pieces and fill in the fields or instance variables of the class. The other is to have the constructor take each piece of information separately and simply initialize the fields of the object. We're going to have you do the second one, just making a constructor that looks like this, which is going to fill in the fields based on the information passed in, with each piece being passed separately. Why would you do it this way? Well, this gives you a little more flexibility. If you wanted to create one of these objects from some other source of information, you could do so. It turns out that pulling this line apart is actually a little bit tricky, so we're going to give you the code for that. It's a little bit ugly, and and we'll package it up into a nice method for you so you can just use it to read the file. Here is the final log entry class with all of the things you just learned about. You would use this to represent one of these log entries as you work with it. So your next task is going to be to use this class, the code we give you to split this up into each separate piece, and put them together to make code that's going to read the entire log file.
Hi, so today what we're going to do is we have this log entry class, and I want to show you toString. So the log entry class, notice it has these 5 fields here, IP address and so on. We've got our constructor, and we've got all these methods. And I've written toString down here, and you can see that it returns those 5 fields as one big long string. And what I've done is I've got a tester over here that is creating 2 log entries, LE and LE2. And I've just kind of made up some information for each of them so they're different. And then it prints out the actual object. It prints out LE and it prints out LE2. So let's run it and see what happens when we do this. So I'm going to come over here. Notice I need to compile both of these. I'm going to compile tester, and it actually compiles both of them for me. I'm going to now run tester. Test log entry, and there you can see it printed out the 5 pieces of information for each log entry. Very nice. So now what I'm going to do is I'm going to come back to my class, and instead of calling it toString, I'm going to change the name. I'm going to call it getLogInfo. And compile it again and run it. And let's see what happens. So I've got my object, and now I'm running test log entry. Oh, so I ran it, but it just printed out something else. Let's see what it printed. It actually printed out the memory location of each of those objects. So let's go back to test our tester here, and you can see when I print out an object, LE, it doesn't know how to print it out. So it just prints out its address location. It's not calling the method we wrote, which is called, let's see here, right here, we called it getLogInfo. It's not calling that because we didn't specify it. So let's come back over here, and we'll specify to print out a log entry with that method. We need to actually write log entry dot get log info. And I'll just do that for the first object, and I'll leave the other one, LE2, like that, and let's see what happens. We'll compile it, and we'll come over here and run tester. And so you can see what here in for the first object I called getLogInfo, and it calls getLogInfo, and it prints the 5 pieces of information. But for the second one, I just said print the object, and so it just shows the memory location of it. So what's going on here? It turns out that every class has a toString method by default, but it only knows to print out the memory address of an object, unless you actually specify a toString class. So I'm going to change this name back to toString. And I'll come back over here in our tester and get rid of this. Because notice, I didn't actually call toString here. I just said print out the object. And again, if I show you what happens here, we don't need the, there we go. So we're just going to print out the object. We're not saying how or anything, but it just knows, go look in my class, and if there's a toString method, that's how I'm specifying how I want to print it out. So again, we call it here. And even though I didn't call toString, it knows, it says, oh, you've got a toString method, so I'll use yours. And it prints out the 5 pieces of information the way I specified I wanted the object printed out. Now I want to show you one more thing. I'm going to come over here. That name toString is very important. It has to be spelled exactly toString with a capital S, because I'm going to show you if you change it to lowercase s, so it says toString, then when I come over here and I run it, let's see what happens. It goes back and writes the memory address, because it says if there's a toString in there spelled with a capital S, it's going to use that. But that's the only thing it looks for. Since I don't have it spelled correctly, it doesn't find it. And so it says, I'll just print out the memory address location. So just remember that all objects have a default toString method, and if you don't like it, it's just going to print out the object address. Then you can write your own, and so when it runs, it'll see if there is a toString method in there, then it will call it. That's it. That's for toString. Thanks.
Hi. Now that you've made your log entry class, you need to parse the lines of the web server log to be able to create instances of the log entry class. You'll do this by splitting the string into the appropriate fields to pass values to the constructor for the log entry class. You could accomplish this task with many index of and substring calls. Although this task is not algorithmically hard, the code for it is very cumbersome. For example, for the time portion of the entry, you would need to turn the string into a date object, the built-in Java class from the java.util package, which represents a date and time. Even though both the date and time class, as well as methods which parse strings, are part of Java, the interface to the date class is complex, especially since the date format in the server logs is not the default format in Java. For these reasons, we've provided code for you which will take a string from the web server logs, parse it into appropriate fields, and return a log entry record. To use this, call weblogparser.parseEntry and pass the string you want to parse. The method returns a log entry object. With that in mind, it's time to turn your attention to starting to write the log analyzer class. For right now, you're going to write code in the constructor to initialize the object, and then write the readFile method. In later lessons, you'll write additional methods that will perform the actual analysis of the log file that you've read in. The first thing you would do to fill in the code for the constructor. The constructor should initialize the record fields to an empty array list. You've created array lists in the past, so what you need to accomplish this task should be familiar. The second thing you should do is fill in code for the readFile method. This method will determine the file name to read from, and then add log entries to the records field to reflect the information from the file you opened. To accomplish this task, you will want to make a file resource for the requested file. You will then want to iterate over the file resources lines. And for each line, you will use the weblogparser.parseEntry method to convert the line of text into a log entry. Then you'll add that log entry to the records field, which, as you may recall, is an array list. When you've written the constructor and the readFile method, you'll want to test out your code. We've provided a convenient method called printAll, which will print all the log entries you've stored in the instance variable records. Remember the toString method that we taught about? System.out.println will make use of that toString method to represent the log entry as a string. Once all this works, it will be time to start analyzing the data you've read in. Happy coding!
In this lesson, you learned a bit about web server logs, which can give you a lot of information about your website. You learned what is in them, how those records are formatted, as we looked at the Apache web server documentation together. And then you learned how to make a log entry class based on the information in that file. As part of that, you learned about toString, which is an important Java concept, as you will want to write a toString method in many of the classes you create. Finally, you wrote code to read in the log file using the parsing code that we provided. Now you are ready to write some code to analyze the data you've read in.
Welcome back. You have already written code to read a web server log file, parsing each line into a log entry object and creating an array list of them. Now it is time for you to write some code to analyze the data you have read. The first problem you're going to solve is finding out how many different people visited a website. You don't want to just look at how many elements there are in your array list, since some people may have visited your website multiple times. So you need some way to distinguish requests from different places. You can use the IP addresses recorded in the log file to tell where the requests came from. Using the IP address is not perfect, since you cannot distinguish between different people using the same computer. But how many different IP addresses you see is a very good estimator for how many different people visited the site. As you might recall from Programming and the Web for Beginners, an IP address is the address of a device on the internet, whether that device is a traditional computer, a mobile phone, or something else. So what you are going to need to do to solve this problem is take the array list that you have read the log entries into and find out how many distinct IP addresses are in it. Have fun.
You have already written code to read in the entire contents of a web server log, and now you want to find out how many unique IP addresses it contains. As always, you're going to want to approach this problem with the 7 steps you use for every problem. We're going to walk through this problem, starting at step 1. But we're going to use color names instead of IP addresses. This problem is really the same problem. You're finding out how many unique values there are in an array list of strings. But color names are easier to say and to see which ones we're talking about. So when we look at this list of 10 values, you might be able to tell just by looking at it that there are only 4 unique values. But if this list had 1 million elements in it, we'd like to develop a method that would still work. There are many ways of solving problems in general, and in this case, there are a couple that I'll mention and one that we'll realize in code. One method that we won't do is to, as we look down the list, cross out values that we've seen before. Crossing out values in a list is a problem in Java programming because if we replace the values in our parameter with other values, we've caused a side effect, something we've spoken about before as a thing to avoid if you can. So instead, we'll use an idea of visiting every value in the list in turn, which is typical for array problems. And if we haven't seen a value before, we'll copy it into a new list. So first, I'm copying the value pink because I haven't seen it before in my new list. Then I'm going to visit green. I haven't seen it before, so I'll copy it over into my new list. Now I'm going to visit pink. I've already seen it, so I don't copy it. Then green. I have seen it, so I don't copy it. Pink, 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 I've seen them all. Orange, I haven't seen before, so I'll copy that into my new list. The next value is blue. I haven't seen, so I'm copying it into my list. Finally, I get to pink, the last value in my original list. I have seen it before, so I don't copy it over. Now I look at my list that I've created. It has 4 values, and so I'm going to return the value 4 from my method that I'm writing that determines the number of unique values in the array parameter. Developing this algorithm follows a lot of the same patterns you've seen before. You'll see that sometimes you add an element to the copy, and sometimes you do not. And you'll want to think through the conditions under which you add. Once you've done that, you can express the main portion of the algorithm in terms of steps to do for each element of the input. We'll let you work through steps 2 and 3. Hopefully, you came up with pseudocode that looks like this. Now for this particular problem, you'll want to do things just a little bit differently. Remember that you have log entries in the field records, and you want to use the getIPAddress method to get the string out of the log entry object. There are a couple of ways to deal with this difference. The simplest is to just use the same algorithm, but adjust it slightly to reflect the fact that you want to use records, the fields in the class. And you want to get the IP address out of each element of records. check to see if that IP address is in copy, and if not, add the IP address to copy. At this point, you'd want to test out your pseudocode. Then you're ready to turn it into Java code.
All right, now you've devised the algorithm to count the unique IP addresses in a web server log, so it's time to turn it into code. As usual, we have here the outline of this method with the pseudocode that you've just developed. The first thing we want to do is make unique IPs, which starts as an empty list. So we're going to have an array list of strings, and we're going to call it unique IPs, and it's going to be a new empty array list. Now, we want to do something for each element, which we'll call LE, in our records. So as you're familiar with by now, this is a for each style for loop. Each of these is going to be a log entry. And remember that records, even though we don't have a records variable in here, is an instance variable in our class. So we're going to take each log entry in records, and then we're going to get the IP address out of it. And then we want to know if IP address is or is not in unique IPs. So we're going to say if unique IPs dot contains IP address, but we want not that. That is the opposite, so we're going to put a not in front. Then we want to add IP address to unique IPs. Unique IPs dot add IP address. Close that. Close that. And then at the end here, it says we want to return unique IPs.size. Now my braces have ended up in slightly weird places. That's probably just because I have some braces in my comments. So I'm going to delete those and then try to make sure my code lines up nicely. Okay, so now I'm going to hit compile. It says class compiled, no syntax errors. Of course, we want to test this. I've already written a tester here, which is going to create a new log analyzer, read in short test log, which is this log file here. It has this IP address. This same IP address appears 3 times, so we've only seen 2 unique IP addresses. We have a third and we have a fourth. All right, then it uses the log analyzers to count unique IPs, to count the unique IPs like we just did, and then it prints out how many there are. So I'm going to go over here to BlueJ. I am going to make a new unique IP tester, and I'm going to run test unique IPs, and it prints out there are 4 IPs, which is the result that we expected. So we're more confident that our code is correct.
Now that you have written code to find the unique IP addresses in a web server log, let us take a brief look at something very close that would not have worked. Here is the code that you just wrote for the unique IP addresses problem. Remember that you have an array list of strings and that you put the string for each log entry's IP address into that array list. But what if you had written this code instead? This code is the same as what you wrote, but the array list holds log entries, and the code checks if it has the current log entry, not the log entry's IP address. Likewise, it adds the entire log entry object if it was not already there. If you were to run this code, it would give you the wrong answer. In fact, it would tell you how many total log entries there are, not how many unique IP addresses there are in the log file. Why is that? To understand this problem, think for a moment about how contains would work. In particular, how does contains know if 2 objects are the same or different? Contains is going to check if they are equal. But what exactly do we mean by equal? Java has two different notions of equality. To illustrate this, consider the situation in which you have three string variables, A, B, and C, which refer to two different string objects. A and B refer to the exact same string object, so they are clearly equal. A and C, however, refer to different string objects with the same logical contents. On the one hand, you could say they are equal because they talk about strings that mean the same thing. On the other, you could say they are not because they are talking about different objects. These are the two different notions of equality that exist in Java. The notion of equality, meaning the exact same object, is what you get when you write equals equals. If you write A equals B, then Java checks if A and B refer to the exact same object. Since they do, this expression evaluates to true. However, if you write A equals C, then Java again checks if A and C refer to the exact same object. But because they do not, this expression evaluates to false. The other notion of equality, do they mean the same thing, is done with the dot equals method. If you wrote A dot equals C, then Java would call the dot equals method in the string class, which checks if the two strings have the same sequence of characters. Because these two strings have the same sequence of characters, A dot equals C would evaluate to true. So how does Java know whether two objects have the same logical meaning? Each class defines dot equals to specify what it means for objects of that type to be the same. If you do not write one explicitly, the default behavior will be to have the dot equals method check if the two objects are equals equals to each other. That is, if they are the exact same object. So now that you know about equals equals and dot equals, should you write a dot equals method for log entry? Well, the first thing you should do is think about when two log entries are logically the same. What about if they have the same IP address? While that would fix the broken code for this particular problem, it's not a good approach in general. It does not actually match with the notion of two log entries meaning the same thing. Two different requests are not the same, even if they came from the same computer. So what if you checked more information? What if you checked for the same IP address and the same request string? Even this would not really mean the two log entries are the same, as the same computer could ask for the same page many times. For log entries, it makes sense to just say that they are logically the same only if they are in fact the exact same object. Because the behavior you want is the default for dot equals, you do not need to explicitly write it. Since you do not need to write a dot equals method for this class, we're not going to delve into how to do it yet. Fully understanding what goes into a dot equals method requires a little bit of knowledge that you will not get until the Principles of Software Design course. However, now that you understand the ideas of equality and that the contains method checks if two objects are the same, you can understand why this code did not work, and why this code, where you use the IP addresses, did work. Thanks.
Great. Now you have completed your first analysis of the web server log file data that you read. You wrote code to figure out how many unique IP addresses there were, which gives you a good idea of how many people visited your site. Doing this gave you some great practice with array lists, which are useful for solving a wide variety of problems. And you also learned about Java's two different notions of equality. Equals equals, which tests if its operands refer to exactly the same object, and the dot equals method, which checks if two objects have the same logical meaning. Each class can define this method however it needs to so that it can provide the appropriate definition of having the same logical meaning. Now it's time for you to solve a new problem with web server logs. For this problem, you'll be writing a program to determine how many times each user visited the website. This information can be quite useful for understanding how people use your website. Do the same people visit your site repeatedly? For example, this person keeps coming back to the site again and again. Her IP appears many times in the log file. Seeing the same visitor repeatedly coming to your site might indicate that they find the website useful because they keep coming back. By contrast, this person visited the site once, but never came back. Maybe it wasn't what he was looking for, or maybe he found the site hard to use. If most users only visit your site once, it might suggest that there are some issues you would want to look into. Of course, as with all problems, the techniques you are going to learn are useful in a wide variety of other problems, not just those dealing with web server log analysis. So let's dive right in. As always, you are going to apply the 7 steps to solve this problem. As with the previous problem, we'll observe that the problem is fundamentally the same no matter what strings you use, and use strings that are easier to talk about than IP addresses. We'll work through this using some animals. We want to count how many times each animal name appears in this list: cat, snake, T-Rex, snake, cat. Now you start by working through this example in a step-by-step fashion, examining each animal and keeping count of how many times you have seen its name. When you have finished looking at each animal in the list, you have your answer. Cat and snake both appear twice, and T-Rex appears once. Now that you have worked an example, it is time to think about and write down exactly what you just did. The first thing was to make an empty table where you could keep track of each name and how many times you had seen it. Saying you made a table is fine, but it is also good to think about what this means in terms of actual data types you can use in your program. What type have you seen that is useful for representing this kind of information? Yes, a hash map that maps strings, names, to integers counts. Once you realize that this is a hash map, you may as well call the columns by their technical names, key and value. Finally, you would want to give this hash map a name so that you can refer to it easily. We'll call it counts. Next, you looked at the first string in the list, cat. Then you looked for cat in counts and saw it wasn't there, so you put it in with a value of 1. You did a similar step for the second string, snake, which was also not in counts, and for the third string, T-Rex. For the fourth string, snake, things were a little different. When you look in counts, you see snake is already there with a count of 1, so you update the count to be 2. And similarly, for the last string, cat, you find that it already has a count of 1, so you update it to have a count of 2. After all of that, the entire hash map counts is your answer. That leads to these steps for this particular instance of the problem. So now it is time to find patterns and generalize to any instance of the problem. Notice that there are several steps where you did not find the current string in the hash map. In each of these cases, you put it into the hash map with a value of 1. Why 1? Do you always want 1, or should you look for some other pattern? If you think about it for a moment, you will realize that here you always want 1. It is the first occurrence of that name, so you have seen it once. There are also some cases where you already had that particular name in the hash map. In these cases, you updated the value to be 2. Again, you should ask yourself, why did I use 2? Do I always want 2, or is there some other pattern? In this case, you do not always want 2. Instead, you want the old value plus 1. That just happens to always be 2 here because of the specific example you worked. With all of that in mind, you should be able to generalize these steps and come up with an algorithm that looks like this. This algorithm makes an empty hash map, then iterates over each string in the input and checks if that string is already in the hash map. If not, the algorithm puts that string into the hash map with a value of 1, and if it's already there, it updates the value to be 1 more than the old value. After processing all the strings, the answer is the hash map counts. Now, you want to test this algorithm out. Test it on the input fish, dog, fish, fish. This algorithm got you the right answer, so you can be more confident that it's correct. Before you turn this into code, we're going to remember that our input is not actually a list of strings, but a list of log entries whose IP addresses you want to process. This slightly adjusted algorithm is basically the same, but we have changed this variable name to LE to stand for log entry, and are iterating over the contents of the array list records, which is an instance variable in the log analyzer class. Then you want to get the IP address out of that log entry and use that as the string that you use to update the hash map. Now it is time to turn this into code.
We'd like to find out how many times somebody visits a website. So we're going to look at a log file that has IP addresses and see, for example, for one IP address, how many times did that IP address appear in the file? That's how many times that person visited the website. So we have a program here, a class called logAnalyzer, and we are going to write the method count visits per IP. So how many times does each IP address visit a page? And what we have in here is we're going to put log entries in an array list. It's called records. So we have a constructor that initializes that array list. We then have read file, which is going to have the file name of the log entries, and that is going to allow you to select a log entry file, and then it just goes through and reads through all the lines and puts them into records. So we're going to focus on writing count visits per IP, and we're going to use a hash map to do that. So the first thing we're going to do is we need to make an empty hash map, and we're going to be mapping a string to an integer. So for each IP address, which is a string, we're going to map that to the count, which is the number of times that IP address appears in the file. So first let's make, let's see, a hash map of type string, which is the type of the key, and of type integer, which is the type of the value for the hash map. We need to give it a name, so we're going to call it counts, and then we have to create a new one. So a new hash map of type string for the key and integer for the value. There we go. Now that we have it, we want to iterate over all the records that we have. So we're going to use a for loop for each log entry. We need a variable name, so I'm just going to call that LE. We're going to iterate over the records where we've put all the records from the file. Okay. All right, there's our for loop. And now we're going to look at each log entry one at a time. So first what we'll do from the log entry is we'll get the IP address. Okay, so we need a variable for that, and that is going to be of type string. So we'll call that variable, say, IP, which is of type string. And we will use the log entry to get the IP address. So if you remember, we have get IP address. And that should get us the IP address. Now that we have the IP address, we have to see if it's already in our hash map or not. So we'll have to ask a question about that. So we're going to ask if counts.contains key. Okay, so again, counts is our hash map, and we're using the contains key function. And we will ask if that IP address is in there or not. And I'm actually going to ask first if it's not in there. So we'll put the not there. And if it's not in there, then that means we want to put it in there for the first time. And when we put it in there for the first time, its count is going to be 1. So we'll add code for that. So we get the name of the hash map, which is counts, and we'll use the put, And we need to put in the IP address, which is the variable IP, and we put in 1 for the count 1. Now, if it's not in there, then we'll want to, if it is in there, then we'll know it's already in there. We need to get the value out, we need to add 1 to it, and we need to put it back in. So we'll do that now. So essentially we're going to use counts.put, but what we're going to put in there is we're going to put the IP address in there again, or basically replace it with, we have to get the old value out and add 1 to it. So we'll have to use counts.get to get the old value of it, and then we'll have to add 1 to that. And then what else we have to do? We come down here. So if we get to the end of that and we've looked at all of the, we put all of our log entries into our hash map, and essentially they're each in there once with the count of how many times they appear in the file, then we can return the answer, which is just counts. So we'll compile this, and let's see. We got to spell get IP address correctly, so we'll fix that. And we've compiled it with no syntax errors now. All right, so now we want to test this out. Again, let's just see. Count visits per IP is going to return the hash map that is all the mappings of the IP addresses to their counts. So you get the whole thing. We need to test it out now. So in order to test it out, we're going to create another class here, which I've started, called countTester. And what we'll do in here is we'll first create a log analyzer, the class that we just had. So we'll create a log analyzer object. We'll just call it LA, and we have to create a new one. Okay, so now we have a log analyzer object. We'll need to pick a file to read from. So I'm going to use the read file, and we'll put in, I happen to have a very small test file to make sure and convince myself that this actually works. So it is called short test log, and I'll show you that in a minute. And then I want to now call count visits per IP. And remember, that's going to return a hash map. So I need to have a hash map variable to put it in. So I'll do that. Hash map of type string integer. I'm going to call it counts. And now that is going to be assigned the value returned by our log analyzer, which is called LA, and that's going to call the method we just wrote, which is count visits per IP. And then once we have that, we can just print out the hash map that we created. So I'll just have system.out.println on counts. Now let's see if this compiles. And we're missing something. Let's see. Oh, we need to use, we used the wrong kind of quotes, so we'll put double quotes here. And we'll try compiling it again. And we forgot the colon at the end, sorry, semicolon at the end. All right, good, we're good. So that works. And I want to show you over here my simple file, and then we'll run it. So I have this very short test file, and you can see it's got 7 log entries in there. You can see the second entry, which is 152.3.135.44, is in there 3 times. Now we're going to run it. So we'll come over to BlueJ Everything's compiled. We'll run count tester. We got to create the new object first. And we'll run. And there we go. And you can see, if I can put both of these up here at the same time. There we go with one. So we created a hash map. And you can see that the one that starts with 152.3 is listed as being there 3 times. That is, we print out the hash map and it prints out each IP address equals its count that we came up with. And so the second entry here is 152.3.135.44 with a 3. And you can see the 157.55 one is only in there 1 time and we got 1. And you can see the 152.3.135 is in there twice, and you can see we counted it twice. So now I'm more convinced that what we wrote is correct. All right, happy coding. Think back to the problem where you found how many unique IP addresses there were in a web server log. That problem was essentially finding out how many different strings there were. If you look at what you just did, finding how many times each string occurred, you may realize that you have solved a larger problem. The solution to the problem of counting unique strings is already here. You have each unique string in this hash map as a key, and would just need a way to turn it into the answer you want. Your counting algorithm has already done the hard work. You would just need to be able to extract the answer from the hash map. This situation is common in programming. You may write code to solve a more complex problem and then be able to solve a simpler problem easily by using the more complex algorithm to do the hard work. Recognizing such situations can be quite helpful to becoming a highly productive programmer. In this case, using the hash map from the second problem to solve the first problem is easy. Hash maps have a dot size method, which tells how many key value pairs the hash map has. As each key appears once in the hash map, the result from dot size tells you exactly how many unique keys there were in the input. If you had written count visits per IP first, you could have written count unique IPs with just these 2 lines of code. The first line uses count visits per IP to solve a larger problem. And the second line uses the dot size method in hash map to turn the answer from that problem into the answer to this problem. The size of the hash map is exactly the number of unique keys, which is the answer to this problem. Whenever you are programming, try to think of ways to use code you have already written and tested. Thank you.
Congratulations! You have solved the problem of counting how many times each user has visited a site. You solved this problem using hash maps, which you learned about previously and should be becoming quite proficient with by now. That proficiency is great, as hash maps are a really useful data structure to solve a lot of different problems. You also saw how you could use the solution to this problem to solve a different problem easily. You could just take the size of the resulting hash map to figure out how many unique IP addresses there are in the log file. Being able to realize when the solution to one problem can be used to solve another is a very useful skill to work on as you develop as a programmer. If you think back to the start of this course, you learned a little bit about cryptography and implemented the Caesar cipher. Now you are going to learn a bit about the Vigenère cipher, which historically is quite important, as it was thought to be unbreakable for hundreds of years. However, as you are going to see and do, the cipher is quite easy to break with a computer. Now, let's see how this cipher works. The key in Vigenère was classically a word. For example, here we picked dice as our key. You write down the word repeatedly to match the message length. Each letter represents a number for how much to shift by. So dice means shift by 3, 8, 2, and 4 repeatedly. In a Java program, it would be quite convenient to represent the key as an array of ints. Now, to encrypt, you shift each letter by the amount written under it, much like you did in a Caesar cipher, but each letter gets shifted by a different amount. The first letter is M, which has 3 added to it, so you get P. The second letter is E, which has 8 added to it, so you get M. Then you repeat this process across the entire message. As we did for Caesar, we'll have to skip anything that's not a letter. Notice that conceptually, this cipher is like 4 different Caesar ciphers. One with a shift of 3, shown in blue, one with a shift of 8, shown in red, another with a shift of 2, shown in green, and a fourth with a shift of 4, shown in purple. This similarity means that a programmer who has already written an implementation of Caesar cipher could make use of it to help implement a Vigenère cipher. In fact, you could make an array of Caesar cipher objects, one with each shift specified in the key, and use them for your encryption. If you did something like this, you could use the mod operator to wrap a count into the pattern, 0123, 0123. For this mini project, we're going to give you the code for a Vigenère cipher, and you are going to write the code to break it. Your goal is to take messages that we have encrypted with Vigenère and find the decrypted message without knowing the key we used. You will start with breaking a message that you know is in English, and then expand your program so that you can try to break encryption in a variety of languages.
Hi. The first step of your Vigenère breaker is going to be to write code which only handles the case when you know the key length and are working with a single language like English. Whenever you're developing software, it's a great idea to implement one feature first, to test it thoroughly, before you build more features into your program. And that's exactly what we're going to be doing here. Remember that the Vigenère cipher acts like several Caesar ciphers for different slices of the message. Here you see a message which was encrypted with a Vigenère cipher whose key length is 4. We've colored the letters based on the part of the key that was used. If you take only the blue letters, you could use the Caesar cipher cracker that you wrote previously to find that part of the key. These letters are basically just a message encrypted with a Caesar cipher, but they're spread out through the total message. Then you could do the same thing with the red letters to crack that part of the key. And similarly for the green and the purple letters. This is the conceptual idea of how to break Vigenère. If you know the key length, you slice the string up and you break each slice using a Caesar cipher. So what should you write to implement this? The first method you'll want to write is slice string, which takes 3 parameters: the message to slice up, which slice you want, and the total number of slices. For example, if you call this method with 4 total slices, and which slice equals 0, you would get the blue letters put together into a string, like this. Similarly, which slice equals 1 would get the red letters, as you see here. The new line character counts as a string. And which slice equals 2, you'll get the green letters in the string. And finally, which slice equals 3 would give you the purple letters. Again, you see the new line character. We have some advice for you to help you write slice string. First, remember the string builder class you learned about earlier. It will be useful as you build up the resulting string to return. You will want to append characters to a string builder object. Second, you will likely want to make use of counting for loops in ways that are slightly different than you've seen before. You've typically had for loops start at 0, but they can start at any number. Here you see an example of a counting for loop that starts at 4. Of course, you could use a variable or a parameter to indicate where you start counting. That will prove quite useful in this method. You can also have counting for loops that count by something other than 1. This loop counts by 7, so it would print the values 4, 11, 18, and 25. Of course, you can count by a variable or a parameter instead of the constant 7 you see here. That may be very useful as you write slice string. Once you've written slice string, you'll want to write the method try_key_length. This method finds the Vigenère key for an encrypted message, assuming that the key length is k-length, the parameter. It also takes a parameter for the most common character in the language. This parameter is for later. For right now, you'll just pass it E. When you write this method, you'll want to make use of slice string that we just discussed. And you'll want to use the Caesar Cracker class. We've provided you with a version of Caesar Cracker that's similar to the one you wrote before, but with a few changes. First, we separated out the code that finds the key from the code that decrypts the message. And second, we've made a constructor which takes the most common letter in the language that you're working with. In this part of your program, you'll just pass the most common parameter. This method should return an int array of length key length, which holds each of the shifts that the Caesar Cracker found for each slice of the message. After you've written try key length, you have one more method to write for this part of your program, breakvisionaire. This is the method you'll want to call from BlueJ. It will set everything up and will call the method try key length. You'll want to use a file resource object to read in the file that you'll want to decrypt. File resource has a useful method, asString, which reads the entire file into a string for you. Once you've read the entire file, you'll want to call try key length, passing the message you just read. The key length, which is given to you at this stage, and the letter E, which is the most common letter. Try key length will return the key as an array of ints. You'll simply pass this to the constructor for visionaire cipher, and you'll make use of its .decrypt method to decrypt the encrypted message. Finally, you'll print out the result. Voila! You are done.
Now, you've written the code to break visionaire if you know the key length. But what do you do if you don't know the key length? Well, you could just try some different key lengths. You could use the code you just wrote and pass it a key length, then see what the result is. Maybe the key length is 1. That output is incomprehensible. 1 is probably not the correct key length. What if you try 2? That doesn't seem to be right either. How about 3? Oh hey, this output looks like it could be English. It has readable words. It would seem this message was encrypted with a key length of 3. You could write a loop to try many different key lengths. Start at 1 and count up from there. The computer can try one particular key length in a fraction of a second, so even if a message which is thousands of lines long is encrypted with a key length of 92, the program can do it in no time. But how do you tell if the key length is right? Do you really want to look at the output for each iteration to say? That's what we did a moment ago. Looked at the output to see if it was meaningful text. But maybe if we think carefully about what we just did, we can find a way to automate it. As you look at the incorrect decryption here, think about how you knew it was not right. This group of 3 letters forms a word, but JOW is not a real word. Likewise, YT isn't a real word, nor is YOB. None of the words in this message are actual English words. Contrast that with the correct decryption. HOW is the word how. DO is do, and YOU is you. All of the words in the correct decryption are actual words. This observation leads to the idea of how to figure out which key length is right. Count the number of real words in the output. You would start by reading a list of English words from a file. You could store the list of words in an array list, but we are going to recommend that you use a hash set, which will give you the same functionality but work much faster. Then you try the decryption for various key lengths. Start at 1 and count up. Where do you end? Well, you could just count up to the message length, although if the key is close to the length of the message, you won't be able to break it, because there won't be enough letters to meaningfully frequency count. For this mini project, just count up to 100. Then, for each key length you try, see how many of the words in the decrypted text are actual words from the file you read in. Once you have done that, choose the key length, key, and decrypted text which give you the most real words. As we just mentioned, using an array list would work just fine. As you read in the file, you would use the .add method to put each word in the list. When you want to see if a potential word is actually a real word from the list, you would use the .contains method. A better option is to use the hashset class. Like ArrayList and HashMap, you can use a hash set containing different types of data. So you need to put string in angle brackets after hash set. You want a hash set of strings. For this problem, you will use the hash set in much the same way as you would an ArrayList. You can call .add and .contains on it. You cannot index into a hash set like you can an ArrayList, but if you wanted to iterate over one, you could do that with a for each loop. That is what has been happening behind the scenes when you iterate over a hashmap's .keyset. The main advantage is that .contains will be much faster. Instead of searching through every word in the hash set, it can look at only a few words to figure out if it contains the requested information or not. The last thing that we will mention before you start coding is how to split a string up into individual words. You've already seen that string has a .split method. You can use that passing in quote, capital W quote. This asks the split method to divide the string up at every character that is not part of a word, spaces, punctuation, or numbers. Once you have done that, you can iterate over those words with a for each loop like this one.
Okay, great. Now you have cracked Visionaire for English messages of unknown key length. But what if the messages were in other languages? What if you did not know the language? Well, you can use the same techniques and just try each language. For each potential language, you would need a list of words in that language and to know the most common character, which is not E for all languages. Then you can try breaking the cipher for each language. You would use the same code you already wrote to find the key length that gives you the most real words in each language. This gives you the best choice for that particular language. Then you just see which language results in the most real words. That is, which language's best decryption is best overall. To do this, you're going to read the words in for each language. You can make use of the read dictionary method that you already wrote. As you read each dictionary, you will want to put it into a hash map whose keys are strings and whose values are hash sets of strings. In particular, the key is the name of the language and the value is the dictionary that you read in with read dictionary. Such a hash map would conceptually look like this here. Here you have a table where the keys are the names of languages. The values are then the sets of words in each language. You might think that this type looks a little complex. You have multiple sets of angle brackets nested together. However, it is a great example of an important programming principle. Do you remember the idea of composition? If you took our course, Programming in the Web for Beginners, you learned about it in the context of HTML. The idea that programming languages allow you to put small pieces together to make larger pieces, and that they obey the same rules when you put them together. This principle lets you make and understand large and complex things. In this case, you can understand this complicated looking type by understanding the pieces. So what exactly do you need to make your Visionaire breaker work for unknown languages? You need to write two new methods. One that counts the most common character in hash set of strings, and one that tries the different languages. You also need to modify two old methods. The break Visionaire method, which is what you run from BlueJ, and the break for language method. You need to write the most common car in method to account for the fact that E is not the most common letter in all languages. So you will count the frequency of each letter in the hash set of strings, which is the list of words for that language. You have seen and done many problems with counting how often you find something and figuring out which of something occurs most often. So hopefully you are getting proficient in these skills by now. The other new method will try each language in the key set of the hash map language. You will want to use break for language to do the work of trying to break that one particular language. You will want to use .get to get the word list out of the hash map to pass into break for language. You will then want to see how many words you ended up with in the string that break for language returns. Fortunately, you already wrote a method that does that. You will then want to pick the best language, the one with the most words, and its decryption. Print them out so that you know what your program found. You will want to make a few changes to break visionaire, the method that you call from BlueJ. Instead of just reading one language's word list, you'll want to read many of them. The other change is that you will want this method to call break for all langs instead of break for language, so that it tries all of the languages that you read in. You will also want to make one small change to break for language. Up to now, you have just passed in E as the most common letter. However, now you will want to use the most common car in method that you just wrote to find the most common letter in the word list and pass that into try key length. So now that you know the plan, it's time for you to devise your algorithms and write your code.